started. So
Yeah,
yeah,
I know.
yeah, and she moved
So, and the ladies that are here from the organization, who were right there.
Oh, good. Okay. I'll go and introduce myself. And I saw over at the watershed, great commissioner.
This is a great group. Okay, good morning, everyone. I gave you your last warning. It's like a football gets a 2-minute warning. I gave you 5, so we're going to try to get started here. I guess first of all, I'd like to thank all of you for taking some time from your busy schedules to attend this meeting. I know it's a lot to ask for a lot of you because it's tough sometimes to make a choice of where you're going to try to be in a given day. And I hope in return that we're going to offer a lot of very good information and connections for all of you to enhance what your individual role is. I think that we are very fortunate to be able to use this facility, and I want to make note that the township's been very supportive of all our activities, and in particular, trying to set up meetings like this. So I wanted to make sure that I said a little bit of that about that. Okay, so we've shut the doors, and the reason for that is that the township has their normal business hours, and we don't want to interrupt them, and we don't want them to interrupt us, of course, either. But it doesn't mean that if you need a bathroom break or something during the presentation, you're still welcome to go out, use the restroom, whatever, grab another cup of coffee. The only thing I would say is be mindful of the fact that this entire meeting is going to be on YouTube video. It's being live streamed, and it'll be recorded. So we just want to be mindful of that to minimize interruptions. Also, the presenters and anyone asking questions, we're going to provide a microphone. We're going to ask you to speak into it, not only for the people in this room, but again, for the videotape. Oh, I have this little thing here. This is a hearing aid for anyone that needs a little bit of help with hearing. I suffered some ear damage a couple weeks ago in the shooting range, and I decided to try one. They actually work pretty nice. And Mike Strange, Mike, stand up, say hello to everybody. He's our technician. He has a supply of those if anyone wants to use them for their convenience today. And anytime there's any questions or anything that you want to understand, either ask Mike, myself, or any member of the team. Okay. So you've got a copy of the agenda. We got a couple of little minor changes on it. I'll be going over with them. We have a lot of information we want to transmit. So in order to manage our time, we're asking that there's a little blue card in your folder to write down any questions you have for 2 reasons. One, to make sure you remember the question, and then that'll give us a chance to give it to the right presenter and give them a chance to prepare an answer. At the end of the agenda, we have allocated time for Q&A and discussion, and we want to make sure that we answer everyone's questions that we possibly can. And any questions that come up that we can't have an answer immediately, we'll follow up with those with the right people, the right subject matter experts, and get an answer to you. There's going to be some exceptions to that rule. I know that, for example, Dr. Robertson, when he goes through the USGS data, there's an awful lot in there, and we're going to try to manage our time, but still allow some time for questions at the time of the presentation. And we're going to try to keep that on pace, but at the same time, give everyone an opportunity to exchange. There is a little survey, a blue survey that's in your folder. And this is the deal. There's no free lunch. You got to fill out the survey in order to earn your lunch, all right? But it helps us because we do hope to have another adaptive management meeting next year, and any improvements or anything that we could come up with from your suggestions, we'll be able to incorporate. And last but not least, a little bit of details and a welcome. We notified everyone that there is a social and a dinner following this meeting today at the Torchlight Cafe. Whether you RSVP'd or not, if you would like to attend or attend portion of it, please do so. It's a nice casual setting. The hors d'oeuvres will be set out at 5 o'clock. It's a buffet dinner. It'll be out at 6 o'clock. Very casual setting. We have reserved the back room at the cafe, which includes a little patio outside. It's a very good opportunity for people to be able to exchange communications and stuff. So we hope that that accommodates everyone. Yep. Well, I touched the keyboard. Here, I gotta walk around the other side. I meant to turn that computer around. All right. There it is. Okay. Okay, at this time, I'd like to introduce the project team that has been working this project for a couple of years. So would you please stand up as I read your name, just to be recognized, and also so everyone knows who to turn their questions into, the project team members of the people who do it. Of course, I'm Tom Joseph. Rick Knopf and Bob Millern are not here today because of family issues that took them out of town. Wayne is right here. Say hello to everybody. Sarah, say hello. You might have to stand up. I don't know. Peg Comfort, she managed the greeting table, so everybody got to see her. And Trish, you'll see Trish a little later with a presentation. Bruce, there's Bruce, and of course Dr. Dale Robertson and James Wilkerson. Jim, where are you? Oh, there's Jim. Anyone that has an interest in understanding of what we do in our field, Jim's the guy. He did all the field work, or ran the field work, because he obviously had to have help. And I've learned a great deal from him, and I think it's good to know Jim. So why are we here today? This is our focus. Our focus is Torch Lake. Many of us are very vested emotionally, financially, and family-oriented wise to see the precious resource that we call Torch Lake, which is part of a large chain of lakes, remain as beautiful for future generations as what we've been able to enjoy. And we want to keep that focus on that. There's science, there's a lot of different aspects, but our focus in our organization is the lake. And we just hope you can join us in that. So on the agenda, we're right on the number 2. The highlighted areas compared to the copy that you have, we're going to adjust a little bit where we are going to introduce Sherry Martin and her groundwater information intermixed in with the Dale Robertson's presentation a little bit, and that's to keep the 2023, 2024, 25 data a little bit separate and move a little smoothly. So that'll work out. Another reminder, during the lunch break, that's a good time to start filling out the survey. I mean, we don't need it till the end of the meeting, but we just want to make sure that it's not a free lunch. Now, Dr. Jan Stevenson, who's been involved in studying Torch Lake and specifically the Bethnic algae for over a decade, does have a presentation today. Unfortunately, he can't physically be here. So his presentation is going to be by way of Zoom through the computer. And we'll have to make special arrangements and any questions that are oriented for him. But he is very supportive of this activity, and I just wanted to be aware. Also, Heather Hedinger from the DNR, the Michigan DNR, had a conflict today, but she sent us a video of her presentation. We'll be able to see that, and we'll have to handle questions outside of the meeting. The other highlighted areas last year, if anyone has participated with us in 2022, we had a roundtable discussion, and we thought we could do a repeat of that this time, but there wasn't enough response to make it a formal item. But we wanted to have time available for anyone in the audience that is involved in a current action to make sure that they have an opportunity to share it with the group, and particularly the USGS team, because as we uh, go forward in our adaptive process to modify our future plans, we want to make sure that we're consistent in with other activities that are involved in the lake. And number 14, Josh Fay is the person that is putting together the project for the mussel survey on Torch Lake. He's in South Africa, so we couldn't zoom him in. So Wayne Lancaster graciously accepted the or volunteered to give the presentation for Josh. And I think that the only other thing on the agenda is make sure that the questions are, we really want to have an interaction time at the end of the meeting for Q&A. Any questions on anything in the room? Okay. Then we're going to go to the next presentation. That should do it. Okay. So just a little bit about the background of why we're here today, what this is all about, when it started. I call the journey. If you ever study the history of Torch Lake, I find it completely fascinating. Maybe that's because I'm a mechanical engineer, not a limnologist or something that's takes a lot of things that they know I don't know of at all. But it is fascinating that sometime like 11,000 years ago, the glaciers start moving around and they form Torch Lake. Okay, uh, and most things that you read tell you that Torch Lake at one time was part of Lake Michigan. And the reason why I bring that up is that anecdotally, many times that we find things that we're learning, they're closely follow Lake Michigan more so than inland lakes. So I think maybe that's relevant, maybe it's not. Okay. And where it connected to Lake Michigan is about 1 mile, maybe less than a mile north of where we are here today. So we happen to be very closely related to that. Now, when the glaciers moved back and forth, they crushed up the limestone and they left calcium carbonate. And that's part of the reason for the color and the clarity of Torch Lake. And that plays a big part in our analysis. Now, in this time frame, the lake was able to develop naturally without the interference of man for many thousands of years, and that's probably why it was so nice and pristine until man arrived on the scene, and we don't seem to do things very well to the earth. So some of the things that happened to the lake was fish that were very plentiful at one time have been reduced and without regard to sustainability. The shorelines were stripped, especially for hardwoods. The interesting story, when Chicago had a fire, they needed a bunch of lumber to rebuild Chicago. Northern Michigan was ravaged for their pines and hardwoods, okay? And unfortunately, at the time, the logging industry was not very sustainable in their practices. And our watershed was affected by that greatly. Unfortunately, the resources in the area were exploited by few for profit. And the logging industry, it was just it was sad to see some of the pictures that go back in the late 1800s and early 1900s. But following the logging industry, even development had very little concern for the health of the lake. So now we're going through that time period where all too often the people that have come to enjoy the beauty of this beautiful resource are in fact bringing the most damage. And it's our job to educate those people. So in the last century, there's been a lot of reason for hope. And it seems like once the logging industry people left, the people that stayed behind started woken up and said, well, we got a pretty nice area here. Maybe we got to take care of it. And little by little, things have improved, but there just wasn't enough people dedicated enough or with enough authority to really turn things around. And then in the last 20 to 30 years, there's been a pocket, a number of people with the dedication and the effort to try and regain the clarity, the cleanliness, the protection of the lakes. There are multi-generation people. I'm looking at a couple of them in this room, all right, that have dedicated most of their lives to taking care of the lake and the chain of lakes. Uh, we want to be part of that. We want to be part of that heritage. This activity is dedicated to trying to preserve these resources that we have. And I want to highlight there's one bright spot, at least that I've become aware of, and that's the Elk River Chain of Lakes Water Improvement Plan. Uh, Everything that we do is going to help to support and supplement that activity. And in fact, hopefully, that is going to be one of the driving forces to sustainably maintain this resource. So today, physically today, I find us in a pivotal position. We got a name for what we're doing. It's called Keep Torch Blue. It's intended to supplement the work that's been done by so many and build on that work and develop a sustainable monitoring plan well into the future. So if you go back to 2022, our first meeting, we took a year and did a lot of research. We collected a lot of papers. We tried to analyze them, organize them, share them, and find a baseline or starting point. When we go through and listen to Dale Robertson's presentation from USGS, that's going to be key to understand that we had some baseline and we're trying to build on that and find a way to the future for an ongoing long-term monitoring program. All right. So today, some of the information should help us with the what's going on in the lake and what the health record of it is. And there's still a lot of work to be done. But the key thing is that we have to maintain our focus on our goals because there's too much at stake. The chain of lakes, Torch Lake, just too precious of a resource to not do it. Okay. So we coined a phrase in our first meeting when we said that that meeting was not a destination, but simply a step along the journey. And today continues that journey with another step. I borrowed this picture from Dale because I don't know how to draw pictures on a computer. But so the Keep Torch Lake Blue project, with the help of USGS and their guidance, takes a look at everything that affects the lake externally, the atmosphere, the input from tributaries. Fortunately, we don't have industrial or urban development around Torch Lake that influence it. Those are two things that he might have to worry about on other lakes. At least we don't have those. We do have our agriculture, and agriculture is something that we're focusing on because there's anecdotal information that that might be part of the influence on the lake. All right. There's one thing that's indicated but not shown. It says biotic, and we're going to talk a little bit today about invasive species, specifically mussels, that not only are impacting the health of our lake, but we want to get a step ahead of it. And I think we're going to find some very information on that. But that's what our Keep Torch Lake Blue project's all about. So real quick summary. Dale's going to go through this in detail. He's a scientist, but at a high level, 50,000 feet. So when we put together our original plan, the key things were we monitored open water and nearshore sites. We monitored them every month. We took a lot of samples. We analyzed them. Now, I'm impressed with numbers. Some people aren't. So GLEC, the Great Lakes Environmental Consultants, they've been analyzing our stuff every single month. We got like 561 data sets. That means we analyzed for multiple nutrients out of each sample. And we've done that every month since April of last year. I think, Jim, right up through December, right? We even got some readings in December. We've got automated gauges set up at Clam and Torch River to monitor continuously the inlet, the main inlet and the outlet of the Torch Lake. We collected plankton samples that we're going to hear the analysis of today. And we did that April through November. And Phycotech analyzed 27 tow samples, generating 81 reported data points. And that was the phytoplankton, zooplankton, and villagers. So we've got a lot to cover. Dale gets to do the hard part. He's doing that. Real quickly, and Dale's going to talk a lot more about this. So I want to make sure that people that are within the chain of lakes are aware of what these gauges that we talk about do. So they measure velocity of the water flow. They measure the height of the water at the inlet and the outlet. And then by way of calculation, calculate the volumetric flow. And this is the record for the last 12 months at Clam River Inlet. That record can be broken down by day. If there's a chart, you can have it in graph or in chart form. That data becomes very useful when you want to do calculations, like load calculations. And there's a website you can go on. It's public. We make it available to everybody. And like I said, Dale's going to give you some more on that in his presentation. But I want you to make sure that we're all aware of that. So in 2024, we already got started. We've been very busy already this year. We're going to continue much of the sampling that we did in 23. We're going to expand our tributary inlet monitoring. We've got a nice new setup at Spencer Creek. Dale will go over that with you. And then we're going to add Eastport, Wilkerson, and Auguming Creeks to monitor them biweekly, grab samples and analyze them to see what influence from the tributary areas are coming in. Atmospheric deposition setup is done. We've got a buoy set out in the lake now with thermistors that go all the way down on the bottom so we can measure vertical mixing. And we're going to talk about groundwater sampling. Sherry's going to cover that with us. So the next step is to talk and think about 2025. And that's some of the input we're looking for. Have we missed something? Are we doing too much of one thing, something else, or we should do something more of something else? Those are the kind of inputs we're looking for because we're going to adapt for 2025 and what we learned today. So now I've done the easy part, and I'm going to introduce Dr. Dale Robertson, our USGS team leader, to take over the real stuff. This is a bio. I think that everybody got a copy of the bio in the first email, and it's critical to me to be surrounded by people that have been doing this a long time and are really smart at it. And Dale's been a terrific leader for us, and I can't thank enough for all his work that we've done. So that's his background. We're ready for you, Dale.
All right, I think Tom finished off my talk already, though. All right, I just wanted to, first of all, before I get started, just wanted to introduce my team. Jim was one of the ones that was mentioned before. He's doing most of the sampling out here right now. It made it sound like the way Tom was describing it, that it's done. We're only a year into this. We just started, all the sampling that we started, actually started about last March and April. So we're just really getting going. I'd like to really show a lot of results today, but it's really only 1 year of data. And you know how 1 year can look a little different than another year. The other person that's going to be really heavily involved is Sherry Martin. She's going to be doing a lot of the groundwater work. We just really are just starting to do that. We're just starting to look at the models, the past models that are out there, and we'll be putting in a number of piezometers that she'll be talking about. And then Leon Quintona, he's really new to the survey, new to this whole program. We're hoping to get him a little bit more involved. He's more of a plankton person, knows a lot more about that than we do. So he'll be looking at that a little bit more, hoping to interact with Jan Stevenson. One of the things that Tom talked about is whenever you look at water quality of lakes, you usually get into this whole idea of eutrophication. And eutrophication is a natural process, just a natural aging of a lake. And how it ages through time is really a function of nutrients and time. It's how much nutrients get into it, basically with respect to the shape of the lake, where it's found. And some lakes go through this very different than others. When it formed 10,000 years ago, some of those were fairly shallow. The nutrients accumulate a lot quicker and it moves down this whole process. Then there's others lakes like Torch. Torch never moved, really. It's still way up on the upper part, but there is concern that it's moving downward. So we have this natural process going from an oligotrophic lake, low nutrients, low productivity. The fish you can catch, if you catch them, are sort of nice. It's hard lake to fish though. And then you move into that mesotrophic range and finally into the eutrophic. And the idea here, normally when I give a talk to a lake group, I'm way down below this and trying to say, what we can do to get out of it. Here we're way up on the upper, we're actually beyond the upper one. I would consider Torch not even a oligotrophic, but an ultra oligotrophic. It's one of the nicest lakes around, but there's always still concerns. And that's really the concern here. And that's a concern across the country. Wherever you have water, basically, we have to worry about this excess nutrient loading. And you don't want a lake like Torch to turn around and all of a sudden to look like this, or even Lake Erie, other places where you start to have more than just problems with algae. You can get into problems with oxygen and other kinds of things. So that's really where we are. This is the side where it's just a natural process. But if you get that excess loading, that whole thing can really change. Instead of looking at thousands of years, you can go down to tens of years and have a lake really go down really quickly. Would Torch turn that fast? No, but it could still change. We start up at that oligotrophic. We're trying to keep it at that ultra oligotrophic range. And that's usually where, all right. There it goes. Okay, that's where lake management usually comes in. It's trying to stop this rapid changes in time. This kind of thing, it's a little bit harder to do anything about. It's usually natural sources, and it's really hard to control those. But in lake management, we're really trying to slow it down. And in some cases, we're actually trying to reverse that. And really, when you're looking out here at Torch Lake, there are only a few things that could possibly be reversed. And one of those is benthic algae. Now, can we reverse that? Depends on what the sources are. There's a lot of studies that have been done on it already. And a lot of those are trying to find out what the causes of that are to try to see, is it even possible? Is this a natural progression in a lake? Or is there something leading to that that can be done to try to prevent or to reduce the amount of algae in the lake? And Tom mentioned this. So a lot of this concern about the changes in the water quality of the lake led to this whole project of Keep Torch Blue. And with that, it started a few years ago. And in 2022, a whole team of people, I had very little to do with this, put together this whole package. And it was trying to assemble all the studies that have been done. The real hope was here is to assemble all those studies so we wouldn't have to repeat them. And because there's a lot of data has been collected. I'll show you a number of time series. It goes back a long time. But the question is, are they good enough to really look for things in the future? And as part of that, if you get into here, there's a USGS research project. It says 22, but it really started last year. 22 is really just to get an idea of what we could do on the lake, what can be studied, what can we understand, and try to really sort of lead into a more in-depth management plan. If we can find out what's driving this, we can look at what can be done. Okay, so if we go back to that one, in here it's a research project, so we had to come up with what did we really want to look at. So we went through there after we looked at some of this, then we came up with a plan and what we thought we should sample out here. And in there, we wrote a proposal. And so starting in 2023, we wanted to start looking at the water quality of the lake, keep it going. We knew that there was some data out there that's been in a series of reports. Some of those are every 3 years, some are annual. But what we wanted to do then was to look at I was most interested in the open water areas of the lake. And then there were others that wanted to push for the near shore. So we not only look at the open waters, but I'll show you some of our sites. We're sampling around the periphery of the lake. That's where people really feel the water. Some are, I'm looking at my audience, some want to get out there and really test the temperatures a little bit more themselves. Okay, so that was the first part. The next part was to try to figure out what's driving the water quality. It's going to be loading of some sort. It's that whole part of nutrients coming in from the watershed. And so the past studies, I'll be referring back to a study that was done in about 2005, 2006, right in there. And they did a really in-depth study. Very good study. I'll argue that it's pretty lousy data. But the study itself was good. If they would have had the data to back it up, I would say we would be a lot further along. But one of the things they showed is that the Clam River was a major source. Not surprising. If you drive around, that's where most of the water is coming from. And arguably, it's about 85% of the water coming in is through the Clam River. And so we really wanted to sample that. And we knew we had to do that in a much more rigorous way than was done in the past. We also wanted to see what was leaving the lake. Not so much water quality, because that's not really what's affecting Torch. That's affecting the lakes downstream. But we really want to know how much water was leaving, and that'll give us a much better idea to do a nutrient budget and so forth. We also wanted to try to overall look at all the water, the sources of nutrients coming into it. One of those is groundwater. Sherry will talk about that. All of these things I've talked about have been looked at in different levels in the past. And then the other nutrients, things like atmospheric deposition. That was also studied. We want to look at that a little bit more. And finally, it's a big lake. We're mostly looking at the middle, but we wanted to see how much mixing is going on, how much variability there is from one side of the lake to the other, how much everything is moving around. So we're looking at the vertical mixing in the lake. Now, once we get all done with that, this is all the things that we were supposed to have started in 23. Can't say everything's started. A few of those are starting right now, but that's the basic monitoring. Once we get done with all the monitoring, we wanted to start looking at what we can do with that, and that usually comes in with different kinds of models. There was that study in 2005, 2006, where there was some models out there, and we're going to try to follow up on those with a little bit better data and see if we get sort of the same results. A couple of the models that were out there, some empirical ones, Lake 2K. It's a semi-processed model that was run by a number of people, maybe somebody on the phone who ran Lake 2K. She was hoping to listen in on this. And finally, here's the hope, it's really a hope. I don't know if we'll get there because really one of the main concerns on the lake is golden brown algae. And we really want to see, can we find out what's driving golden brown algae so we can put it in some kind of model to say what can we do to prevent it, reduce it, get rid of it, that kind of thing. But to do that, we have to know what's driving it in the first place. We don't know that. Ken might talk, I know he'll talk about it when he talks, but we still don't know what's driving golden brown algae. So without that, we really can't say, or I know we can't model it until we know what's driving it. Because a model always going to do what you tell it to do. And it can quantify things, and you can put it into context, but if you don't know what's driving it, a model's not going to tell you what's driving it. Okay. All right. Come on, there it goes. So as I described all those things that we're doing, where's Fred? I'm sure he's saying, well, I'm sorry. I'm sure we looked at this all in the past. Why do it again? We're looking at water quality. Heck, we got a lot of data out there. 2 years ago, Doug Endicott came in here. These are a few of his slides, just two. And he showed a slide like this. And here's the phosphorus concentrations in the lake from 2004 to the present, or to 2022. And it looks like there's a real nice trend in the data. But one of the things he did is when he looked at it, he said, well, I don't trust my own data. I don't trust the data, well, not his own data, but he doesn't trust a lot of the data that went into it. And just so you know, I did not change this slide. So he wrote this down. It was the Endicott rule. Basically saying anything greater than 5, I don't trust. Maybe we shouldn't lose it. Those are outliers. Maybe they're contamination. Maybe they're the lab. Maybe there's something else. So they're probably not good data. What did I say? Okay, micrograms per liter. I don't like to use parts per billion in the first place. But usually it's micrograms per liter, and that's what it is here. So it's numbers up around 14 and as low as 1. So they're a wide range. I actually went into the numbers that when they did this big study back right around in here, and I think what happened with some of their numbers, because they were getting some really low numbers. I'll show you that in a second. But then they decided to do something, they wanted to do a composite. I think they stuck it into a bucket that completely contaminated their samples. And even they saw that, so. But anyhow, so there's some real problems with the water quality that was measured. And what Doug had said is these are extremely low concentrations. The ones that are reliable are extremely low. And that was a big start. If you remember back in 2022, a big thing we wanted to do is to find a lab that we could trust and get down to these low numbers. A lot of labs, they only go down to 3 micrograms per liter. They think that's great, that's good, not good enough for this lake. We had to get lower. And that's why we went with GLEC. GLEC has a detection limit way down here, below these numbers. So we were not hitting detection limits. That's just phosphorus. The chlorophyll numbers that have been collected, you go through the tip of the mitt and other things. Yes, they're low numbers, and that's really good on a statewide survey. If you're the best one basically in the state, that's great. You're the end member, but that's usually not good enough. And if you look at this, all of these, the ones that have these big lines, those are all less than detect. So it's not really telling us much for trend analysis. They're all just very low numbers. Okay, so that's the sort of the water quality that's been collected. Here's this big study. It's done very well in a lot of ways. It's a study that was looking at modeling what was going on. And when they did that, here's some of their raw numbers. You know, like I said, they were down there. They hit really well, and then all of a sudden, boom, something went wild up here. I think what happened with a lot of those is that they were trying to composite it over a zone. They dumped all their samples into a bucket. I think they completely contaminated it. And all of a sudden, you get a 20 or something. If you look at this lake, you know 20 is not real. So anyhow, this is the kind of concentrations that were out here. And to take something and just say, well, anything worse than 5 is not good, because what about a 4.5? Maybe that's partially contaminated. You know, so anyhow, it gives us some problems there. They did a water balance and a nutrient balance. In the water balance, when they went out there, they're looking at it, broke it down to precip, tributary, and groundwater. Here's some data right out of their report. Here are the flows at the Clam River, Torch River, Spencer, and what other one did I want to Wilkinson. And so there's a range of kind of things out here. But if you look at it, it's only summertime, happened to be a dry year, and the numbers are pretty low. I'll show you some numbers that we collected. I don't think we have a number that went down that low. And in fact, when they looked at these numbers, I don't think they believed it either in some ways, because what they did is they ended up taking those numbers and extrapolated them from a nearby gauge in the end. So there's some problems with the Clam River, which is 85% of the load to begin with. Then you look at Spencer. Well, that's really nice if you want base flow. There's no variability in the flow from there. It went from 6.7 to 12 CFS. So there's very little variability. And if you're looking at trying to figure out what's coming in Spencer and you're only sampling it during base flow, well, there's talk about the water going up even a couple feet over there. We haven't seen it go up near that much yet. But even going up, so they're only sampling it during base flow. So try to get whether you want a water balance or a nutrient balance, you're going to be really biased. You're going to be having these numbers way lower than what that river is probably really putting in. And then finally, you get over to something like Wilkinson. They have 2 samples. And again, is that anything indicative of the flow or the concentration? Probably not. Trying to get something out of that is really tough. Okay. All right. The phosphorus inputs, this is where it gets pretty interesting because that's really a big part of the effort we're looking at. They broke it down to precip, tributary, and groundwater. And here are just some numbers if anybody was really interested. So when you're looking at it, they had 4 concentrations in the Clam River total. Actually, that may not be terrible. After looking at it, it's a lot more stable than I expected. But other ones, you look at this, and there just isn't much to go with. If you're computing loads in a river, first of all, you need good flows. The other thing you need is good concentrations, and I don't think they had either one of those back then. And so we're putting a lot of effort into it. Tom mentioned that, and I'll show you what the gauge that we have in over there. Groundwater, actually, this might be totally reliable, which is pretty interesting. But they didn't sample a lot, but they have a bunch of gauges. Fred, I'm still trying to figure out where these gauges are. So if we can find out where those gauges are, that's going to help Sherry and us get along. I don't even care. If you can put an X on the map, yeah. If you can put an X on the map, that'll help because then we can compare ours. But anyhow, I'd like to get, this is something that I think we can trust, but we'll be wanting to go out there, replicate it, and we're going to put a number of piezometers around. Precipitation, they were trying to estimate how much is coming in. Normally, when people are doing lake studies, this is blown off really quickly. On this lake, no. This one might actually be our biggest source of nutrients coming into lake, and I think it's going to be important. But if you look at this, they were looking at 4 places back in their study. When you get something like, this is the maximum concentration of, it's actually 214 ppb or micrograms per liter, you know there's something wrong. You're not going to get that in precip. So I think there's some numbers that they collected, but I don't think they're very reliable. If they are, we're going to repeat it and we'll get the same numbers. But the idea is to go out there and collect some atmospheric deposition numbers so we can get that. So ultimately, we'll be putting the tributaries, groundwater, and all this together with some numbers that we're going to start collecting or have been collecting already and try to get better estimates for the lake. Okay, so next brings us to the monitoring parts. Well, Tom already did it, so I'm done. Okay. The monitoring components. I'm going to go in this a little bit more in depth than Tom mentioned. Whoops. We're sampling mainly 2 spots in the lake. There's been a number of spots sort of like this. If you look at it, somebody's usually sampled over on the deep hole. This is the deepest part of the lake. They've been sampling somewhere around here. That's been shifting depending on which study you look at. It bounces around. But for the most part, this whole area is very similar in depth. So I don't think it makes any difference at all. So it should have been all right. Then we're sampling up on the northern side of the lake, trying to see, there's been a lot of talk about possible variability. So we're sampling both locations. Then I'll talk a little bit about, Tom mentioned nearshore. We ended up sampling 12 locations last year, and I'll show you some of the data from that. Then for loading, right now, we talked about clam, what's leaving in Torch, some of the things that we'll be adding to it. Those are going to be mostly done by a combination of USGS and volunteers. I'll talk about all these in more depth in a second. Atmospheric deposition. Right now we're sampling, or plan to sample over there. Oops, boy, that was not a good thing to do. We're just trying to get that thing going right now, and we're going to start at Grayling, get everything going, and then move it over here. And then finally the groundwater part of it. And the idea is to put in some piezometers. Sherry will talk about this so that we can get an idea of what's coming in there. Okay, so for the open water, we're sampling 2 locations. Whoops. Like I said, if you remember, some of this goes back 2 years ago. We were trying to the number one thing we first wanted to figure out was what was the maximum depth of the lake. Was it 350 feet or was it 250 feet? 2 years ago, we weren't sure. Now we're pretty sure it's pretty consistent, right? I don't think many of the maps are right. We think we've got the deep hole, or real close to the deep hole right here, and it's under 300 feet. Okay, so what are we sampling? Hopefully none of you can see this, because it's just trying to say we're sampling a lot of stuff, okay? So what we're doing is we have a pretty elaborate, this is the south part of the lake, the deep hole. We're measuring a lot of things. We were just out there yesterday. We're collecting things like metals. We want to do that once a year, just try to figure out what's the baseline so that as we go forward, are just some unusual metals changing through time. This is where some of these studies, like people started sampling and all of a sudden they realized this is something we should sample. We'll put a baseline out there. If that gets to be the metal of choice in the future, hopefully we'll have a baseline to compare it with. Mostly what we're doing is measuring nutrients, chlorophyll, alkalinity through here, monthly throughout the year, and then with depth, mostly nutrients. Just really trying to quantify this in a good way, trying to find out, especially near the bottom. I was arguing that I thought there'd be a considerable amount of nutrients coming up from the bottom. Wanted to see if that was right. Then over on the north side of the lake, way cut back. We're primarily just doing nutrients at the top and the bottom. So very basic kinds of things. The other thing that I didn't mention is during 2023, we're also measuring phytoplankton and zooplankton, mostly just a composite from the euphotic zone right now. Okay, all those went to Phycotech, and I think Trish is going to talk about that. I'm not going to talk about the plankton today at all, but we're sampling those at both locations in 2023. So for out in the middle of the lake, we bring out our. Boy, Jim, you're going to have to paint that thing. Anyhow, maybe it didn't show up that well. So anyhow, we take out the boat, head out. We do our typical limnology kinds of things, do a profile from the top to the bottom for things just showing the stratification, dissolved oxygen, conductance, pH, just the real basic limnology. Just looking at how things are changing through time. These are the temperature profiles, starting off with isothermal conditions, same from the top to the bottom. In the springtime, you can see it stratifying. It gets stronger and stronger and stronger up to July, and that starts the thermocline and decaying. So nothing too wild or crazy. This is what we expected. But now we got a better idea where the thermocline sets up and just where we expect to see the changes in the lake. Wanted to make a few pretty plots to show you what it looks like. This is time going across the bottom and depth. And you can see that thermocline setting up here. That's the difference where the colors start to change real dramatically. Thermocline setting up and breaking down. And we end up with a really fairly long mix period. Still hoping that we might get to see a little bit under the ice. This was not a good year for looking at ice in Torch, and maybe we won't see any in the future. But if we do, we sampled all the way out to December and then turned around and sampled in, Jim, I think March was the first time we got back out this year. So we sampled it pretty elaborately. That's just temperature. We also sampled the two sides of the lake. If you look at this, one of the things I was trying to do is color code, trying to see, do we really see any differences in temperature? So if you looked at that, yes, we see some differences in the thermal. For the most part, the two colors are right on top of each other. You can see it good right here or there. Here is a little bit difference of right near the top, but for the most part, they converge down to the middle. And then due to that, like I was talking about, the middle of the lake will seiche back and forth. And that's really what you'll see is that even though it looks a lot different, if you're a fisherman, maybe that's important for you to chase the thermocline around. But for the most part, it's just a seiching in the lake. And that's what's going on here. When the wind's blowing here, yes, this big setup here looks like feet. That might be an inch from one side of the lake to the other. But down here, this can be as much as like 10 meters. 30. I wouldn't doubt if this thing were sloshing 30 feet up and down. And to measure that, that's where we do have a thermistor string out there. We just put it out there earlier this week. And that'll help us trying to say how much variability is there from one side of the lake to the other. Also measuring oxygen. One of the things that this is not, it sort of starts off the same top to bottom. As the summer goes on, we start to lose the oxygen in the top. It's mostly just because warmer water holds less oxygen. So it's not really too much of anything that you would expect or that you wouldn't expect, but you see that. And the lowest oxygen concentration during the entire year is still almost 12 milligrams per liter. So the oxygen is still really high. Not what I expected at all. Even though the past studies sort of said this was going to happen, I really expected to see it really taper off near the bottom with a potential to show internal loading of nutrients. So when we put those two together, we got temperature on the top, oxygen on the bottom. It looks like this is bad, but that's just because of a temperature. Temperature gets warmer, saturation values drop, and we're seeing no anoxia in the lake whatsoever. And that's good. And we're not even close. Like I showed, it was like 12. The lowest we're seeing down here is about 11 or 12. And so if we can keep it that way, that'd be great. Okay. Also look for the differences in oxygen from one side of the lake to the other. And here we do see a little bit. I don't want to get into the curves too much, but later on in the summer, the north has a little bit less oxygen than the center of the lake. So there's a little bit more oxygen depletion going on, but still, it's still well over 12. So even though there's a little bit more oxygen being consumed on the north side, it's still much higher than anything to can be concerned about. Okay. How about Secchi depth? Just how clear is the water? This is the one thing that we have some great records for in this lake. Most people that are going out there, it's just looking at using your eyes. You don't have to worry about a lab or anything else. Just how far can you see down in the water? And you see a gradual progression from about 18 meters, great water quality, dropping down to about 4 in September, and then as it goes down, as it goes through into the fall and winter, it marches its way back up. But when you're looking at 18 meters, that we should have measured the other day when we were out. We didn't do it last time. What's that? It's deep. Yeah, it goes down a long ways. Now, the thing that's nice is, like I said, this is a great data set. We have data going back as far as I could find Fred was helping me try to pull a lot of this stuff together, going through all the records. After grabbing everything I had available, this is what I came up with. This is what Doug presented, a lot of this, just a little bit more in depth. But if you put a time series to that, you can see water clarity is gradually getting better through time. And the best we've seen is just a few years ago, and it's dropped off a little bit since then. Is that a significant drop? I don't know. A little bit of variability going on. But overall, things have improved. Part of this might be due to the introduction of mussels. Hard to say what else, but that's what we see. So that's what I really want to have for all the time series we have. It'd be great to see this. We can see when things are better, when things are worse, and then we can start to look at the other factors driving it and see if we can figure out what's going on. Phosphorus concentrations, a little bit noisy. And this is where 1 year data doesn't, sort of gives us a good mean what's going on. It's about 4 micrograms per liter on average. But this is where I want to have more than 1 year data and see, is this a seasonal progression in the lake, or is it mostly just noise? Right now, if you look at it, it starts off, when we started off right around 2 micrograms per liter, bounced up to about 4 to 5, and moved around. We did get one fairly high value. But even at the high value, it was only 7 micrograms per liter, so much lower than before. Now, this is where it'd be really nice to put this into a long-term perspective. And this is when you take all the data that I could come up with, the data that Fred was helping me with and everything else, you put it all together, and this is what we come up with. Now, we can argue if there's a trend in there, but I would argue that all this is probably crap up here. It's hard to say anything else. I think it's all either data that's been contaminated one way or the other. A lot of these numbers down here, even back then, here's where the lab's detection limit was at the time, was about 5. Now we went from a detection limit, so those are these open circles, went from 5, now we're down to 0.5. So we have a little bit more. The other thing that's interesting here is that if you look at 2005-06, this is where this study was going on here, and they really tried to get those concentrations down for their study. And they did for the most part, but they also had some at 13, and that's where I was talking about, where I think they can put it into a composite sampler, mixed it all up, and I think they contaminated their samples. Because if you looked at a few of the individuals that they had right around there, the individual samples were okay. They were down about 1 or 2, and then all of a sudden they get a 13. So it's really tough to look at that. There's a lot of things that are going on in the lake that make you believe that the phosphorus concentrations are dropping, which would be great. But I just don't think we have the data to say anything on it. So that's where when we look at this, now we've got some data that at least I trust a little bit more. I trust a lot of, hard to say I trust it. I believe some of the early data, but then they mixed it in with some bad ones, so it's really tough. Now we've got the information here for 1 year, one solid year, and we want to do it the same way that we did it last year out in the middle so we can compare that and see, do we see that same seasonality from 1 year to the next, and have that to continue on forward. How do things change with depth? This is where I was thinking that maybe internal loading had a little bit more dramatic effect, and I'll talk about that in a little bit. Here's the surface. It does increase a little bit with depth. The black is the bottom, but we're only talking about going from about 5 to about 8 micrograms per liter. So it's still really low. So is the sediments in the down deeper in the lake giving off a little bit of phosphorus? Probably, but it's still real low. But we do see a little bit of stratification with respect to phosphorus. This is not from this lake. This is from one of my other lakes. And if you looked at this, I was thinking that we'd be hovering around, something low. And if you're looking at internal loading to go from, I know I'm mixing up units, but going from 0 to about 600 is this lake the other lake I was studying. So instead of going up to 8, this lake was going up to 600. And that's what you expect if you have a lot of internal loading going on. So going from 4 to 8 is not really saying much as going on in that, even though it's a big volume, but that's where you look at it and try to quantify it in terms of other things. So, all right. Then we weren't just looking at total phosphorus, we're looking at dissolved, just get an idea what's going on. It's about, here's the total on the top, the dissolved fraction on the bottom. Only once did it really go down to basically the detection limit. Other than that, there was dissolved phosphorus in the lake all the way through. Trish, here's one for you. You're asking about the nitrogen to phosphorus ratios. I just wanted to look at that really quickly, and I computed this last night. And it's about 100 to 1 by weight or 50 to 1 by molarity. So what it's saying is that phosphorus is really the one to be worried about in this lake. And when you look at that, on top of that, it has a lot of dissolved nitrogen and very little dissolved phosphorus. So if we're looking at what potentially driving the productivity in the lake, it's really a phosphorus-driven lake, which is pretty much what we thought. So that was the deep work. So we think we have that's the baseline. We think we have something now to start to compare with through time. We're talking about a couple years study. I'm really hoping that that'll go forever. That's, there's a little bit there, but I'd like to see that. I've got studies that are going 30, 40 years, and that's something that they look at every year to try to see how it's changed. And that would be a great to have that information. Okay. Now on the near shore, all I want to do is just put it side by side just to say we are sampling the near shore a lot more than anybody I know of. We're sampling 12 different sites. We look at that. We have 2 indicator sites. That's our site that we have. We did a lot of our sampling on the near shore to coincide with what Jan Stevenson is doing with the golden brown algae. So there's a site on the southern part of the lake. We call it N10. Sorry, I don't know the name for that one. And N3, this one you'll know. It's up by the yeah. Okay. So those are the 2 sites that we're sampling a little bit more in depth. We're not only, in 2023, we not only did nutrients, which we did at both locations, but we also did phytoplankton and zooplankton at those to try to compare what's in the near shore with what's in the offshore. And we did all the nutrients at those 2 sites. And then we have another 10 sites that we're just looking at phosphorus and chlorophyll. Come on. How close can you come? All right. So here's all those sites I was talking about, and they are spread around. We got a good distribution of those. These are all coinciding with sites that Jan Stevenson had. And so what we want to do is to look at sites that he's doing fairly detailed studies or has done detailed studies, can sort of give us an estimate of how much golden brown algae is out there, so we can try to see what the surface water is right above the benthic algae. And so when I was talking about the 2 sites that we're looking at in more detail are N3 and N10. Okay, those are our sites that we're doing a little bit more extensively, looking at the phytoplankton, the zooplankton, and some of the nutrients. Just really quickly, do we see any differences? So we're doing things like temperature, specific conductance, DO, pH. In general, it looks like it's colder to the north, but I think that's just because we get up there sooner. Usually we get out there, do this circle around the lake, and a lot of temperature is just, I think, at the time of the day. We're up there earlier in the morning, we get down here a little bit later, and so that's probably what the temperature signal is. Do we see much of the other ones? Nothing really to talk about. Phosphorus concentrations. This is where it gets into the possibility of being some areas of the lake having a little bit more productivity than others. And so we measured total phosphorus, and then this is summer phosphorus. We look at that. This is I lost part of my slide there. This is the average difference. So how different is it on average? So N3 actually is 2 micrograms per liter on average higher than the average. Okay. So the reds are the higher, the blues are the lower. So when you look at that, N3 is potentially the most eutrophic part of the lake, right here. But then you turn around and N4 is the least. Is this noise? Well, we're going to do another year to try to find out, do these patterns stay this way? But at least here, when we're looking at it, we only start off with a mean for all the sites of 2 micrograms per liter, and this one's 2 higher than the mean. So it's double. It has a concentration twice that of any place else. So in general, N3 and N10 were the highest ones, happen to be our most intensive ones, and the lowest ones are N1 and N4. So a little bit of variability going on. And then for chlorophyll, this is where the phosphorus should be drying in the chlorophyll. We look at that, and now 2 If we look at that, 2, 8, and 12 are a little bit higher. One's a little bit lower. I don't know. There's a little bit, and if considering the mean is 0.2 micrograms per liter, it's very little difference in chlorophyll in the water column. Yeah.
Yeah, you talk about your average differences. Have you done any looking? Are they statistically significant? I'm not familiar with the study, but that's sometimes when you
Yeah.
look at see if it's statistically significant.
Yeah, it'd be nice to do it with a total number of 6 right now. We only have 6 to compare. I would doubt anything is statistically significant. If we go back to, I was more looking, didn't want to get into statistical significance yet, just trying to see if the percent, if it was something that, like if they were consistently 0.0003 difference, it could come out significant, but who cares? And that's what I was sort of looking at here, is that I don't know if I think this will be different just because I looked at the numbers and it's consistently a little bit higher in all 6 months. But this one, you're basically doubling the concentration. So this one, on average, it's 2, and that one has a concentration of 4. And other than that, I was going to try to talk Trish into stopping this. But then I looked at this, there's a few things that we do start to see patterns. And when we start to see the patterns, I thought, well, let's try to keep this going one more year and try to see if what we're seeing, these same patterns appear next year. See if that number 3 comes back and just as the site has a little worse water quality. But yes, I would like to try to. Right. Yeah. I guess that's not good in a lot of ways because the whole idea, I didn't say, but these colors on the front of it, this is the golden brown algae concentration. So blue is low, red is high, orange is are in the middle. So the whole idea was that we were trying to hit the highs and the lows. And so I really expected to see if there was going to be a pattern that 3 and 10 would be just the opposite. Just because if the golden brown algae was high at one and low at the other, I was sort of expecting if we were going to see any pattern, it would be 3 and 10 would be the most different, and we're not seeing that right now. But yeah, those are about 1 meter down in about 10 feet of water. The one thing I'll talk about that in a little bit, but those are in about 10 feet of water, so they're real close to shore. Yeah. Yeah, let me go a little bit further, and then we'll see what we have after we're done with me and Sherry, and then after that we can answer questions. Oh.
So when we get to the questions, I'll hand the microphone around to people's questions so people can hear it.
Okay. I'm not going to go that much further anyhow. Okay, so yep, I talked about that one. All right, so stream sampling. This is where it gets a little bit more. We really put a lot of effort into this. We're not just going out there measuring it 5 times during the year and get an idea. So we started off at Clam. We started off at Clam and Torch. And this is what our site looks like, Clam, right now. It doesn't look like too much. Mostly all you see is our solar panels, which is good. But we have an acoustic velocity meter under here, which is shooting a beam across the water, trying to tell us how fast that water is moving. And then we have a water level gauge to tell us how much it's going through. So with the combination of those, we get some of the graphs that Tom showed. And you can see what we're doing is we're measuring the height of the water that's coming through, which is only used to tell us, we can take that, multiply it by the velocity to get the total volume and the time series going through. If we put that all together and just do a daily average, it looks a little bit nicer. Then we don't get a lot of the little fluctuations that are going on. What we see is in the Clam River is up around 500, dropped to about 200, and then sort of. So that was the pattern we saw. Now, if we remember the studies that were done before, almost everything was done right in here, right in this time period where it was some of the lowest flows. But this one gives it so we can go through from basically 365 days a year all the way through. We can get a good estimate of going on. And if we look at that, our average flow is about 345, which is quite a bit more. Even though it was a dry year last year, it was quite a bit more than it was done in 2004 and 5. And during the summer time period, we dropped down to about 264. okay, compared to they had 188, but all right. Just a quick showing you these, we only collected the plan was to collect about 18 samples throughout the year. These are our concentrations we measured. And if you look at that, here's how much it varies over here. It's going from 1 microgram per liter up to 8. These are extremely low concentrations for inflow, averaging about 4 micrograms per liter. There was some talk about some sewage treatment plants possibly dumping things late in the summer, and I'll have to talk about a little bit more. But the highest concentrations we've seen were in basically September and October, but fairly steady. Okay. Now the thing that's nice about this is that we can take that, sort of interpolate between the dots. Normally you don't do that for a small stream, but if you look at that, connecting the dots is not a bad idea here, and we can get that. We can play fancier statistics with that once we get more data, but right now I just connected the dots, and it came up with a total phosphorus loading of about 1,260 kilograms per year. During their study, back then, not that much different. So what it really came down to is that they had higher concentrations and lower flows, but came out to the same answer. But I think we're gonna we'll hopefully keep this thing going. This is the bulk of what's coming in through tributaries, and we can keep keep this site running. Okay, so that's the inlet. Here's our outlet gauge. This is Torch River. Same thing going on here. The thing that's interesting is that every so often, I think the water reverses for one period. I think we're picking up a boat going through. So we'll subtract those off. But it's sort of interesting. So we're measuring that. Just sort of what our boxes look like. And we're getting the same kind of information. So we're getting a constant height, velocity, or that's actually discharge. And so we can come up with what is our flow leaving the lake constantly through time. It looks pretty similar to what's coming into the lake. Average flow velocity of 357. If you remember, that's almost the same thing that's coming in. So it's almost a flow through system. What's coming in Clam is about what's equivalent to what's leaving. Here's when we sampled it. What we're trying to do is sample that monthly plus during storm events. And here are the concentrations that we're measuring. Again, not too surprising because it's leaving Torch, so it should be pretty close to what we're measuring out in the middle. Concentrations between 2 and 8 micrograms per liter. And so with that, we can turn around and look at that and not only compute the load coming in, which is about 1263, with what's leaving with 1629. So actually, there's a little bit more phosphorus leaving than what's coming in Clam, but that doesn't include Spencer and Wilkinson and atmospheric deposition and groundwater. So once we put all that together, and if people remember the other study, they're saying that there's a fairly large amount being deposited in the bottom of the lake, and that's where a lot of it is. It's that difference. So what comes in Clam is almost equivalent to what's leaving Torch. If we look at that in terms of precipitation, I just want to show this to say, okay, there wasn't that much going on last year, but here's a storm event, and yes, we sampled right after it. Here's a storm event, and we took a sample right after it and a little bit after that. And in general, during the storm events, what's going in Clam didn't have to do with, I show this on flow, but I can also show it with the rain events. We didn't see much of a relationship with concentrations. One of the things that we want to do is to look at how our sampling year compares in the long run. And so this is precipitation through the entire time period. If we look at when the study was done, that other study was done in 2005, it was a moderate, maybe a little bit below average year. And with where we are now, it's pretty comparable, which is good, I guess. But at least we can put anything we do now into context with what was done back then. This one is for you, Trish. So there's been a discussion, oh no, it was one of you two. Anyhow, we're talking about is there really any global warming going on? And if we look at the annual temperature nearby here, this is just, I think this is actually Traverse City. But when we look at that, here's the change. It's increased by about 2 degrees for the year. And we see about almost the same change in summer temperatures, which is a little bit different. I'm used to summer temperatures having very little change. Over in Wisconsin, usually during the summer, it stays almost pretty constant throughout the summer. Humidity's gone up, but the temperature stayed the same. Here we see an increase in temperatures during the summertime, which is saying that the water temperatures are probably a little bit warmer. and that stratification might be lasting a little bit longer. So both of those things probably are going on here. But we have to look at the months individually, and it'll be nice to see if the stratification period is actually lasting longer. Okay. Where did they sample back in 2005? Well, they hit a pretty warm year. So even though with a little bit of warming that's going on, it'll probably be pretty similar to what we have during our study. Okay. So that was the open water sites. What are we going to do in 24? Well, we're adding a lot of stuff to the program. So to try to keep the money at the same thing, we're trying to drop a few things. What we're going to do is we're only going to do plankton at the south site. I'm hoping that Trish doesn't show big changes from north to south. But the plan is that we're going to, right now we're planning to stop doing all the plankton studies on the north side of the lake. In terms of that station going on, there is now, out in the middle of the lake, there's a buoy. So don't anybody run into it. It says, if you get up close to it, it says stay clear. That doesn't mean that you're supposed to go fishing by it. For the people in this room, yes, there's this buoy here. There's another one right over here underwater. And underneath there, what we have is all of this. So we have our thermistors down. They're trying to tell us the temperature. So it's only about 30 feet away from it. But below that, what we have is a bunch of these little tidbits. Those are things that measure temperatures. Right now, they're measuring it every 10 minutes. We're going to try to run those for a couple of years. We'll pull them up, download all the data, and drop it right back down. So the buoy plans to be out there as long as we can keep it going. We'll probably take it out for the winter, but we'll put a little buoy down there at that point, and then put it back out next spring. What are we going to do on the near shore? Pretty much almost the same thing, except that what we're not going to do is we're not going to do any zooplankton. So again, right now the main thing is that we're looking at is the golden brown algae, phytoplankton, and we want to compare the water with the bent bottom. So we're going to continue to collect the phytoplankton part of it. This is one of the most expensive things that we're doing right now, and so we're going to cut the zooplankton out of the near shore. How about stream sampling? Well, we had the main flow, which was nice. We had about 85%, if the studies were right, of the inflow coming in. Now we just started Spencer. So we have Spencer going, which is, it's a decent sized watershed. I didn't try to show the size of the watersheds based on this, but if you look at it, it's a pretty decent sized watershed compared to any other individual river on here. And at there, so if you go over into Alden, over by the totem pole, if you look close, there's a little staff gauge there. But that's really not, the staff gauge is for our own interest. Well, all of it's our interest, but that's not what we're really recording. We also have a gauge over here. So it goes down, pops up over here. That tells us the water elevation continuously, which we're going to use that to get continuous stream flow. We have an ISCO sampler over here. And the idea there is that we're going to pump, it pumps water, oops. It pumps water from the river up through here, fills up a series of 24 bottles. And then ultimately it'll look something like this. We have 24 bottles. Here's our hydrograph. So we're not collecting it based on time. We have a program in there that says when the water level goes up a little bit, take a sample. Take a sample when every time it goes up it's a certain amount. And then as it starts reclining, we take a bunch more. And now that would get pretty expensive if we wanted to send all those in. So usually what we do is we look at that, we set it down next to this and say, okay, let's sample, let's send this one in for analysis, this one, and this one. And so it's really trying to figure out how are the concentrations varying through time so that we can get a good load. If we had an unlimited budget, we'd sample all those. But we're just trying to save a little bit of money. And it's primarily for phosphorus, since everything is saying this is phosphorus driven. But the plan is right now is to take about 80 samples a year for phosphorus and sediment, and maybe about 12 to 18 samples for nitrogen. So that's the plan for Spencer. Okay. So that's so now once we have that, we got the main inflow, the largest secondary inflow. Then what we want to do is to start sampling these other four. You're right, Tom, I don't have that one, do I? Okay, we're gonna have 4 sites. There's actually 2 up here. One over here. Where's that third one? Is that the third one? No.
Augamine's on the west side of the lake.
Yeah, that's over here. So we have 4 sites, 1, 2, 3. Anyhow, there's going to be 4 sites out there.
Eastport,
Yeah,
Wilkerson,
yeah.
and Ogilvy. Spencer's actually the fourth one.
Oh, okay. So we're only going to add 3. Okay, that's my problem. All right, but anyhow, the idea there is to try to go out there and get an idea of how close to Spencer are these. So we're not going to get a real good load estimate. We know they're a very small fraction, but we want to get an idea of what is the concentration. We can use Spencer as an indicator of whether streams in the area are going up or down. And in fact, we're going to try to get an estimate of stream flow at each one of these kind of things. When the USGS goes out, we're going to do a stream flow measurement. We'll actually do it by hand. When the volunteers go out, they're just going to measure how deep the water is. We'll get a really quick rating curve out of it, just to get an estimate how these other ones are. And if we come out, when we're all done, and show that Eastport or something has got a load that's higher than Spencer, maybe we can talk about trying to put enough money in to put a gauge up there or something. But right now, we think it's going to be small, and this is going to be our way to just get an idea of what kind of estimated loads that we have. Atmospheric deposition. It's very simple. Just basically a mixing bowl that we're going to put out there, measuring not how much water is coming in, but what the concentration of phosphorus is in the rainfall. And then we're going to set it out there during dry periods and figure out what kind of dust is falling down. And then we're going to try to put those two together to get an estimate of what's coming in atmospheric deposition. Right now, we're going to set this up next week over way over in Grayling, get this procedure down, and then we're trying to find a place over here. Someplace out underneath a bunch of pine trees. Okay. All right. So with that, I'm going to pass it off because the next step is sort of, we know that groundwater is sort of that third step, another potential big source of nutrients. And so Sherry's going to talk about what our plans are for groundwater. I'll be back. And then you can ask all of them.
Okay, so I've got to find your presentation.
But yes, what was your question?
You're ready. So he's got the remote if you want to change slides with the remote. So you want me to introduce Sherry or are you going to introduce her?
All right, now we're going to move on to the groundwater part of this. Sherry Martin is going to.
Is that on? Okay.
Here, give me the button. I'll show you the button.
Like I was saying, this is sort of a stool with 3 legs in terms of where those nutrients are coming from. We really want to get an estimate of how much is coming in from groundwater. There has been some groundwater studies in the past. Luckily, we were able to get somebody who's been involved with those. That's Sherry Martin. So she has worked on a model for the bigger area. So Sherry joined the survey about 1.5 years ago. And luckily enough, we got her interested in the study. So she's going to be looking at the groundwater coming into the lake and hopefully working very closely with all of us as we go forward. So with that, Sherry, you want to describe everything?
Thanks, Dale. So my presentation today is just focused around where, check, 1, 2. I've always wanted to do that. About using groundwater models to inform our groundwater sampling strategy. So I'm going to show you a whole bunch of really cool stuff, but I'm going to focus on using that to identify where we can locate some sites based on the groundwater input to Torch. There's a whole bunch of other stuff we can do with the groundwater models, and we can talk about that outside. Yes. Oh, gosh. Is this better? Oh, my gosh. All right. So the model that I'm using was a model that was put together by a PhD student at Michigan State that I worked very closely with, Travis Dahl. He's at the Corps of Engineers. He was at the Corps of Engineers at the time of working with him, but he didn't have the PhD. He wanted to get a PhD, so we worked with him on a bunch of different things in the Boardman-Charlevoix area as well as in the Jordan River. So he constructed this model, published it in 2019. The area that I'm showing here is 2 separate model domains. The north is the Boardman-Charlevoix, and the southern area is the Muskegon. So both of those areas have been published, and we can do various groundwater modeling type stuff with it. Different kinds of things that you can use groundwater models for is to examine changes in climate, like Dale was showing with changes in precip, changes in temperature, anything that changes with land use. So an example is in the Jordan River watershed, we logged it, cut all the trees down in the model, of course. We logged it and we burned it and we changed things like that. So those are the kinds of things you can do in a model that you can't do in real life. So it's pretty cool that way. You can model effects on lake levels. So the Great Lakes levels are not stagnant. They go up, they go down. You can use that in groundwater models to see how that affects your system. One of the things that I was really interested in the Jordan in particular is changes in irrigated agriculture. So center pivots came into the right outside the surface watershed in the Jordan River, but within the groundwater area. And I was really interested to look at that. I haven't pursued that any further, but it was an interesting point to start with. So the basis for the Torch Lake specific model domain would be within this. So right now I'm just using this large regional area to inform where we might use or put some sites to look at groundwater more. But the future and in the near future, I'll be using the same model to look at groundwater flow rate and source areas, as well as estimating the groundwater input to Torch Lake. That's forthcoming. So in a regional model, there has to be a couple things that you maybe take as shortcuts, especially back when this model was constructed. Does this have a pointer on it? So this model was designed to capture the regional scale groundwater fluxes, not site-specific scale. So if you look at Torch Lake, it looks kind of jaggedy and strange, not like an actual lake. These are the NHD flow line, so it's a National Hydrography data set that was used to identify where all the surface expressions of water are present. So in this model off the shelf, the surface expressions, lakes, rivers, wetlands, were all just lines. So they were very simple lines, but for the purpose of this model, when this was constructed, it was sufficient. So that's something I'm going to show in a second here as well. Also, all of these cells, all of these blue cells throughout this area were defined in model terms as drain cells, which means that water can only flow out of them. So it can't go in and out. So that's a thing I think that we're interested in Torch is where is lake water leaving through the groundwater system, not just coming in. So this model, the way it's constructed as is, needs to be updated to be able to answer those kinds of questions. But to get rid of the jaggedy lakes, we did a short-term improvement where we actually made the polygons instead of lines for all of the lakes. It's a much more realistic to what we actually see up in the north area. You can see all of the wetlands as well as actually Torch as a represented polygon, not just a jaggedy line. This resulted in 2.5 more times drain cells in this model. So it's got a lot more rivers and lakes and wetlands in this improved regional model. But still they're defined as drains, which means that they can't have water flowing in and out. They can only have water flowing in the way the model is constructed. Yeah, there's no ability to predict discharge of lake water into the groundwater system currently. I think my next model. So this is when the fun stuff starts. So in this improved regional groundwater flow model, there are lots to see here. So I have this kind of input for this entire area. So we can look at all kinds of stuff, which is really exciting, but also a little bit mind-blowing when I'm just trying to look at groundwater flow in Torch and find some sites. So I really tried to constrain myself because otherwise I'll go down the rabbit hole. The brighter colors in this means there's more groundwater input. So you can see some bright yellows that are coming in. Those are high groundwater input cells. Some interesting things are that this North Basin has groundwater input throughout, as suggested by the model, which was surprising. And then I think a lot of times we identify the North Basin with kind of like a line, and that happened much further north, and as suggested by this model. And I'm using the soft language on purpose, so it's not like set in stone. These are just suggested by the model as is. In the South Basin, the internal basin, it doesn't have nearly as much groundwater input as suggested by this model, but you can also see all around the shoreline that there's these bright areas all around the shoreline, especially down in the south, which I have a bunch of slides focusing in on that. As well as there's just lots of variability in this whole Chain of Lakes area, and it's really cool, and many, many, many projects could come out of this. So sticking with our objective to guide these shoreline sampling spots, just kind of focusing in and looking at these different areas. In the North Basin, the north end, this eastern shoreline has a lot more input, these brighter colors over here, than on the western shoreline. This area at the northern part is pretty interesting, and that goes back to that, that the way these cells are specified in the model is they can't have water leaving. So I'm pretty interested to see what happens when we update the model and allow the lake water to go through there. If that turns into a real losing area of the lake, or if there's just a really strong connection, which I think we've talked about in casual conversation, that there is pretty strong connection, but we can't say that until we change the model up. Okay. Moving down a little bit into more like North Basin, below or right above where I had this change in major groundwater input. Some of the inputs on the western shoreline, but really there's a lot more higher, brighter values on this eastern shoreline with some hot spots. Again, there's one bright cell right here. We're not using this model to look at individual cells. This is just general characteristics. So even one of the things I thought about doing is just taking some like chunk, making a rectangle and taking averages to see where on average the groundwater input was higher, but this is way cooler to look at. So we can do that in the future if you want. Moving down into more of the southern basin, there's relatively modest groundwater input in this internal area, especially compared to the northern areas. There's some areas on the western shoreline that have higher inputs compared to the eastern shoreline, and you can clearly see inputs at Clam. It's the entire polygon of Clam has groundwater input throughout that. And then some pretty cool stuff happening up here, but that's outside of the current objective. In the South Basin, stuff gets pretty interesting in particular. like this, I would call this a hot spot over here of groundwater input. This lightens up, and it's pretty surprising. I guess I didn't really expect to see, I don't know, smaller areas with a lot of groundwater input. So that's pretty interesting. In general, I would say that there's a higher groundwater input on this west line, but really this bottom area with all of the yellow cells is where so much groundwater is coming in, which is also kind of surprising because I kind of thought it might go out. Yeah, yeah. So this all goes to help us do lots of things and come up with new projects, but specifically for now, it helps us guide our shoreline sampling strategy. Oh yeah, so in typical groundwater, if you just gave me the lake without anything going on, I'd just kind of space them out and, you know, move them around and do some in the North Basin, some in the South Basin, just kind of have a variability that looks pretty even like this map. But with some information like this, I would, you know, get these groundwater inputs down here. I'd get this hot spot here, this area maybe more than this area. Up in the north side, I'd heavily put them on the eastern shoreline and hit a couple spots over here to be representative. I'm interested in doing something up here, but not until we have more information. So it's pretty cool that these match up with some of the sites that you've seen the high GBA at. That's pretty awesome. So next steps would be to coordinate with the GN sites and convince Dale that we need to continue the shoreline sampling, because I want to get groundwater samples that are coupled with the near shore surface water. Yep, overlay GN sites, co-locate the sites with high groundwater input areas, add sites in other high groundwater flow areas if possible. Ask everybody if we can do this in their beaches. Install, hopefully, if things go the way I like them to, which might be optimistic, but install sites in late May. We'll have to talk to Jim about that. And I'd like to get out and sampling as soon as possible, because as y'all come, or as more people come back for the summertime, they'll be flushing the toilets more, doing more laundry, and increasing the load in through the groundwater system. And then also back in the office, I'll continue to improve the model for bidirectional flow. And I do have my computer here that we can sidebar and propose all the other extra stuff. That's all I had. Oh, yeah. I did bring what I have previously installed, but I don't know if I can hold the mic and do my presentation with this. Can you hold this? Thank you. So this is what the groundwater sampler looks like. It's slotted PVC with a point on it, and it's got just a tube stuck in it. So what I want to do is go out into about knee-deep water and sink this whole thing down into the bottom, about to here. So that would all go down. I know, I want to talk to you about that too. And then this would just be sticking out of the top, which I'll curl up and put underneath the paving stone, so that really there's a pretty minimal footprint once it's installed. The installation process might include some words, but the site is really robust to going back to the same place over and over and over. I've installed these in another lake, and they're still being used 10 years after installation. So that would be the groundwater sampling instrument, piezometer, which is funny. Yeah.
We got a microphone on that we can use for questions.
Let's finish up this last little piece, then
Okay,
we
is
can
that
ask
okay if
both
we
ways.
finish up and then we'll back to questions? Thank you.
Okay. Yeah, so that basically includes all of our monitoring that we have in 2024. This is going to be, we've argued about how we're going to put these piezometers in. I think Sherry convinced me that this is the way to go. So we're going to put those in. And where it comes down is that we've got these sites, and some of those look really, I was watching those, and hopefully these are going to coincide with some of those or come real close. If we can compare these with some of the ones that were done, hopefully those will coincide and they'll go. There'll be a few of these that, especially where Sherry showed some of those that had a real high area. I don't care if Jan's got a sampling site or not, we're going to put one in there. But so it'll be a few of these that might go rogue, but they're going to be for the model. And then what we can do is to look to see, do we see the same patterns? One is to look at the sort of the head inside those and try to see it as a head higher in those areas where she thinks there's going to be real large inputs. So we're going to look at those for not only how much water is coming in, but then we're going to be pumping those and taking water quality samples. We're not going to collect a lot of those. It shouldn't vary that much. So we're going to be doing water quality sampling probably on a quarterly basis for a little while, mostly again for phosphorus. We'll be doing dissolved phosphorus, but we will also be doing nitrogen. So that's the plan for the groundwater. So that's all of our monitoring for 2024. There's going to be, then it really starts to, after we have 2024, then we'll start to have 2 years of data. We'll have 2023 for Clam River, a few other things. We'll have 1 year data for some of the other stuff, which I hope we can continue on a little bit longer. And so we can start to compute loads. I showed you some of the loads that we already had for what's coming in the Clam River, but everything else we had that we were talking about, we want to compute loads for, because all of the models that you play with really want to have all that information. So we want to compute the loads. We want to start to compute budgets. We want to figure out how much is coming in from the atmosphere, how much is coming in from the groundwater, how much is coming in the tribs, and put it all together. And then in addition to groundwater models, the groundwater models is primarily just to get us how much nutrients is coming in. Groundwater models by themselves can be used for a lot of other things. I'm looking at sort of selfishly saying, what can I use them for in terms of water quality in the lake? But there's a lot of other uses. You start to look at this, and some people look at it in terms of how important it is for septic kind of things. If the groundwater is going the other direction, yes, it can contaminate the groundwater, but it may not be impacting the lake as much. Okay. Whoa. Oh, yep. Okay, so the kind of models that we talked about when we first started, are pretty basic. They range in sort of complexity. Some are very simple models that just say that the concentration in the lake is equal to the function of the loading coming in. That's why we need that total load coming in, and the morphometry of the lake and how fast the water is coming through. So once we have this information, we can run very simple models. And we've done this for a number of other lakes. That's actually what the USGS got involved with early on with this, is because of some of the reports that we had. We're looking at the load versus what we expect the water quality to be. Dan, we were talking about this the other day, where if you said, okay, if we're only worried about GBA, this isn't the model for you. But if we're looking at it saying, if the loads were to go up by 20%, what can we expect and how much the chlorophyll in the lake might change? These are good for those kind of examinations. So this is looking at trying to say, we really don't want that loading to go up, or this lake could really change. There's other kinds of models out there. One of the models is something like this, which is GLM. If we wanted to look at things in terms of, come on. Stop and lose it. Okay. Climate change and what we expect the stratification to change. Now we'll have all that information for that, where we can run some fairly simple models and say, how much longer is that stratification period going to last? We can go out there, simulate that. If that gets to be more than, that's more of interest, But if we start working with Jan and it's the growing season that's important for GBA, we can look at how climate change is affecting that growing season. It's really hard to get that by just collecting a few water temperatures, but by using a model like this, we can try to see how would the growing season change. How would this potentially affect something like zebra mussels or golden brown algae? Another model that was run in the past is Lake 2K. It was looked at as it was used very similar to what that empirical model was. Only this one's a little bit more in depth. It looks at seasonality, the changes that occur. But again, with a model like this, we can go through, simulate what the effects are of changes of the nutrient loading to it in terms of what kind of productivity we get in the lake. But it also simulates some of the processes that are going on. You get an idea of which of those are important. You can see when you look at something like with a GLM model, it has very complex in some ways. This way simplifies parts of it, but it still has a lot of complexity to it. But we can do it on a lot simpler information. Doesn't need quite as much kind of things. So then this is the big, Dan, you like this one. This is what could we possibly do? If we can put this all together, would be the ultimate, which is if we understand what's driving golden brown algae, we can put it into it. So I'm not saying we're doing this. I'm saying this is what the potential is to start off with a model like with GLM that's able to simulate the physics, get into a model that can simulate the processes that are involved, where you're driving it with nutrient loading, predicting the water chemistry, the plankton, everything in the lake. And I have been talking to one of the people who've done a lot of work with this, Matt Hipsey in Australia. And he's got a version of this that does have certain kinds of mussels and benthic algae in it to a very limited extent. And he thinks there's a possibility there. But even with that, we have to know a lot more about GBA before we can do that. But this would be sort of the hope that we would do, probably not as part of this first project, but would it lead all the information we have. When we first started this project, I was really hoping that we could have jumped right to a lot of this. But the more we looked at all the data that were available and how questionable they were, we had to get a lot more baseline. So the idea then was to put that in, the mussels, simulate GBA, and ultimately have that at the far end and be able to predict that. So that's sort of the hope in the long run, is to try to pull all of this together. So with that, now I'll finally open it up for questions. Anything that we've done up till now or plans for next year?
Yeah, thank you. This is a question for Sherry. I just want to make sure I understand the process for the groundwater testing. So you explained very, very well how you use the model to identify kind of areas of interest around the lake and where the model is showing, potential high levels of groundwater flow. And so when you put these piezometers in, just to make sure I understand this correctly, you are going to both verify that those are high level areas of groundwater flow in addition to sampling for nutrients. So you'll do both of those parts so that you'll not only validate the model in terms of predicting groundwater flow, but you'll also get nutrient data and input from groundwater into the lake. Is that correct?
That's the plan.
Okay. All right. Thank you. And then the rest of the questions, I'm just going to catch Dale separately because they involve the sites that he was seeing different levels of phosphorus, and I wanted to match that up with with Jan's work. So I'll talk to him separately.
Rick, you're talking about sites, and I think that's going to be really important. I don't think we can get quite the sites right now, but you sort of Sherry's first real quick cut at where we want them. What we really would like to do is, I don't know if we technically have to have permission to put something in the water itself, but we really like to work with people. We really like to have it so that they know that we're going to have a boat or something coming up, putting a little table in the water, because we want to measure the water level in the wells, trying to see if that's really a source of where the water is coming in, or it's leaving there, or if it's not doing much of anything. We also have to pump that water out, so we want to get the sample from there. So you don't want somebody pulling up a boat right next to your dock and saying what's going on. So what we really like to do is have permission to put these 12 around. I don't know if we wanted to go out in the sandbar on the 4th of July and try to sample next to them, but.
Not unless you want to spend the day.
Yeah, well, didn't say we wouldn't. Yeah. I can read, well. I'm still amazed to see 5,000 boats out there.
Hi, Sherry, this is Becky. Um, I didn't understand if you did or didn't say this, so I apologize if I'm repeating myself here. Uh, with your piezometers, what we've been able to do is like 2 feet max. And I wondered what depths you're planning to put your piezometers at.
So the slotted section is about just under 2 feet, and then the tubing is another 2. So I want the portion of groundwater that I'll be sampling to be at 2 feet below. So it's going to go deeper. And I know you guys had a challenge with getting that other piezometer in. I also had similar challenges at another lake that I worked at, and I got I first he watched me and had a good chuckle, but then he offered some pretty interesting help that has helped me. So we put in 20 something piezometers in another lake, and there were some challenges, there were some words, but we got them in. So it's probably not going to be as easy as cutting butter, but I think we'll succeed.
We've never gotten piezometers into the lake floor at like 15, 20, 25 feet water depth. And it occurs to me that groundwater may be flowing into the lake in the shallower and out of the lake in the deeper. Are we going to be looking at that at all?
That's not in the current plan, but the shelf, the groundwater dynamics in the shelf looks really cool, and I'd love to do more stuff there. But yeah, I gotta have boundaries for what's the objective of this project. So
Just to follow up on that, if you looked at some of the earlier studies that won in 2005, 6, what they did is they put together a full water budget, and they all the errors were put into the outflow. We're going to have really good outflow. We're going to have much better estimates of inflow. We can get an idea if we're missing a lot with groundwater. I'm really hoping by the approach we're taking that we can constrain those a lot to try to at least get a net groundwater a little bit better handled. So anyhow, I think we'll have a little bit better idea of trying to address yours a little bit better than what was done in the past. It's always tough for groundwater, especially when you're looking at something that's 300 feet deep and this close to Lake Michigan, trying to decide, could it be losing it? Typically, lakes don't lose groundwater in the really deepest spots. It's usually around the periphery. I know this is a little bit different, unusual lake, given how deep it is and especially how close it is to Lake Michigan. So, but Rick?
Any more
Oh.
questions?
Dale, this relates to the phosphorus testing and the detection limit. Obviously, now we're down to 0.5 parts per billion or micrograms per liter. As a living, I used to measure trace amounts of boron and phosphorus and silicon metal at trace parts per billion. I know how difficult it is to not get contamination and stuff. What is now the repeatability of that test at 0.5? I mean, if you submitted 5 samples from exactly the same section, would you get 0.5 plus or minus 0.1, 0.5? Any comments on that?
We should have. We haven't tried that yet. We did submit blanks, although we're not as sneaky as we probably should be. Jim's got to use better abbreviations. Can't quite BLK. That doesn't work. But the blank that we did send them did come out at less than detection, which made me feel good. But I agree with you. It would be nice to send in a couple 3s. That 1.7 still scares me. But it would be nice to send in a few more duplicates and try to see if we can get 2 to say 3. We have had I think we do have a couple duplicates, but they're not our duplicates. It's the lab's duplicate. They're doing it, analyzing it twice. Every so often I see a duplicate, so I know they're doing it. but I want to do it blind too. So the numbers that I have seen when they've done duplicates in the lab, they've hit right on, which makes me feel good. But I want to do it myself and just don't tell them that they're the duplicates. And I always like to keep them guessing. So, yeah.
So the atmospheric deposition is primarily, so you haven't set up atmospheric deposition yet for this round, right? So
Right.
all the information is coming from 5.6?
Yep.
And you had a number of areas where other information from that study, you weren't feeling confident about it. How confident are you with the atmospheric deposition?
Not at all.
part? Not at all.
Not at all. When I showed you those plots, they had concentrations up to 200. And I think what they did is when they computed their numbers, I don't know exactly, you read through, it's hard. I think they took the median values and used those. So if there's a few outliers, at least those will disappear. For the most part, they look pretty good. I just have a hard understanding why Bel Air would be 3 times higher than the other 2 sites. But we'll see. I think it'll be interesting to find out. Dry fall is always really difficult. Wet fall, you get out there and it's raining and it's coming down. Dry fall, if you're underneath a couple of pine trees, you get a lot of pollen, and that sort of exponentially decays out into the lake, and so you don't want to use that too much. So we're trying to talk somebody to getting up early and going out to the airport all the time. And, oh, didn't see you there.
It's on the way to the golf course.
Okay, all right. But anyhow, I don't think if we don't have to be right on top of the lake, because really what we want is a concentration in the wet fall and an estimated dry fall. So I don't think it has to be that local. A lot of the other studies that I've looked at is, you're pulling it from quite a distance. So I just would like to get some numbers.
All right. So
But we are repeating the whole thing.
got it. So as it stands, there's a lot of work that's being happening to verify both groundwater and the atmospheric, and
Yep.
and what you've collected so far couldn't give a good estimate of how that balances out yet.
Right, no.
Okay.
And then there's also where'd John go? It's in the back somewhere. Oh, there he is. There is other people collecting atmospheric deposition around here. For some reason, I've been pushing for years with the NADP program, trying to get them to add phosphorus to it. You'd think that since phosphorus is the #1 issue with lakes around, that a program like the National Atmospheric Deposition Program would collect phosphorus. They only use it for contamination. We do know they've got a lot of, how far is your sampling site from here, John? Okay, but up there we see some real rapid changes and some pretty dramatic changes in pH, and they are measuring some other stuff. Maybe if we do it here, I don't think you're collecting any phosphorus right now, but maybe if we start, can convince other people to do it too. And I know right now I've done some stuff for like the Great Lakes, and we've had to rely on people from Canada because Canadians are still doing it. There isn't many people in the U.S. So.
I don't see, but we had a discussion earlier, and you used the term standing wave when you were talking about vertical mixing. Could you clarify that for us in your presentation on the vertical mixing?
Okay,
You
I
said,
wouldn't call it a standing wave, but no, what happens is if you're looking at the seiches in a lake, when the wind blows across it, the whole silt, you look at it, and yes, if you're on Lake Michigan or something and the whole thing is blowing at you, it could raise a foot. Out here, you might be looking at maybe an inch. So if you get a real north wind, it might go up an inch. But as you go down deeper into the water, those kind of changes, and so instead of being like 1 inch on the surface, you can get the whole thermocline to hold up like this as the wind blows. And it might be a difference of 30 feet from one. One reason I do that is usually I'm talking to fishermen. But you can get a 10-meter tilt across the whole lake. And at that point, normally we're doing this for nutrients. It may not be as important right now because usually what happens is that the deeper water comes up and it'll come up and sort of gets squirted into the top almost when these things are moving around. And so usually you're looking at this to try to see if nutrients are getting transported up. That's why we're measuring nutrients throughout. And maybe when we're looking at a difference of 4 versus 7 or 8, that might be still something to consider. But that's what one of the purposes of those that thermistor string out there is, just to see how much of that is going on.
any more questions? We're actually pretty close to schedule. All right. So we are that close. Ladies, are we ready for we start the lunch? A reminder, make sure you fill out your survey, but we're going to take a break now for lunch, fill out the survey, and then we're going to get the next event, I think, is Dr. Stevenson's talk, and we'll get him ready just about 12 o'clock, 12:15. So let's try to wrap up lunch by 12 o'clock. everybody is pretty much settled down. As I said earlier, Dr. Stevenson unfortunately was not able to join us in person today, but we, in spite of some technical difficulties, have him online now on Zoom. So the way this is going to work is he's got control of his own presentation, his computer, and we'll be able to see him a little bit and hear him. Now, we'll have to make sure that we handle questions. And as you do have questions, we'll either try to pause him if it's a good time, or we'll hold him to the end of his presentation. But we will take care of all questions for Jan. So this is a little bit of his bio if you had not seen it. Dr. Stevenson has been involved in Torch Lake and specifically with Bethnic Algae for at least a decade. And he's done a great deal of work. We don't have enough time if we spent the entire day on what his work has been. But he's going to give us a nice little recap of recent work and how it ties into the overall project. It's been very helpful. What? Yeah, you can switch it. You don't have to. No, you can leave it because it's gonna go. Yeah, plug it in here. No, I got it. All right. Okay, Jan, can you hear me?
I can hear you. Can you hear me?
Well, we're gonna get as much volume as we can out of here. Never tried this before.
Touched.
Okay.
Okay. I might be able to now.
I think we can all see you and hear you now.
All right. How does that sound? I don't think you need to see me, but
All
if you
right.
can hear me, that's what's important.
Okay.
All right. So I'm going to talk about the ecology of the golden brown algae and what we've learned actually in the last year. Not so much about the past. That's been presented last year and is available in other things. And this is kind of an update of what we've learned with projects that we've done over the last couple of years, I guess. And so I'm now an emeritus professor at MSU. And the work that I'm doing has been supported by Three Lakes Association, and the university is supporting me, has supported me in the past quite a bit, but is now still supporting me with providing lab space and for this project and several projects that I have going in the Everglades and elsewhere. So that's very nice of them. And what I want to talk about today is basically just to give you a little info on what's going on and some very preliminary conclusions about what we've learned. We've had to change just as an update, a piece of info, we've had to change where we're doing our mat and water chemistry assays because the University of Michigan shut down their chemistry lab, their analytical lab. So we're going to go with GLEC for the water chemistry. And I'm going to send samples to Florida International University for the mat chemistries, where they can do really accurate and detailed chemistries of the algal mats, looking at phosphorus and carbon and nitrogen, and specifically give us a really direct measure of calcium in the mats, which is an important attribute of the mats. So again, I'm going to be talking about preliminary conclusions, and I'm going to actually tell you those in a few slides here so that as I go through results, you can actually see how that lines up or doesn't line up with those, the results of the experiments. I'm really hesitant to do this because there's so much more work yet to be done. I mean, we've got 50% more sampling to do and assays to do. So this is short of 50% of the information that we're going to get And so I don't want to bias anybody's, understanding of what we know about GBA and the ecology of the golden brown algae, the mats that we're talking about with the golden brown algae. And because we need to keep our minds open to all the new information that comes through and constantly testing hypotheses. So what I'm not going to have any algochemistry results today. I have a bunch of species composition results. So I'll present that. And I'm going to present that relative to the 2 experiments that we ran with the frames that leak nutrients and the bowls that need nutrients. So I kind of refer to those as the NDD frames and the NDS bowls, or short to frames and bowls. And then the 20 site survey and the 20 lake survey, which will be close to 20 sites and 20 lakes. And then finally, I'll talk about the plans for this summer. So again, we are remembering all of these hypotheses, not throwing anything out, and gathering information, and particularly pushing toward understanding the groundwater hypothesis and the idea that low phosphorus might actually be causing these mats, not high phosphorus. And our work links together with the USGS in this conceptual model that I've shown before, where USGS is primarily working on how natural and human factors affect water chemistry and potentially the introduction of herbivores and bioturbation, bioturbers, things that disturb the bottom, or invasive species. And then I'm really focusing my work on how those in-lake conditions would affect the bottom algae, and particularly the development of this golden brown algae. And we're at the point that we're really looking at the possibility there could be a decrease in phosphorus that's causing it rather than an increase. So our experiments were specifically designed, and our research is specifically designed right now. Our main focus is it an increase or a decrease that could be causing the GBA? So we're using these 4 different approaches to do that. We're integrating experiments and observations and a little mental modeling to these surveys, experiments, and modeling to basically understand what's regulating the development of this golden brown algae on the bottom of the lakes that wasn't there before, and at least not in great abundances. So we're using a frame experiment, and one of the places that we did this, I'm going to describe the results from today, was at Hayawenta north of the point at Hayawenta Camp. And the reason for doing that is there is very little GBA there. There are no thick mats that were developed. So if phosphorus was causing GBA mats, if we could drop a source of phosphorus down onto the sand like we did with these frames leak nutrients, these frames of PVC tubes leak nutrients, then if we leak phosphorus into there, we'd expect to see an increase in the attributes of the benthic algae that indicate the development of calcareous algomats. So the other experiment was to do something almost the opposite at the Petty property, where there are thick, and so this is on the east side of the lake, where there are pretty thick benthic algomats. And we don't think too much else is going on there, so it's a fairly straightforward location to look at. So if you have thick algomats, if you then add phosphorus, do you lose those attributes of the algomats? So they're complementary experiments. We have a 20 site survey in Torch Lake going on, where we're sampling around the lake, but near shore at 6 sites, and then more like 20 sites. We're working our way up to 20 sites. There are 18 sites that, there were 17 sites, and then Dale wanted a site by Wilkinson Creek. And based on some of the interesting groundwater results that Sherry had, it looks like there might be a couple other sites that we should pick up and add to that 20 site survey this summer. And then finally, the 20 lake survey, where we're looking across lakes, looking at many lakes across northern Michigan which are much larger phosphorus gradient, and trying to determine, so from less than 2 to almost 20, and asking the question, which of these lakes have GBA, and is that related to phosphorus or any other attribute that we know about those lakes? So that's the combination of projects that we're working on, and kind of how the pieces fit together to help us address what's causing GBA. And so the major conclusions that we've come up to, and again, you know, there's just so much more to learn. So I'm just trying to update you on what we've learned so far, right? That was what I was asked to do. That's what we kind of agreed to do last year. And so I'm just updating you on what I've learned so far. I'm sure you're curious about it. I'm curious about it. So it's kind of nice to stop everything and sit down and analyze the data and graph it out and think about it. So it's not going to, so these are the results. What's interesting is nitrogen has an effect on regulating species composition as well as phosphorus. Phosphorus effects seem to be much greater, but nitrogen is having a little bit of an effect. Species indicators of the golden brown algae. So if we look at characteristic species of these mats, they were reduced in the phosphorus treatments in the frame and the bowl experiments. And so phosphorus addition had a negative effect on the species that we consider characteristic of GBA, on their relative abundances. In the 20 lake survey, it was the low phosphorus lakes that had thick calcareous mats of algae, and that decreased with increasing, either the mats weren't as great or they weren't calcareous, they were just kind of muddy mats, and species composition changed with that. The biomass of the GBA mats and lakes also decreased with total phosphorus in that 20 lake survey. So the survey and experiment results are really consistent with the idea that low phosphorus is causing these thick GBA mats. So I'm going to walk through the results here, and you can think about what I've interpreted the early conclusions to be. So first, we'll start off with the frame experiments, and basically these are frames of PVC pipe that leak nutrients, so enrich the nutrients within that square and a little bit outside that square too. So we sampled inside and right outside that square using a Petri dish. So we got the top 1 centimeter core of all the algae in the sand. And what's great about this approach, which really hasn't been used before, we dreamed it up here for this system, is that you can manipulate the environment without disturbing the assemblages that are already there. So it's not, you know, that has an advantage. Of course, the disadvantage is you need a really big change in 30 days to basically affect what's happening there, because you're already starting out with a lot of algae. And so you cause a change over a 30-day period, which is how long we had them down there. Then you hope that you'll be able to actually detect it. And we were able to detect it. Not a great change. I'll show you it's actually much bigger in the bowls, which are contained, than in the frames. But it was nevertheless a substantial effect. And we expect to see basically an increase in the GBA species with phosphorus or nitrogen enrichment. So we had several control frames, phosphorus enriched frames, nitrogen enriched frames, and then nitrogen and phosphorus enriched frames. So I'm going to present the results of the species composition information in actually 3 of the projects. I'm not going to talk about the 20 site survey within Torch Lake because that's really preliminary, just to save time and target these results, which are clearer and more complete. So I'm going to present maps of sites in species space. So just think of a map with north and south, and we're going to replace those axes, those latitude and longitude axes, with species relative abundances. And then we're going to map sites out in there. And that'll show how how samples are similar or different. And then I'm going to select a simpler analysis based on a subset of those species. And I'm going to select some of the GBA species that we've seen in GBA in the past. So kind of a preliminary, a priori kind of, these are the species we expect to see in the algae, in these thick mats of algae. Where do we see them? Or how did the experiments and the surveys affect? So you're going to see kind of two pieces of information. What's called ordination of samples in species space, and actual just box plots of relative abundances of diatom species, that GBA characteristic diatom species. So this is an example of the ordination for the nutrient diffusing substrate, the frame experiment. And these were sample numbers 29 through 52 in the samples that I assayed. So those samples are shown here along two axes. And there's an ordination technique called non-metric multidimensional scaling. That's not particularly relevant here, but this is an example of ordination. The samples are spread out in species space. And you can think of it as just replacing, as I mentioned, latitude and longitude with, in the simplest way, the relative abundance of species A and the relative abundance of species X on those two sites, on those two axes, and then mapping the sites in that space of the relative abundance of species X and the relative abundance of species A. It gets more detailed because it's actually tens and tens and maybe, or actually hundreds of species on each of those axes, and they're positively and negatively related. But the point is that ordination places samples in a space, in a species space, and samples that are located close to one another are really very similar in species composition. They've got the same identified species and their relative abundances. Where samples far apart in these maps are very different, or the most different among the samples that were collected. So here's an example from, these are the results from the diatom samples that I counted for the frame experiment. And basically these are spider diagrams. So the sites are now connected and showing relationships among these sites and environmental characteristics by these spider diagrams, where the sites are connected by the red lines around a node for the treatment. And the treatments are, HC is the control for Hayawenta. HN to the left of that is the nitrogen treatment. Those are the samples for the nitrogen treatment. And for the two treatments, phosphorus and MP, those are to the right of the control. So this figure shows us that the samples associated with these different treatments are located in different locations in the species space, and therefore have some differences in species composition. And there are next steps in this kind of analysis where I can associate exactly which species are associated with these treatments in detail, these axes and these treatments in detail. But I haven't used that technique. Yeah, we'll go to a different one. But so that's what this tells us, that there are differences among the treatments. And then we can put ellipses around them, and they kind of show how the treatment effects overlap, and they provide basically an idea of the range. There's a lot of variability. There are some, there's a sample, way over here, and 42 is way to the left of 41, 43, and 40. There's a lot of variability among these samples, but despite the variability, there are distinct differences. The differences here are unlikely to have occurred by chance, by just random data. So, in looking at it a little bit more detail, the nitrogen and phosphorus, I'm sorry. Yeah, the NP treatment, nitrogen phosphorus treatment, and the phosphorus treatment overlap. They have pretty similar species compositions, and they are really the most different from the control. The nitrogen treatment, it's interesting that it's in the other direction from the phosphorus and the NP treatments relative to the control. And it is also distinctly different from the control in this ordination in this species study. So the treatments affected species composition based on the ordination graphs. Now I'm going to talk a little bit more about species composition and how we measure it, and not just in ordination, but all kinds of ways, and why we do that. So we can measure species composition just as a list of species that we observe in the samples. But then we can also look at, because we count them, I count them, traditionally we count them, we count how many individuals of each species are there. So we can look at their relative abundances. That's number 2, that should be relative abundances. Versus number 3, which is absolute abundances. How many cells are there per centimeter squared? I actually plan to do the third step as well. I have not gotten that's a different set of counts that I have to do. So I have not gotten that information, but I have the species list number 1, and I have the relative abundances number 2. And the table down below shows you basically examples of how this occurs, that, you figure out 50% of the individuals we see in sample A are species A, 25% are species B, and we didn't see any of species C. There are a bunch of others that were there. And so that sums up to 100% with relative abundances of species A, 50, B, 25, and 0 for species C. And so this is relative to other organisms without actually knowing the numbers that are present. That's the next step. So that these results are based on relative abundances. And so the interpretation is a little more complicated. So why do we look at this? So now you get the question, that's not a very big difference, or that's, so how is this related to actually seeing GBA? Well, basically, so I have actually done this for 50 years, and I started this because I was sitting in Rex Lyle's algae class as a senior, and I was going to go work with fish and in environmental work. And I was sitting in his class, and I saw that how many more species of algae there were and how sensitive they were to environmental conditions. So I was thinking, this is going to be a lot more informative information than fish with only, 10 or 20 species in a habitat. So that's why I got into this. And it's really to look at the species that are there and determine whether they should be or they should not be there based on what we know about the natural conditions in that habitat. And then to infer based on the shifts in species composition, which ones are shifting? Are they high phosphorus species or low phosphorus species? Are they high nitrogen species or low nitrogen species? Infer the differences in conditions that based on the diatom species composition, and then relate that to things that we're interested in. For example, the GBA MAP biomass. In work that I've done, where it's really difficult to characterize chemical environments, the diatom species provide really robust indicators of those chemical environments. So, and in the study design that we've got the experiments. I'm actually going to go back and recount the experiments based on what I see in the surveys to learn more about some of the rare species, so I can learn what these species are telling us about changes in environmental conditions. That's why understanding the species are important. Maybe the species have something to do with the actual cause, directly cause the GBA. But more, I'm using them to infer changes in environmental conditions. There was a question or a cough? Okay, I'll assume it's a cough. I'll assume you guys are still there.
Yes, yeah, Jim, we're all here. You can hear a pin drop in this room. Everybody's listening.
All right, so these are the species. This is the simpler version of the species composition analysis, where I'm just going to pick some species that are pretty robustly related to the GBA and the thick mats that develop over the summer. And this is data from several summers ago to show you the 3 species that I picked out. Nitsia denticula, so Cimbella delicatula became Delicata delicatula, and now is Lacophycus delicatula. Thanks to people like Pat Kaselik, who changes names on genera, which is an inside joke among some of us who actually know Pat and love him. And Cyneema evergladianum, which is actually named, again, just to repeat the obvious, it's named after being in the Everglades. It is one of the most common diatom species in the calcareous algal mats of the Everglades, and it's most abundant relative to all other taxa in the lowest phosphorus concentration. So that was the first kind of kicker with thinking about, man, this is a lot like the Everglades, and we're looking at these samples. Okay, and here's the effect. Much simpler version of looking at but less complete, because I don't have all the species in it. I'm just picking out the GBA species of the effects of the frame treatments on the relative abundance of these GBA species. So in the control, we were between 16 and 20% for the sum of these 3 species. In the nitrogen, it was actually higher. They were up about 20% usually. When we added phosphorus, or added both nitrogen and phosphorus, really no difference between the effects of them. The relative abundances were lower. They were more around 14, typically less than 16. And again, these are differences that would not likely occur by chance. It's close, but that's kind of based on the low sample size and the high variability we have. But I put a lot of credibility into, phosphorus and nitrogen are definitely higher than the other 2. And there's other evidence that indicates these kinds of things too. The nitrogen is actually higher here. So the question that should come up in your minds is, so is nitrogen stimulating the growth of these species? Or is nitrogen, so that would be a direct effect, or is nitrogen indirectly affecting these species by stimulating the growth of other species that lower the phosphorus and increase the relative abundance of these? So there's a little more evidence of that, but actually looking at actual species densities will help me resolve that when I get that information. But this is obviously pretty interesting. Okay, the bowl experiment. The bowl experiment, we basically manipulated nutrients in the bottom of a bowl. And I went out with Fred and Art and Becky and Susan, and I sampled algae off the bottom, mixed it all up. So now I'm mixing the algae all up. So I'm taking algae off the bottom at the Petty property where we have a lot of the GBA species, and we've got a GBA environment, and I'm going to put them into these bowls, and I'm going to manipulate just carbon and just phosphorus, and the C is a control. And so control and phosphorus treatments here. And the idea is that the phosphorus should decrease the relative abundance of the GBA species if it's having a negative effect. The advantages of this approach are you can really quantify effects, and it should be really sensitive. And the disadvantage is we're just breaking everything up and we're putting it into a bowl, and we hope the bowl is a realistic enough environment that we get responses that are faithful to the more open and natural environment. And so what we predict is basically with phosphorus addition, we're going to see a decrease in the GBA species at a site where there are a lot of GBA species and GBA and other GBA attributes. So just briefly, the phosphorus enrichment and so focusing on this one, the results first, the statement of the results first, and then the graphs, the data to show you. The phosphorus enrichment had greater effects on species composition in this study than at Hayawenta. And the phosphorus enrichment decreased the GBA species here. And again, I can't quantify them. Not again, I haven't told you this yet, told other people, but not this audience. That when we set these up, some of the stands spilled out. And I knew we wouldn't be able to do quantitative work, but I didn't want to start the, take everything out and start the experiment all over. Because I knew we'd learn something, but it'd be impractical to start it all over. So we're going to redo this bowl experiment with additions to it because I liked the way that it worked. So starting again first with the ordinations, and here I've actually included the frame experiment samples in this species space. So the frame experiment samples are all located over here to the northwest. And then in the south central zone, that's the bowl control. And then way over here in the northeast is the bowl phosphorus. So the distance between these two treatments is much greater than any of the distances between treatments in the frame experiment. The bowls had much bigger effects. And go on to the next slide. Here are the box plots of the GBA species specifically. Over on the left, I've kept the frame treatment effects so that you can remember what they are in their location and compare them to the bowl effects. The bowl control had relative abundances of the GBA taxa above 25%. And they were only present in the phosphorus enrichment done at 10%. And there are nuances to this. So for example, I'm looking at all diatoms in the sample, whether they're alive or dead. That's the assay that I've had so far. It will not be the final assay. I'll gather more information, determine which ones are alive and dead. But because diatoms have glass cell walls, those cell walls persist, whether they were alive or dead in the sample. So this 10% could be stuff that was just left over and then either died or persisted, but did not reproduce much. This is kind of like the background of what you'd expect from actually taking samples from a site that already have these taxa in it. So this is a big difference. This is a very big difference. So that's the bowl experiment. Again, indicating that phosphorus enrichment is having a negative effect on the relative abundances of the species that we find in the thick GBA max. So the 20-site survey, the goal of that is to look around the lake and look at the spatial variability in GBA around the lake and relate that to in-lake environmental conditions. So I sampled in July and September last year at 6 sites offshore, and the Birch Lake Association volunteers, Rick and Becky and a number of other people were out, and they sampled in the nearshore zone within a day or so when I was out sampling offshore. And I'm not going to present those results because they're just not complete enough to spend the time on right now. What I'd like to spend a little more time on is the 20 Lake Survey. And the idea with this is to look along a variety of northern Michigan lakes, some of which we knew had GBA in it, which suggests that we should do this over a larger region and we might learn something, and some that we've heard that there isn't any GBA in it. So, and this is a set of lakes that has a 20 microgram per liter gradient in phosphorus in it, or close to that. And we've sampled, I've sampled half of those. And I'll present the results of, I think, in detail of 8 and 10 or so that I've got observations of GBA map biomes. So just to remind you, what I do is I've got this sled that I've made out of a sheet of the stuff that I had in the garage, a sheet of tin metal, sheet metal that Rick has made a much nicer one that I have to put together for this summer, where it's got folded edges. It's going to be really advanced. And so it's not as likely to cut me while I pull it out of the water. And then there's just a quart plastic container, which surprisingly has lasted for years in this, that's held in place in this sled. And I pulled the sled across the bottom. The container is about 1 centimeter below the sled. And so it scoops the top centimeter of sand or sand and algae on the bottom of the lake. And then I sample that. I use a spoon to pull mats out. I put a nice, any sample of mat that I can get into a petri dish with no water so that it doesn't disturb it, but the mat stays moist until I take it back and I freeze it. And then I mix up the rest of the stuff that I get in what I call a gray sample, and put that into a Whirlpack bag and preserve it with formaldehyde and a special mixture of preservatives. So this is, in action with the spoon. Here's an example of a mat that's been buried in this goo or not, but the mats typically have enough cohesion that I can get them out of there. And then I lay that in the petri dish, and then I mix it all up and take 3 spoonfuls and put it into the Whirlpack bag as the second, the gray matter sample versus the mat sample. And here's just a couple of examples of 2 samples from the same location, just to indicate that there's a lot of spatial variability in this. The species composition doesn't vary quite as much, but spatial variability in how much algae there is. This was 2 sites at Sand Point. So I've looked at a lot of algae at the bottom of this. These are all samples taken at the deeper area. And down in the lower left-hand corner are GoPro images of a low biomass site on the left, and then a high biomass site where you can actually see the mat rolling up and then folding into the plastic. That's from Lake Charlevoix on the right. The Garley site has mats that are this thick that just roll up and then roll into the plastic container. I also see the mats and the thickness of the mats when I'm subsampling, and then back in the lab as I was sampling these things taking these really valuable samples and starting to cut them up and hoping all the methods would work. I see them again sitting in the petri dishes. So I've got 3 times I actually look at the biomass and have a good sense of what was in the different lakes. And when I look across the lakes along a phosphorus gradient characterized a couple different ways, the biomass of these mats decreases and shifts in whether or not it's got calcium in it along this gradient. So algae typically are on the bottoms of lakes. You're just surprised that there's not algae on the bottom of the lake. But the idea of having these thick calcareous mats, that's different. That's different. And the 2 sites that I sampled, both sites everywhere and they're all sampled at the same season, different years. Charlevoix just had these thick mats, no matter where you sampled. So the variability was really small, even though I just hit a few sites. But I looked down a lot, and you can tell a lot by just looking down from the boat. Torch and elk, we know Torch has got a lot of variability in it. So, but Torch and elk looked a lot alike, and some sites had some, but then there were some really good mats at other locations. But then there were places like Harriet Went to North that don't have mats until this year in September when I saw mats there. But that's not included in this. That's an anecdotal observation that is mentally significant in thinking about things. So Torch generally is a little less than Charlevoix, but Torch and elk are pretty high, and their phosphorus concentrations are around 4s. If we bump up a little bit to Traverse and Bel Air, Little Traverse and Bel Air, there are nice mats in Little Traverse, but they were not everywhere. And the same thing in Bel Air. There are some nice mats in Bel Air, but not everywhere. So there's variability, but they tend to be lower in biomass. So you could bump this up a little bit higher, but we're tweaking things. Burt is lower. The biomass in the mats was lower. There was some calcareous nature to the mats in Burt, but generally the biomass that I could see with the GoPro videos and the mats that I got are less. Mullet had, it looks like a lot of algae in the mats, but they were not calcareous. So it's kind of comparable to Burt, but a little thinner, less calcareous, and just slightly thinner on average. There was a site at Mullet that didn't have mats at all. Both sites at Burt had mat, but these were thinner, and they just looked different. And then Skagemog, my interpretation of the Skagemog samples is there are mats there, but they're not really very calcareous, and they're not as thick. So this is the gradient. What was really interesting is the Glen Lakes are associated with or have characteristics of low phosphorus based on the data I was able to get. It'd be interesting to see that there's a presentation by a couple of people with the Glen Lakes, it's the Leelanau Conservancy Group. And Steve Hamilton actually presented some data that indicates that phosphorus is increasing since a low point of around 2015 or so. That phosphorus has been increasing in the lake. So this might be an underestimate of phosphorus, but I don't think so. I think it might also be, although the diatoms tell us a little bit different, they're different. So maybe it's true. Maybe the phosphorus, these old phosphorus measurements are just off, but the Glen Lakes do not have the GBA mats in them. One has, you can go find a muddy mat, but it's not a thick GBA mat. Okay, so that was biomass. Generally a decrease, particularly in calcareous mats, as phosphorus increases. In the 20 Lake survey, now the species composition, so here I've ordinated the mat species composition, the diatom species composition of the mats. I don't have Skagemog and Bel Air analyzed yet. So we start with Charlevoix, both samples, so 2 samples from every lake all the time, at least 2. One from a site that people there might really want me to go sample, and then another one that I think, based on looking at the topography around the lakes, might be different. Land use and topography around the lakes might be different, and I go to that site. Charlevoix was really different from Petty and Hayawenta being really closely the species composition, even though the biomass is different, the species composition is really pretty close. And then Little Traverse is close to that, and Burt is actually kind of lumped over here with the calcareous algomats group. And then, Mullet is kind of here in the middle, and then the two glens tend to slide over to the south and east side of the species composition. Big differences between the two glens, the two little glen samples, because we went and we looked all over to find a muddy mat, and we found it. And so that's one of these two samples. So we're looking for variability within these lakes and trying to characterize that. And then plotted over this, the red lines are phosphorus isopleths. So you can see that in the low phosphorus, less than 3, that's where we've got Charlevoix up in the less than 2 region. Petty, Hayawenta, Little Traverse are in the 4 zone. And Burt is a 4 to 5 zone, 4 to 5 zone for Burt up to 6. And then the isopleths flip around so that Little and Big Glen Lake are in the lower phosphorus isopleths, but they're at the opposite end of this kind of GBA gradient. Or actually, I shouldn't say that, of this species composition gradient, whether it is or is not related to GBA taxa. And it does seem to be related to GBA taxa. So now if we look at the sum of the 3 GBA taxa again, because I've only got 2 samples, I didn't do box plots. I just plotted those 2 samples. The relative abundance of GBA taxa is high in Lake Charlevoix. It's also high in Petty and Hayawenta and pretty high in Traverse. It's low in the glens, except for one of the samples, which if I went back, it was a little thin calcareous mat. So that might be that sample. I'd have to tweak that out. But again, it's just one observation out of so many that you can make, and trying to come up with generalities. But we've got a decrease in the GBA species as well as the mat biomass as we increase phosphorus concentration among these systems. So again, back to the conclusions that this is just the beginning, or not the beginning. We're halfway through looking at stuff. It's always dangerous to do that. I really hesitate to do that, particularly in public, so that we don't jump to conclusions. But just to give you a peek under the hood, some idea of what's happening is it looks like nitrogen and phosphorus are having effects. Phosphorus effects are bigger. And I've said in past reports that nitrogen concentrations are low enough that they should affect growth of algae in Torch Lake. They're low enough. Phosphorus is relatively lower than nitrogen, so it should be more limiting, but it doesn't mean that nitrogen would not control growth of some algal species in the system. Or if you give all of the algae, all the algae do get nitrogen, but maybe all the algae are just doing better because they get more nitrogen, build more amino acids to help them harvest more phosphorus. So this idea of limiting by one thing or another breaks down a lot. Liebig's law of the minimum breaks down a lot. The species indicators of GBA were reduced by both the phosphorus treatments and the frame and the bowl experiments. They were decreased also with total phosphorus at lakes in the 20 lake survey. The biomass of the GBA mats decreased along the phosphorus gradient in the 20 lake survey. So these results are really consistent with low phosphorus causing thick GBA mats. So the plans for this summer to finish the 20 site survey and to get a lot more lakes in the 20 lake survey. I'm not sure I can get 10 lakes this summer. But in particular, I'm going to rerun the NDD bowl experiments, where I think we can learn a lot through experimental manipulation of these, the mats, using the homogenized samples and to see if phosphorus enrichment stops. I mean, so I'm imagining going to a site, taking one of these PVC pipes that make the bowls, inserting it into mats, pulling it up, and then sliding a whole mat down into the bowl and seeing what happens to actually pre-existing mats, as well as looking at the development more quantitatively like we have in the past. And so these approaches are just exactly the same approaches that we've used in the Everglades, where, you know, people were concerned about, you know, you add phosphorus and the algae disappear in a phosphorus limited system. And we were going, no, that's not possible. And then we ran experiments and we found out that, yeah, it is possible. That it changes the form of the algae. You lose the characteristic calcareous algal mats in the Everglades with phosphorus pollution. So maybe here we've got just the reverse, and we're going to use the same kind of techniques that were successful there in teasing out those cause-effect relationships. That's it.
Do we have any questions for Dr. Stevenson? Oh, you have one? Can we put you on here?
Hey, Jen, Dale here. Real interesting. The question I have is if let's say we added phosphorus, we get rid of GBA, what do we get? Because right now, the phosphorus is going to go somewhere.
It's going to go to a water column.
Okay, so is the main answer saying you got your choice? You got either GBA or you got an algal bloom?
No, there's probably a sweet spot that a good friend of mine called it the Goldilocks kind of. You know, there's a sweet spot like it used to be. You know, I think it used to be the phosphorus a little bit higher, or it was before there was this decrease in phosphorus potentially caused by a lot of different things that happened. Maybe a tight spot. Now phosphorus is coming back up in the lakes for multiple reasons. And maybe this is just going to go away. But if you add phosphorus to the lake, you're not going to be adding phosphorus in a layer across the bottom to get rid of the GBA mats. You're going to be adding to the water column. It's going to cause algae to bloom in the water column. And you don't want that. Even if you put it, you know, if it comes through groundwater, it's not going to have an effect on the mats, and it'll take a time for these mats to actually be quenched. But once phosphorus comes back, I mean, the best thing is, you know, I mean, that's what the modeling is all about, is that could there have been a decrease in phosphorus across the region like this? And could that have caused these mats to develop? That's a broader question. What I'm really looking at is this, and to answer your question, no, you don't want to add phosphorus to the lakes because it's going to cause bad algal blooms. I mean, it'd be as treacherous as trying to manage global change by increasing clouds and shooting a bunch of stuff into the atmosphere. You never know what's going to happen.
Jan, this is Becky.
Hi, Becky.
Question for you.
I'm doing okay.
On the bowl experiments, have you considered adding intact mats to see whether there's a change in them with your nutrient manipulation?
Yeah, that was what I was describing by taking a core of the mat and then sliding it down to the bowl. So yes, we're thinking the same thing. That would be a nice experiment to do. That'd be really interesting, because that was what we did and we were able to do with the thick mats in the Everglades. Is you can just cut them out like a cookie cutter. And you've seen pictures of me and the classic picture of Trish holding the mat in her hands, standing there like a thin mat of Jello, which is kind of what it is. Yes.
Just a quick observation. Last year, I was throwing the Frisbee to the dog on Torch, and all of a sudden I saw some paths that didn't seem for the algae mats to grow back in front of the property. And so then what I did is I took the hose and I put a pressure nozzle on the end of it. And I walked, it was probably, right where the surf hits to about 30 feet into the water and just ran the hose back and forth. And the algae mats pretty much disseminated, sort of like what you said, there was a sort of a magnetism or something with the different species that held them together. And for the rest of the summer, they never came back.
Yeah, yeah, yeah. So did you have a question or just an observation? Not just an observation. That's a good
Just an
observation.
observation and basically I plan to do the same thing this year if I get some algal mats, in front of the house, only like 20 feet long and 20 or 30 feet wide. And hopefully the wind will be from the north and I'll be able to send it all to Tom Joseph's house.
Well, that's actually the conversation we've had with people in the past is, just go out and rake it up and let it go over to your neighbors. But it could go offshore too and just fall into the abyss. It should regrow, but it takes a while to regrow.
Jan, I don't know if I can get this question right, but torch already starts out with a low phosphorus level. And so somehow the phosphorus level gets lower and the GBA goes up. And you've kind of got almost like a partial derivative of the change in the amount of GBA with the change in the phosphorus. And when you look at all your 20 lakes. So is it possible that torch even has low enough phosphorus levels such that when you drop the phosphorus even more from that response curve, you still have phosphorus left, for example, in torch, if you drop the phosphorus level by 1 part per billion, because you're starting out at 4 or so, how much the amount of GBA increase or decreases by if you went up, say, the other way around.
Yeah.
Either way, if you took the response curve and said to yourself, I have this starting phosphorus level, so now I decrease it even more. Can you make sense of the increase in the amount of of GBA, or do you kind of run out of phosphorus to deplete? You know what I mean?
Yeah. Well, I think what you're saying is, what's the problem with decreasing phosphorus even more? You get closer to Lake Charlevoix. Well, Lake Charlevoix hasn't. You've got a ways to go to get to Lake Charlevoix. So, and I don't think that's what, we don't have enough data, although it's across a lot of lakes that shows that, phosphorus is now coming back up from that 2015 or so low that has been observed in a number of lakes. So,
Jan, with your experiments, you're talking about the number of species mostly. Isn't the real thing we want to know is sort of this graph, which is biomass? And so it's if we add phosphorus, yes, you can look at this one and say this is what you expect to see. But if you add phosphorus, the real question is, does the abundance go up? Not the abundance of species, but the gross abundance of algae. Isn't that really what we want to know? More than anything else, more than just the species numbers?
And just not to get this, so let's just keep it, you can have more algae, but it won't be a thick GBA mat. It won't be a thick calcareous mat. So there might be more algae in Lake Skegamog in the benthic surface area than in Lake Charlevoix, but you've got big, thick nuisance mats in Charlevoix, and they're kind of, yucky for people in Skegamog too, but they're not like the Charlevoix torch elk mats, which seem to be new. And that what's caused the processes that cause the development of these mats in low phosphorus are different than the processes controlling the development of mats in high phosphorus. And, but it's important to know, so it's important to know how, you know, the nutrients are affecting growth rates and absolute abundances. Absolutely. Yes. You know, that's true, but that's not the whole story. And then the other complexity is, if you go back through the many wonderful pictures that Becky has sent to me for over the years, primarily Becky, that there are different growths of algae that people around the margins of the lake in particular, that people have said are new. And so trying to understand what's regulating the ecology of the algae in the bottoms of these lakes will help us kind of model mentally, at least mental model, you know, so could that also be causing these thick mats that don't have calcium in them, but have the same GBA species in them? So that's the caveat that's here. I mean, there are two of them. So two caveats to your question: that yes, we're interested in whether it increases growth rates, but increasing growth rates is not necessarily the answer. It's increasing accumulation rates, and accumulation is growth minus loss. If you have thick, firm mats that are difficult to break up compared to nice thin mats that snails and everything else likes to eat, then you know, you can get a large accumulation over a summer-long period of a thick mat that grows slowly. That's the Everglades story. That's the Didymosphenia story. You know, when the algae can't grow at a maximum rate, they extrude tremendous amounts of mucilage because they can still photosynthesize. So they produce the mucilages, and that holds them together in these mats. And so this is kind of, you know, what we're trying to understand. Increased growth rates, increased mucilage rates. Does that mucilage combine with calcium precipitation? All that kind of stuff. Okay. And the bowl will help us learn that and experimentally understand that, and then relate that to the survey results.
One of the things that'll be interesting, we do have our 12 nearshore sites, and right now, based at least 1 year data, some of our highest phosphorus numbers go with some of your highest GBA, but it also goes the other way. So I see very little relationship. It'll be interesting. We're going to keep it going. The other comment I have for is that you were saying that nitrogen is relatively low in the lake. It's 500 micrograms per liter.
What?
It's 500 micrograms per liter of nitrogen in the lake.
Yeah, those aren't the numbers I remember. I remember them being lower.
Because right now, for nitrate, we're at about 300 micrograms per liter, with Keldol at about 150. So we're at about 500 micrograms per liter of nitrogen.
Right. We can discuss this at some other point, but the numbers that I remember seeing were down in the 250 range. I think of nitrogen starting to be limiting at 200 to 300. And again, we're parsing out whether it's particulate or dissolved, all that stuff. So, and we're parsing out, is it right along the bottom or is it up in the water column? Nitrogen could be limiting. It's on the border there. I mean, that's something that I think we should consider based on these results.
Any more questions from the audience?
Any of this is another question, right? Whether it's important in understanding the GBA, but you certainly wouldn't want to be adding more nitrogen into the lake either.
Thank you, Jan. Are there any more questions from the audience? Here.
Hey, Jan. Hey, Jan. That was a really, really excellent presentation, and I appreciate all of the work that you did, especially this kind of, you know, more granular species level assessment.
Yeah.
And I was wondering if you could tell us a little bit more about the 3 GBA species. I know 2 of them are like heavy mucilage producers, but I was trying to to make out in your 2018 data, just the kind of phenological data, do those three taxa, is there interplay between them? Like when the abundance of one goes up, does the other goes down? Or do you see any kind of relationship between those three in particular?
So I don't think I've got enough, or I haven't analyzed enough detail, or probably have enough samples to pull that out. But just anecdotally, again, I remember the Schnitzia denticula, which was misidentified in some of the earlier samples, being really abundant in one of the Charlevoix samples. And so it's kind of interesting trying to parse these taxa out and figure out, are they producing, are they, actually the cause of this or not? And of course, the other really important group in here is the crust of cyanobacteria that will develop over the top of the GBA mats as they get a little bit older. But we're trying to figure that out as well. So I don't know which species are responsible for producing the mucilages. In general, I think of, plankton produces lots of mucilages when they're nutrient limited. So I think it's a more general phenomenon. In the Everglades, they really tried to attribute, using the concept of ecological engineers, that there are specific species that are really important in making a change in the habitat structure. And they've used, they've made some presumptions about certain taxa doing that. And I'm not that convinced that that is as helpful as understanding that a lot of the taxa do that. And but trying to understand those, I mean, I am not particularly looking at how much mucilage is produced by each cell. I hope to just be able to get somebody to analyze mucilages in the cell, in the mats, right? How much extracellular carbohydrate, how much EPSs are there? But that's another, find that assay, get the samples of those.
Absolutely. Thank you.
Any more questions for Jan?
Dave Holzschlag, thank you for your presentation. Really interesting.
Okay, I'm watching on YouTube.
Oh, okay. I was just curious about why Skegamog would have 17 microgram per liter total phosphorus when it lies right between Torch and Elk with 4 micrograms per liter total phosphorus.
Was that a question for me? Oh, I'm sorry. I didn't hear it. I thought we were done.
Hi. I was just curious about your sense of, you show the lakes in rank order of total phosphorus.
Yeah.
And Skegamog is at 17 micrograms per liter. Physically, it occurs right between Torch and Elk, and Torch and Elk have 4 micrograms per liter. So what's the story?
Yeah. I you're asking why? How is that plausible? Or so I guess it's I mean, my first hypothesis would be all the wetlands that are in the northeast corner of Skegamog. That is it pronounced Skegamog? Is it a long E? Yeah. Okay, Skegamog. It's the wetlands in the northeast and along the river channel that are draining. That often wetlands contribute load more nutrients into the water streams for sure. But I assume the same is for lakes, especially if it's a lower nutrient lake. So wetlands often leak nutrients in the 20 to 30 micrograms phosphorus per liter concentration. So I was assuming it's wetlands, and it's more tannic, right? Than indicating DOC and phosphorus related to that. So that'd be my first hypothesis. I don't know, but that'd be my first hypothesis.
Jan,
Yeah.
how thick does the mat have to be before the cyanobacteria, the blue-green algae start to form and cause ultimately blooms?
So I don't know. So I'm guessing that they seem to come in from the samples that I've looked at, and that's not a lot, you know, because we haven't sampled these thicker mats that much. But I'm thinking, you know, and also looking at some of the earlier samples, earlier in the year samples, it looks mostly like diatoms. But then, so I'm thinking they come in later in July. I'm not sure whether it's an issue about mat thickness or it's an issue of stage of mat development. How late in the summer is it? What are the water temperatures? What are the phosphorus concentrations? So there's remember, well, I don't know whether everybody has all the background, but I created a YouTube video showing me kind of ripping apart a mat and showing these the calcareous crust that was part of the surface of the mat with, you know, almost like structural mucilaginous components, but then a relatively thick brown mucilage on top of, and they were coccoid cyanobacteria. They weren't filamentous cyanobacteria. They were masses of these coccoid bacteria, which are difficult to really identify without using molecular approaches. So I would say it's not necessarily a matter of so much. So just to characterize the cyanos a little bit, you can learn more from that YouTube video. And I don't think it's so much related to the thickness of the mat as kind of the time and kind of the state and the stage of development of the mat.
Answer your question? Okay. If there's not any more questions, we're going to move on to the next presenter. Any more? Okay. Thank you very much, Jan. Excellent presentation.
Yeah, you bet.
Hi. Does anybody need to stretch, or are you guys going to be awake for this next little presentation? Okay. All righty. My name is Trish Narwold. I'm a co-founder of Torch Conservation Center, and I was volunteered to give this presentation due to sadly, the untimely death of the chief scientist at Phycotech, Dr. Anne St. Armand. She was a woman science pioneer, opening her own laboratory, and I and others in this room will definitely miss her knowledge in phytoplankton and her enthusiasm for lake science. I'm going to be talking to you about microscopic plants, otherwise known as phytoplankton, way down there in the bottom of the food web. And then I'll move into zooplankton, but I guess I don't have to worry too much about talking about it because you're going to cut that part of the survey next year. So let's go to the next. You're going to see, you might as well. Can somebody pop the slide for me? Yes. All right, here's Dale's map, and I'm going to show you where the plankton samples were collected from. There were basically 4 sites, the 2 stars, which was the deep north basin and the deep south basin. I'm calling them DN and DS. I don't know what you called them. And then there's the 2 near shore sites, which is, the one is up by Hayawenta Point, which is also where Dr. Stevenson was talking about, and that's the N03. I changed it to NA because it was just too many numbers for me. And then the other near shore site, and this was supposed to be the high algae area, is off of Alden, and that's the N10, and I changed that to NB. Jim was out 7 times from April to October, 1 time a month. So we have 7 times 4 samples, which is 28. 1 went MIA, and so we do not have a June sample for the Alden area. So basically everything I'm going to tell you about is coming from 27 samples. All righty, next slide, please. All right, phytoplankton is where we're going to start, and just a quick little basic review that phytoplankton is like land plants, and it contains chlorophyll that requires sunlight and nutrients, and that's why we're so concerned about nitrogen, phosphorus, and sulfur. It is buoyant. I'm showing you some common types of phytoplankton, and those are diatoms on the left, golden algae in the middle, and cyanobacteria. These 3 species were actually found in a lot of the Torch Lake samples. The diatom Psychotella and diatoms have this interesting characteristic in that their cell walls are made of silica, so it's like glass walls. Golden algae, we had a lot of Dinobrion in our samples. Golden algae have accessory pigment that allows it to give off this golden brown color. And then cyanobacteria or blue-green algae, it can be hazardous or not. This species, which was common, the Alphanocapsa, is not harmful. So I just wanted you to have a visualization of what these species that you can't see with your naked eye look like. We'll go to the next slide, and we're going to start talking about the abundance, how much of this phytoplankton was around. So in this graph, I have a x-axis, which is time, which is the months, and the y-axis, which is natural units. And I learned that natural units is not necessarily cells per milliliter, but it could be a colony. So if I had 5 of one species kind of grouped together, it would still be counted as 1. But this was the easiest number for me to grab from the 96 pages of report and the Excel file that went out 100 columns. So bear with me. I've put the deep north and the deep south sites in blue, and the near shore A, which is up there at Hayawenta, and the near shore B down by Alden in green. So what else do I need to tell you? Abundance can be defined as the number of phytoplankton in a certain volume. So you see that I have a volume axis. The abundance of phytoplankton in the nearshore sites was slightly higher than the deep basin sites in July, which you can see the peak up there in green, July, August, and October. I did not perform any statistical tests for significance in case that gentleman is still here. But they were pretty close forget what I said there. I just didn't do any tests. So let's go to the next slide, and let's look at the phytoplankton abundance through the season. Again, I'm looking at a bar graph where time is across the x-axis, but I've grouped my sites now so each month has a different color, and my y-axis is still the natural units. And what you'll see is that we have a pretty similar trend in all 4 sites. And that's where we start with low phytoplankton abundance in April and May, and we increase markedly in June. We peak in July, except for the nearshore B, where we peaked in August. But then we start declining declining in August and September. Although when we end up in the season, we're much higher than we are at the beginning in the springtime. All righty, next slide for you, me, please. In that 2020 study that TLPA funded, looking at tributary nutrient loading, they also did 6 sites for phytoplankton analysis in 3 months, the May, August, and October. So I've plotted them on the left side of this graph, and it's very similar to the last one where we have time across the x-axis, but we're looking at just 3, not 7 months. And the y-axis is still the natural units per milliliter. And what you'll see is on the far right is our data from this year for May, August, and October. And I added the table because we actually do have numbers in May for both sites in 2023. You just can't really see them because they're so low. So, all righty. What else? So basically, this one is pretty easy to look at, and you can see that the 2020 phytoplankton concentration was much greater than the concentration in 2023. In 2020, Dr. Saint Amand identified or characterized the 2020 phytoplankton as being low, but expected this for oligotrophic lakes. I looked for a scale. I couldn't find one and wasn't referred to one, but I would think that if she were around, she would call our 2023 sites very low. I did do a comparison where I averaged each month's abundance for the 6 sites in 2020 and did the same for the 2 sites in 2023, probably breaking every statistical rule possible. But the May average phytoplankton counts in 2020 were over 150 times higher than that in the 2023 counts. All righty, let's pop to the next slide. And we're going to slide through this really quickly because what I wanted to point out here, and I forgot to tell you, but Dale did mention that the deep basin sites for 2023 were composite samples. They took samples from 0.5 meter, 3 meters, and 9 meters. The research design for 2020, they just took a grab sample at the surface. So we can't really even compare these 2 things because they're sampled differently. For all we know, by grabbing the water at 3 meters or 9 meters, we've diluted our phytoplankton. So the message for this slide is basically we need to have very standardized methods so that we can compare our data from year to year. So pop out of there. Alrighty, so I've talked about abundance, and now I'm going to go into a little bit of species composition. And in 2023, the 27 samples, 20 of them were dominated by diatoms. And they had a high relative abundance of 50 to 92%. The other samples, the key ones are the ones in June where we did have a transition from diatoms to golden algae. The other, what does that add me up to? 3. So the other 4 samples were more evenly distributed between diatoms, golden algae, and cyanobacteria. I had the one sample where I did get a little higher cyanobacteria, but 36%. The next one was like 35%. So it's not very different. So the key picture here is we had a lot of diatoms in 2023. And remember, these are in the water column. Let's look at what happened in 2020, going back to that TLPA study. And you'll see that the cyanobacteria dominated all 18 nearshore samples. They had another high relative abundance of 71 to 97% of the cells. So this is an easy comparison. You know, one year's a story about cyanobacteria and the other's about diatoms. All right, so let's move on up the food chain up to zooplankton. And for those of you who haven't spent much time learning about zooplankton, copepods is the story of zooplankton. There's thousands of species. They have these little antennae that they use to move, and they're typically found in the sunlit zone because that's where their prey is. That's where phytoplankton is. There's also a group of rotifers, which are about the size of a grain of sand, and they move with a kind of a unique crown of hairs that pulls water in. And again, these are phytoplankton eaters. So let's take a look at the abundance of zooplankton in the nearshore and deep basin. This is similar to the other line graph where you have months going across the x-axis, and this time our concentration or abundance is in animals per liter, and the lines for the deep north and deep south are still in blue, and those for the near shore are in green. And basically the zooplankton abundance was higher in the nearshore sites than in the deep basin. If you can look at those June and August lines. We were missing that June sample, so I have a bit of a hole. Yeah. So, all righty. What else can I tell you about this? Oh, we're going to look at it during the season. So this is that similar table bar graph where I have my sites on the bottom, but each color is a different month. And what you'll note is that the lowest concentration of zooplankton occurred in April for all sites. And if you look at that deep north on the left, it's the only site where the zooplankton abundance increased throughout the season. And basically, I couldn't make out any discernible trends in the other three sites. Luckily, there's a great void in zooplankton information on Torch Lake, and I guess we'll perpetuate that. So I have nothing else to compare this to. And so with that, let's move on to my zebra and quagga mussels, which we're going to talk about veligers here. Alrighty, and this is a picture of a veliger. It looks like a little teeny plate. If we can go to the next slide, I'm going to give a brief introduction to zebra and quagga mussels. They both are native of the Black and Caspian Sea, although it looks like they're quite happy here. Zebra mussels, the way that I was taught to discern that from a quagga mussel was to lay them on the ventral side, and if they can lay flat, they're a zebra mussel. There's a bit of an elbow in your quagga mussel, so they have a much difficult time to stay flat. They'll roll over, and this is basically as you're picking them up as shells on the beach. But let's talk, I want to share a little bit about their life cycle. They can live 4 to 9 years, depending on the reference I was looking at. They reproduce in their second year of life, and one zebra mussel female can release 1 million eggs, while a male zebra mussel can release 200 million sperm. Spawning typically occurs in May through October when the water temperature is in the mid-50s. 2 days after fertilization, there's a free-swimming larvae that's called a veliger. And this veliger can live for 3 to 4 weeks floating around in the water before it settles down and either attaches to rock, depending on what type of species it is, or the sand. In their veliger state, they do eat bacteria and small phytoplankton. Let's go to the next slide and look at how this invasion of mussels occurred in our area. In 1994 to 95, zebra mussels entered into Lake Michigan. A few years later, they popped into Torch Lake. This is the time where everybody started wearing water shoes because feet were getting cut by the sharp edges of the zebra mussels. In 2000, quagga mussels invaded Lake Michigan. 2005, they were found in Lake Charlevoix, which isn't surprising because it's basically an open channel to get to Lake Charlevoix through Round Lake from Lake Michigan. And then in 2015, there was this mysterious little report that not many people saw that stated that quagga mussels were found in Torch Lake. This was an eagle expedition, and it wasn't common knowledge. And in fact, Tip of the Mitt that same year was out doing invasive species monitoring, and they stated that there were no quagga mussels in Torch Lake, which is probably very true. They weren't in the same location where the Eagle researchers were looking for mussels. But I want to point this out because in 2015, that was the first year that Jan Stevenson started looking at golden brown algae in Torch Lake. That was the first year that Rex Lau and Pat Kosiocek started working on looking at our GBA in Torch Lake. And I just feel that if this knowledge had been a little bit more common, the path of research may have gone a different way. And so the lesson here is that sessions like this, despite me not liking to talk to you all, are really important that we share this information about our lakes. Luckily, the 3 lakes jumped on this and they were out on their boats last season, and they have a report which was in your folder. So let me give you a few highlights of what they found. They found that the lowest number of mussels were retrieved from the north end up there towards Wilkinson Creek on the east side. The highest number of mussels, and they were initially just looking at what they would find. Mussels were retrieved from the south end off of Deepwater Point, which is across the way from my NB, which is the Alden Way. But what was really interesting is 94% of the mussels they collected were identified as quagga mussels. There were very few zebra mussels. Well, let's see if my villager information how that plays with the findings from 3 lakes. And first of all, I have to let you know that Phycotech Labs, their techniques are unable to discern between quagga and zebra mussels. So any mussel or any villager that was counted could have been either. So I can't help with the, what I want to do is take the information from 3 lakes and assume that probably most of these villagers were probably quaggas. So in this graph, once again, I have a bar graph where I have the sites going across the x-axis with their each month having a different color. Up here, my y-axis is going back to those natural units per meter cubed. And I want you to notice that I included the table because in some sites, which basically the first 2 months, none of the sites contained any villagers. And I wanted to make sure that you didn't think that perhaps you were missing a little teeny line or something, but there's really were a void there in those samples. And you'll also see then the nearshore samples in August and September also did not have villagers. And villagers were most abundant in the deep south site, which complements the 3 lakes results with the greatest number of mussels retrieved from Deepwater Point, which was in that area. So overall, the South Basin water samples contain 2 times as many villagers as the North Basin. So let's go quickly and I'll summarize what I've learned from going through this data and have hopefully shared with you, and that phytoplankton abundance nearshore sites were slightly higher than the deep basin sites. There was very low abundance in 2023 compared to low abundance in 2020. The seasonal pattern in 2023 was really low in April and May. We peaked in July and August and declined down in September and October. Next slide, please. When it comes to species composition, the nearshore and deep basin sites were similar. In 2023, the diatoms dominated nearshore sites, except in June when golden algae dominated. And in 2020, we had a whole different story where cyanobacteria dominated. Okay, and then for zooplankton, the nearshore sites were slightly higher than the deep basin sites. And I I could not find a seasonal trend. Need more data. The villager abundance was highest in the Deep Basin South site. And this opens up some questions, which luckily there's some great presenters still to follow me. And some of these questions come up. Is the delayed phytoplankton abundance peak, which occurred in July, the result of quagga mussel grazing in the spring? Is the overall decline in phytoplankton abundance from 2020 to 2023 the result of quagga mussels invasion in Torch Lake? Why is the phytoplankton species composition so different in the 2 years of sampling? And what factors are contributing to increased numbers of veligers and quagga mussels in the south end of Torch Lake compared to the north end? So with that, I say thank you. We'll go on.
You have a question? You don't get up that easy. Got some questions for you. No, that's okay.
What will eat the villagers?
What will eat the veligers?
Yeah.
I assume whoever's the fishery person, I assume whatever's going to.
What is okay? So in the native habitat for these mussels, what controls their populations?
Our native population?
Well, in
Or the-
Ukraine or wherever it is.
Or the invasive ones?
Gobies.
Oh,
Gobies.
okay.
We don't want any more.
We're Gobi
Okay.
deficit. We're Gobi deficit.
No.
We don't want any more.
All right. So brown gobies are what we're going to say eat our.
No, we don't want any more round gobies. They're bad.
Alrighty.
And in fact, when we do get to the DNR presentation, she does talk about it a little bit.
Oh, you're not allowed to ask a question.
I am. I flew all the way here to ask you a question.
I should have just come up to Tahoe. This could have saved us.
So I really appreciated your point about needing to standardize monitoring methods. I noticed that you were presenting the phytoplankton data as, I guess, counts, sort of so many.
For which one, Jeff?
Well, I guess for all of them, the
For the
phytoplankton.
phytoplankton,
Yeah.
the natural units, yeah.
Yeah, I'm just worried that because Cyclotella dominates and because they're really small, you may be misrepresenting the biomass. And so, so from a modeling point of view, we model carbon or chlorophyll, something like that. So knowing what the biomass will be important in the future.
Yeah.
They probably have that information.
They
but
do.
it would be-
I did
okay.
graph one biovolume, but I
Yeah.
was saving time, and so, but I do have it. I can't remember it. But
Okay.
yeah, it's a good point that the size.
We could get in to stay a couple more days, but it's
Ah,
all 100 pages.
I will. There you go. You can help me out. And
Yeah.
that's where some of these phytoplankton are very small and some are larger. So the counts will be high, but the size, the biovolume could be very low.
Yeah,
So
I mean, at Tahoe, for example, it's by numbers, Cyclotella is 80-90%. Biovolume, it's 5%.
of course I would have picked Psychotella for you to be able to comment on.
Thank you very much. Thank you.
Just to follow up on Jeff's, I think the one thing that would be interesting is that we can compare the Secchi depths between years. And if the Secchi depths are the same, it's probably going to push towards what Jeff was saying, that maybe it's just the same amount of mass in the water. But
And that's sunlight driven?
I'll let Jeff.
Oh,
That wasn't what I was saying. Actually, the Secchi depth probably correlates more
with the
with number of Cyclotella.
okay.
It's another
But
story.
so it sounds important that we should be looking at comparing the biovolume from 2020 to 2023. Okay.
Trish, quick question about the villagers. If you monitor those each year, can you get an indication of where the quagga mussel population is in its life cycle? Is it in the increasing mode, stable mode, declining mode by monitoring, how many and all that, or is that not?
I don't have the knowledge for
Okay,
that.
all
Maybe
right.
somebody else
You
does.
might be able to ask that question when Mark's
Yeah.
done.
feel that
Yeah.
you could answer that question. Did you?
Okay.
Okay.
I didn't
Great.
want to put you on a spot.
I like that answer, though.
You want to push it off the mark. You got one more question coming.
When you say a standardized sampling for the plankton, are you referring to things like we're not starting at the same depth, we're not analyzing the same amount of water column gallons? What do you
I'm
mean
sure
by
Jim-
standardization?
Well, and I probably should have compared it to also the other way is a grab sample where you're looking at just taking water from a half a meter below the surface and you're using that as a sample versus where you're taking and combining from half a meter, from 3 meters, and you're adding that to 9 meters. So you're putting all that together versus taking just that one top sample. And so standardizing that, which the USGS is doing.
And,
Really much of a difference here. We're not filtering anything. It's just compositing it. So it's, I don't think the phytoplankton would stratify.
I didn't think so
You don't
either, but
think
I don't
so?
think we can compare them. No.
I would, I work, I work with the Inland Seas Education Association. When we take the students out, we generally go down a fixed amount of feet and we sample a fixed amount of water column of gallons. And
Well, that's a tow, right?
no,
That's
it's
water.
done vertically static, so to speak. But yeah, but when you say we're going to swirl it around, and I mean, we're getting a yard, a meter versus 6 meters. I mean, there's a lot of, just like fish, there's a lot of different variety in that growth, what's growing in that water column.
Sounds like you experienced this.
Alrighty.
I think we're
Thank
going to
you,
have a
Gail.
discussion on that at dinner time or something. But any more questions for Trish? Thank you very much, Trish, for taking on.
For volunteering.
Yeah, you'll probably never let me twist your arm again in anything. Okay, so obviously we're a little bit off of our original agenda. So what we're going to do now is we're going to take our break now because it's about that right time, and we're going to take lines 9 and 10 and move them down so that the next presenter, when we come back from our break in 10 minutes, will be Jeff. Okay, is that all right with you, Jeff? So we're going to let Jeff come after the break. So let's take about a 10-minute break and come back and try to wrap up with the rest of the last part of the agenda. Thank you. we're going to have Dr. Schladow come up and talk to us a little bit about Lake Tahoe. I got to get your bio up here. I don't have you set up on this computer, and that only works on this one, not on this one. I'm using two different vintage computers here.
You kicked me also. I mean, you have, you only have 14.
Are you picking on him for that? Okay.
Yeah, it took me hours to come up with that. Hi, my name's Jeff Schladow. I'm really happy to be back at Torch Lake again, and reconnecting with many of you who I met last time. Next slide. So I guess part of the reason for that title is that the first time I came here, and even before I came, everybody was saying, oh, Torch Lake, it's like the Lake Tahoe of Michigan. And I believe them. And in many ways it is. I mean, it's a beautiful lake. It's a clear lake, even with all the issues that people have been discussing today and last time. But there are some very important differences. So Tahoe's a little bit deeper. So it's about 1,645 feet deep, making it about the 11th deepest lake in the world. It's larger in area, 500 square kilometers, which is maybe, I don't know, 350 square miles, 300 square miles. The watershed is relatively small compared to the surface. I mean, it's bigger than the surface area of the lake, but it's small as far as lake systems go. It's more or less a headwater lake. So we don't have this chain of lakes feeding into it, regulating the water, changing water quality. It's 80% forested. There's no agriculture, so no cherry trees, no tomatoes, no dairy farms, no nothing. People try to grow tomatoes and they can't up there. And no mining, no logging, etc. Septic tanks were discontinued in the 1960s. So there's a deep sewage system and the sewage is pumped outside the basin. So it goes, and California, and used for ag. It never freezes, has a 650-year residence time, meaning that's the average time a drop of water would spend in the lake. And it's known for its outstanding clarity. Next slide, please. So just repeating, it's very different than most lakes. It doesn't have the major sources of contamination. And so the usual suspects, and Dale and I have worked on many lakes over many, many years, and it's, within 5 minutes, we're sort of betting each other what the cause is, what the culprit is. In this case, the usual suspects, in the case of Tahoe, the usual suspects aren't there. Septic tanks, wastewater treatment plants, industry. It also has very high dissolved oxygen levels, top to bottom, very similar to Torch Lake. So this internal loading, the release of phosphorus from the sediments, also doesn't occur there. So that's sort of one of the unusual suspects that we don't have. So what we do have is people. We have a lot of people. Deceptively large number of people. If you look at the census data, the permanent population is about 60,000. But we have 15 million visitors a year, stimulating a $3 to $4 billion economy, which may sound good, but it brings with it lots of problems, lots of challenges. And what we determined based on analysis, probably going back 20, 25 years now, is that the biggest contaminant at Tahoe were very fine particles. So what we refer to as the urban particle loads. And that's the thing that is they're attempting to control there. So we have a different set of problems with a different cause. And that's yet a further difference between our two systems. Next slide. Well, I guess I just said that. The drivers of degradation are different. Okay, next. Okay, so water clarity has been used as a metric of water quality at Tahoe. And I'm not saying, we shouldn't say that Secchi depth is the be all and end all. It's just a very convenient integrator of lots of things, and it's really pretty simple to use. And the fact that we had a long-term record is convenient. And that's one of the big advantages we have over many lakes, is that we have a long-term record. So just sort of pointing at this graph now, this is sort of an inverse graph. So zero clarity or zero Secchi depth is at the top. And so the lower down these points are, the further down you can see. So every one of those white circles is an average, an annual average of about 25 points. So we go out, we're not wimps in California, contrary to popular belief. We go out summer, winter, spring, fall. So every month we're out there. So those averages represent an annual average clarity. And what you see is that for decades, it was declining on average. There were periods of multiple years where it got better, but then it got worse. So this is when most of the work was done study-wise, and a plan was devised, and it was targeting these inorganic particles coming in from the watershed due to development, building of roads, shopping centers, houses, dust stirred up by hikers, all these things, just the influence of us, of people in the watershed. And so according to the modeling that was done, that red dashed line is what was thought to be the trajectory of improvement if you put in sufficient money. Well, it turns out, as you can see, it hasn't followed that trajectory, but it has flattened out. Whoops. It has flattened out. So instead of just declining, in about 2000, it's flattened out. So that is an improvement, but things haven't gone completely to plan. Ultimately, the goal is by 2076, it'll be back to what it was. It's a plan. Right now, something isn't working. Whether it's the methodologies used to reduce loads or whether there's something that's being missed. There's some factor or factors that are influencing the lake. So big money was spent, $2 to $3 billion collectively over 20 years. And it's flattened, it stopped the decline. It hasn't led to the improvement yet. Next slide. Okay, so the reason this money was even available is that a very good job was done over a number of years of identifying the causes of the decline, although it seems we may have missed something. Predictive models were used, and models are being mentioned by many people here, and they're really important. I mean, you can come up and say, you have to be quantitative. And although there's good reasons to think if you do this, it will improve, or do that, it won't, how much will it improve, and so on. So we had a whole nest of predictive models, and based on that, a management plan and costs and the like were developed and broadly accepted. And that broad acceptance, I think, is important. And I think this group, or these groups who are here, are really part of that process of broad acceptance, which is great to see that you're so far along. So Torch Lake, however, is different. The root cause of the problem still need to be identified. And that's what many of the talks today are addressing before these potential solutions can be proposed and tested and a plan formulated. All right, next slide. Okay, I want to talk mainly about variability. I've been involved in, I've attended many meetings like this. And you know, it takes a year or so to get initial funding, a year or so to plan what's going to be done. And here we are today. After that, there's a year of data. And so many people in the community say, we've been at this for 3 years. When are we going to stop the research and do something? What I want to talk about is it's so easy to do that too quickly. Frustrating as it may seem, it's the variability in everything is so large. So next slide. Okay, so I'm going to give about 6 or 7 example graphs from Tahoe, showing some of the variability in different aspects. So this is one for the meteorology. This is going back to whatever, 1915, 1916 or so. This is the snowpack as measured in early April. It's been measured consistently at the same location. And you can, so 150 inches of snow as the mean in April, early April. If you had just 1 year of data, like the USGS has now, which year would you have chosen? Yeah. And here, I mean, and there are multiple years of low or multiple years of high. So next slide. So this is the surface temperature. So we've had a wonderful collaboration with NASA since the late 1990s, where we have buoys out on the lake. And one of the things we're measuring there is surface temperature every 2 minutes. So this is just the data for July, probably the warmest month we have there. And again, this is 2 minutes data, 2 minute data every day, day and night. And you can see some people would expect it to be warming because of climate change. Well, it's a pretty weak trend there. But what's more important is the interannual variability. Once again, which year is typical? We don't know. Next slide. This is something that was alluded to earlier on, the length of the stratification. So those of you who don't deal with lake physics all the time, this is in the spring, the surface of the lake warms up, and then in the fall it cools down and the lake mixes to the bottom. So how long is it between when it starts to stratify, get warmer on top, and when it starts to mix? And that's really important for the physics of the lake, for the biology, for the biochemistry. It controls everything. What I've plotted here is the number of days of this stratified period at Tahoe. Once again, it's changing. Here there really is a long-term, statistically significant trend. And this isn't just a Tahoe thing. You know, there's people are seeing this on lakes all around the world.
So you're saying half a year it's stratified? The lake stratified for half of the year?
Well, it depends how you define stratification. So we have basically an index. I mean, we're looking at stratification between the surface and 120 meters down. So, I mean, we could have chosen a different index. This is one we came up with. We can evaluate it objectively. So it could be weakly stratified, but weakly stratified from the physics point of view is still stratified. It doesn't have to be strongly stratified. It's like someone say, well, I'm just a little bit pregnant. You can't, you either are or you aren't. You're stratified or not stratified. Oh. No, it's just for whatever number of days, that's when there's a significant amount of stratification that will constrain motion to be more horizontal than vertical.
So if we did the same thing with George Lake, and of course,
Yep.
we don't have the long-term data, but what number would we pick to be comparable for depth of level?
Oh, I mean, what we use is we take profiles of the type Dale was showing, and we take it from our shallow site. Our shallow site is 120 meters. I'm sorry. And we do that because we do that one every 10 days. So we have a lot of data. So we have statistical robustness. The important point of this thing is that their days on the left. So between 1970 and the last 50 years, the stratification season, if you will, the summer-like conditions have lengthened by a month. Winter has decreased, or winter-like conditions has decreased by a similar amount. Again, it's changing. It's not changing the quality of your life. It's changing processes in the lake.
Intuitively, that looks like a very big change.
It is.
Very, very big change. You would think that would be an indicator of a lot of changes of the lake. Does other things correlate to that?
You could say the lack of improvement in the clarity may be correlated with that. I mean, it's again, there are a lot of connections that we're still trying to make. And this is climate change driven. And certainly when the plan was being formulated, climate change was treated very superficially. When you have questions, please use the microphone. Okay, so yeah, this is nutrients from the largest stream. We have 63 inflows. This is the Upper Truckee River, brings in 25% of the water and about 25% of the nutrients. Again, which year would you pick? So it's highly variable. And so even though you may feel frustrated with the various groups that they're not making sufficient progress fast enough, it takes time just to have confidence in what you're seeing is high or low or what normal is. So I guess I should say the total bars is total phosphorus. The pale green is the soluble reactive phosphorus, the part that can actually be used for photosynthesis. Next slide. This is just chlorophyll. This is integrated chlorophyll over the whole lake. So again, we have low values, something like 1 microgram per liter. And this is just going back just the last 30 years. And you see there is a lot of variability. There hasn't been a long-term change in the concentration, but there are low periods and high periods. And certainly, just as you're seeing here, there's seasonal variations. Next slide. Okay. So we too have attached algae, different, very different. We don't have these, the same ones you have. Ours are more, they attach to hard substrates, to rocks at the edge of the lake, referred to as periphyton. And this is what I'm showing here is for the last 20 or so years, the different colors represent 3 different sites. And I guess this is concentration of this periphyton. So the point here is it too is variable, even though it's a different kind of alga. Because I was bullied into providing my slides 2 days ago by people who will remain unnamed, There are some slides I would have liked to have added here based on the conversations that were taking place earlier. So I'm just going to talk about them, and I can provide slides additionally. So we've been measuring periphyton at Lake Tahoe in the same way for 37 years. At times we've had up to 55 sites around the lake. I mean, the shoreline's about 60 or 70 miles. And after 37 years, we wrote it up, and the conclusion was there has been no statistically relevant change in chlorophyll, in biomass, or anything. Pretty good science, huh? And everybody, agencies, the public said, you gotta be kidding. This isn't the lake I grew up on. It's changed. And we knew it had changed, but the data didn't support that. Which probably means we were measuring the wrong thing, or measuring something that wasn't showing the change. And so in listening to what's being proposed here, I was wondering whether maybe some thought should be given to what is it that we're trying to measure. We did something very similar. We chose a number of index sites and measured changes in chlorophyll and things like that. What we've started doing over the last 4 or 5, well, what we realized is that it's probably changed in aerial extent. And that's what people are reacting to. There are always bad parts of the lake, good parts of the lake, but it's the aerial extent. So about 5 years ago, we started doing it differently. So we still have fixed sites, much lower number now, but we're starting to use drones and a helicopter to basically give us an area, a quantifiable aerial extent. So using, say, for the drone, for example, when we go out to our different sites, we use the drone to go say 500 yards either direction, has a GoPro camera, has georeferenced date, has the shoreline in sight. It can see, just with an RGB camera, the different colors at the bottom. We can classify that, using site data to say, these are the golden brown algae, these are rocks, this is duckweed, this is something else. Basically working with Esri, we have been able to do this now pretty much in real time. We can fly the lake or do our drone surveys or the helicopter survey, have a gimbaled GoPro, and by the time it lands, we have the acres of golden brown algae, let's say, or whatever, quantified. So maybe that's something worth thinking about. I can send you the reports. Maybe it's not appropriate for here. Okay, next slide. Okay, conclusions. Torch Lake can use Tahoe and other lakes to provide guidance. For example, what I just said, hey, this is what didn't work for us. This is what may work for us. But our solutions are not going to be your solutions. And the same for most other lakes. Your existing data collection program is up and running. I think it's great. Talks about standardizing how you do things is exactly what should be happening. And I think the data program is allowing for modeling to take place in the future. You don't want to get to a point where now we're ready to model, but we don't have the inputs we need. So that prior thought is taking place. Things such as climate change, invasive species introductions, yeah, I mean, they're evolving over time, and it's only making it more difficult. Okay, next slide. So I love this painting. So this is Sisyphus by Titian. It's in the Prado. Okay, so Sisyphus was a really bad dude. I mean, he killed his relatives. He just did terrible things. And Zeus punished him. And his punishment while in Hades was to perpetually have to carry this rock to the top of a mountain. And when he got there, it would roll back down to the bottom. And so that was his punishment. That was his life. Lake restoration or lake management is pretty much, you know, well, it's almost the same. I mean, in that it's never ending. I mean, his task was futile. Nothing was ever going to change. But at least with lake restoration, it's hard work. It will never end, but you will get there, which is important. And I think that's it. Next slide. Yeah. All right. Thank you. We don't have quaggas. They have a very effective, it's quite expensive, boat inspection program. And boaters, I think it cost them, say, around $50 to get their boat inspected if it doesn't have a sticker. And I thought people would be up in arms. They probably would be in Michigan. But here they accepted it because they know what the price of having quaggas can be.
Jeff, if you do the aerial extent, I understand the shallower area in where you can line it. My understanding is that the golden brown algae goes down a little bit deeper. Did you have problems at Tahoe going into the deep end of your algae at the bottom?
I mean, we're really only doing, the parts where we can see, where you can see the bottom.
Constrained by.
Oh yeah, no, it's not. I mean, it's not the whole lake, but at least that way, we're starting to see, is it growing year to year in extent? We pretty much knew the rates it was growing at, but that wasn't the problem. It was necessary data, but not the problem. Dan.
Microphone for you. Is that okay?
Yeah.
How much money a year do you spend on monitoring Lake Tahoe?
A lot. We receive something, I'm guessing around, I mean, rough terms, maybe $400,000 a month. No, it's a year. It's a year. And that's actually subsidized by the university and things like that. I mean, if we were a for-profit business, we'd have gone belly up a long time ago. But it is, yeah, it turns out to be an expensive business. I say it proudly, we're out on the lake throughout the year. I mean, literally 3 or 4 days a week. We have a boat out there, and you add up, 3 people out on a boat, the mooring out 2 boats is, I'm trying to think, it's like renting a condominium in San Francisco. It's more expensive to moor a boat at Lake Tahoe than.
So how is it you were able to, what about the culture and the people around there allowed for that kind of expenditure starting 30 years ago, let alone perpetuating it,
It was cheaper 30 years ago. That's, I mean, part of my job was writing proposals. We get, say, we'll talk more about that, say, $2 to $3 billion. Where did that come from? I mean, that was a combination of California, Nevada, and the federal government. Maybe the federal government was, I don't know, 30%, 40%. California was probably 40%, and Nevada was the remainder. But it's a struggle. I mean, Tahoe had the advantage of saying it's Tahoe. It's so unique. It's so marvelous. Michigan has a lot of beautiful lakes. So even though Torch Lake is beautiful, everybody else is going to say their lake is also beautiful. So that you have a lot of competition here.
So the comments on Torch is that, it's not the way it used to be. And you mentioned that about Lake Tahoe. And you said, well, you've made all these measurements and the science doesn't say that there's anything wrong, but you haven't measured the right thing. Do you know what you have to measure to determine if there's a problem?
Yeah, well, I said we haven't measured the right thing for the shoreline algae. So we believe it's, measuring, what we were doing, we had measurement sites, and for each site, we were microscopically measuring algal growth. Whether the algae grew faster or slower wasn't changing people's perception. It was that it was spreading, that it was starting sooner, things like that. So now we've changed how we're doing it in an environment that's also constantly changing. So I think we have stepped on, we are on the right track. And I'd really like to talk to people here who will be doing those measurements. But we'll see. It's a very imprecise science, at least the planning part. Once you have the data, then you can get a lot more precise. A bit like fishing.
Any more questions? Well, thank you very much. And I'll remember to use the microphone next time I have a question. All right. Is Jerry next? Yeah. Jerry, are you ready? Okay, let me get his up on the. Jerry Sweden was kind enough to come up here from Indiana and join us today. And I want to welcome him. He's new to our group and hopefully be very helpful. Oh, you got him over there. Oh, okay. I thought he was on this one. No, he is on that. Didn't he jump try it?
Thanks, Tom.
We are over here.
Appreciate the invitation to come. I'm a retired professor and just tired. And I was drawn out of retirement because of water quality in lakes and streams and taking out dams out of streams. And so here I am. And one of the things I learned about teaching is there's a terrible time of day to teach. Guess what it is? 1:45. So I have a bag of lifesavers. And I used to take them to class, and I got really good at throwing them. I would tell the students, I wouldn't want to listen to me for 50 minutes. And when I see heads nodding, I could throw a good knuckleball. Look at that. So if you feel yourself nodding off, you just let me know, and I'll toss you a lifesaver. If you need a really wake up, I have some atomic fireballs. So, boy, oh boy, have we learned a lot today? Oh my gosh, how many of you are outside the sciences? Anybody? Is your head swimming? Mine is, and I'm in the sciences. What an awesome group of people to get together. And, one thing I did learn too from the last presentation, we need to be gentle on the moderator. He's taking, no, he doesn't. Okay, gloves come off. All right, man. Yeah. So I am going to be the reciprocal of the last presentation. And information on Torch Lake, I'm afraid, and a statistical outlier. So I'm going to talk about Indiana lakes, and I call them troubled waters. So if you want to go ahead and, oh, we have a pointer. That's perfect. If I can figure out which one of these to push. There we go. All right, so if you can go to the next, oh, this will advance it. All right, very good. So here's what I want to just briefly talk about. And this will be kind of, mostly, sort of, kind of, toward Indiana, is to take a look at sort of the temporal and spatial referencing as much as we can. And if you notice through a lot of the talks today, what's missing in action is historical data. And we just, don't we wish we would have known what it's like here before Europeans set foot on this country. And then we'll talk a little bit about the response of lakes to chronic nutrient and sediment pollution. I'll talk a little bit about our study design that we use and use 3 lakes as an example. And then we have started looking at lake sediment that helped, at least helps us close the rest of the story on phosphorus pollution and then why it matters. And this is the hardest part to get through, isn't it? We all like boiling the world to numbers. And so but eventually, we need to make sure that what the data we're collecting turns into something pragmatic that results in change. And then I was asked to put a little something in there about precipitation chemistry for Torch Lake. So I don't know how many of you have read Aldo Leopold. I started out in my career reading this. And as I was preparing for this presentation, this little quote out of Aldo Leopold came to my mind. And I'll just let you just spend a couple minutes reading it rather than I read it. Or not minutes, you should be able to read it in about 30 seconds. And so I think for those of us who know the most about natural systems, we are the ones that maybe feel the pain a little more. And I can tell you in Indiana, when it rains, we have streams that look like chocolate milk. And I will tell you that most people today think that's normal. We have a lot of lakes with blue-green algae blooms. People today thinks that's normal. And so there's been kind of this shift in lack of understanding that we need to help people understand how natural systems function. So this map is from Meyer 1995. It was with the Forest Service, and it shows the approximate location of virgin old-growth forest across the United States. And this could be 2024 pretty much. And here sits Indiana. Look in the north part of Michigan. Aren't you guys lucky? You still have some of that. But as you gave the story about Torch Lake, we know that that virgin old growth forest was removed. And so I tell folks, I'm not saying this is good. I'm not saying it's bad. But I'm just saying that when you make such huge landscape level changes, nature will have a response. And as scientists, what we want to do is we want to try to understand not only what the response has been and what it is, but we like to use modeling to help us understand what it will be based upon the data that we're able to generate from our research. Well, in Indiana, we're suffering from what I call the Great Chronic Pollution Spill. And it includes the aquatic dust bowl as one. By volume, sediment in our streams and in our lakes is the largest pollutant that we have to deal with. So when I get finished with this, you guys should feel very good about wrestling with some little microscopic, what do you call it, diatom that has a little gelatinous sheath on it. And so it should make you feel really good. You feeling better already? Or you just wait. So in the north part of the state, I drew a line there. And I call these the forgotten dead zones. We have hundreds of glacial lakes in northern Indiana. They're beautiful. There's millions upon millions of dollars of real estate around those lakes. And these lakes are dying right before our eyes. And so here's what we don't know. And this is what I've got drawn out of retirement for. And Melinda, who's sitting here, came with me. We actually thought we were just going to go fishing after I retired. And somehow that didn't work out so well. Although I think I have a fishing trip lined up. Is that right? Yeah, right. Okay. Got to barter somehow. So here's what we quickly learned in my very first meeting with the Lake Association was Lake Wawasee. And they had this whole pile of reports. And they said, would you tell us why can't we understand what's going on with our lake? And so the stack was like, and so I looked through them. I said, well, it's pretty simple. They said, what's the problem? I said, you have no data. You have a lot of information that you can draw off a computer from a desktop, but you really don't know anything about this lake. And so we set up an experimental design, very similar to what you're doing here at Torch Lake. And I know, Dale, we have a little bit of different approach, but still the end kind of being the same game, is to look at what is the water budget, looking at external loads by tributaries, which there was no data on, internal loading, legacy phosphorus in the sediment, what sort of load reductions needs to be to bring this lake back into compliance, ecological compliance. And in our case, we're, we're not looking at 4 micrograms per liter. We'd be happy with 40 in a lot of cases, but try to get those lakes back at least in close to the mesotrophic scale. The social science, I can't tell you how important that is, and this is a good illustration of that, is helping people who live around the lake understand why these things are important, and you were talking about the expense. And I call it conservation sticker shock, because we've underestimated in our culture the cost of ecological restoration and the importance of that. And so I tell every lake association, you should have a clean water fund, and it should be big. You can't have too much money in a fund similar to that. The other thing that is so important, I kind of got ahead of myself one bullet, because funding is so important, but is to leverage the data with milestones. And I know you're going to do that with this group. You have a tremendous team of scientists here working on this situation, where we don't have that luxury in where we're doing our work. But monitoring, that word monitoring, has sort of a negative connotation some places, because monitoring has been monitored for monitoring's sake. And we haven't quite made that next step of what do you do with that data to help restore the system that somebody has hired you to collect data for. And it's because it's difficult. And most studies, and this one is the same, no different, is that the questions you're addressing are, and the data you get, guess what? It's going to generate more questions than you answered, is what will happen. And that's the fun part of science, but it kind of gets to be a little bit challenging for people that are looking for answers. So Lake Wawasee is the largest glacial lake in Indiana, 3,000 acres. How big was Tahoe? Just a little. Darn. Well, I tell them, you know, this lake is propped up with a 6-foot dam. And I told the folks at Lake Wawasee, I said, just pull that dam out and see how big your lake is. They didn't like that very well, but they're great people. And again, this was the first lake that I received a call about, because they were concerned about the water quality of the lake. And without having that data, we initiated a program with them. It's called the WINS, the Wawasee Inlet's Nutrient Study. And so we took this is kind of stale news. You guys understand this. We looked at all of the tributaries coming into the lake, and we set up gauge stations coming in. This is about a 3,000 acre lake, I said, and then about a 24,000 acre watershed, and about 70% cultivated agriculture. So we had some real challenges here, but the group that was at the Conservancy are science-based people. They understood the need for science to help, number one, assess this system, to better understand how to move forward to take either protection or restoration initiatives. So I'm not going to go into a great deal of the data that we have for the lakes that I am going to share with you. This is going to be a very sort of high-level talk, but I can tell you we have lots of data. Our gauge stations are very similar to what was explained here earlier, where we measure stream discharge. We have a rain gauge, air and water temperature, and then ISCO samplers that, again, you're using here. And we do a little bit different approach. We take a time-based approach. We kind of break the year up into an agronomic calendar. Since we're in an agricultural part of the world, we see April through May as the real critical part of the year, because that's when the soil is most vulnerable. A lot of herbicides, other pesticides applied. Planting takes place at that time, and the soil is most vulnerable. So 6 samples a day, April through June, weekly samples the rest of the months, and monthly lake vertical profiles. We look at, again, the parameters we're measuring are essentially the same that you're going to be doing here, with a focus on phosphorus. So this is I kind of picked the worst of the worst. This is one of our drone pictures. of a field with a tributary leading to Lake Wawasee. And the folks around Lake Wawasee have spent a fair amount of money doing sort of in-channel conservation practices, little sediment basins and stream bank stabilization. And I told them one day, I said, those are all wonderful projects, but I said, you know which is the best sediment nutrient trap in this system? And they said, what's that? I said, Lake Wawasee. And they about fell out of their chairs. They weren't too happy about that. So this is a continuous seed corn field. I don't know, how many of you are familiar with, so where somebody grows seed corn, and it's corn every year and it's irrigated and was a big problem. So in the watershed, there's also this sub-watershed, which is called Turkey Creek. It's about 10,000 acres. Again, about 70% cultivated agriculture, but it also has a 100-acre wetland that the stream goes through before it reaches the lake. And this year we saw, and we have a gauge station on this stream, and you might just look at, this is the wetland, and what's that? Nope, I wasn't ready yet. There he goes, changing my slides. Huh. What are we going to do with them? No, that's all right. So this is Turkey Creek. I'm just messing with you. And we always talked about this wetland. It's a beautiful wetland, but it just has a channel going through it. So we don't have laminar flow. And it doesn't really stop the phosphorus from moving through. We say phosphorus is a stubborn molecule. You can't, as you know, there's no real atmospheric form for it. And so it just continually moves downstream until it enters into the lake. In fact, we see this is the highest input into Lake Wawasee, is an area that they thought was most protected from phosphorus and sediment getting into the lake. But it turns out, and we have, and you probably all know this, that wetlands don't equal phosphorus sequestration. And so this is the plume coming out into the lake, out of this Turkey Creek wetland, wetland that you can see. And it's a huge source of sediment and phosphorus. We know from our research that 75 to 80% of the phosphorus and nitrogen and sediment load coming into Lake Wawasee happens in about 20% of the year. And you can guess what 3 months that 20% is without me telling you. Yeah. And so here are some of the bottles. I think, Dale, you showed a couple bottles from an ISCO sampler. And these are taken every 4 hours. And you can see how quickly the water quality changes. And so if you just kind of keep your eye on that star bottle in the circle, in the clear bottle, that suspended sediment was 2 milligrams per liter if, and this is obviously if because there's time intervals here, that would be about 85 pounds of sediment in 24 hours. In the turbid bottle, the suspended sediment was 232 milligrams per liter and or 18,777 pounds. I'm telling you, there's enough sediment going into Lake Wawasee that if you went and tried to get a permit from the Corps of Engineers, they'd laugh at you. But we allow sediment and nutrients to indiscriminately flow from the landscape into our lakes and without any responsibility from where it's coming from. Look at the phosphorus here, the clear bottle. How you like that number? There's no 2 zeros in front of that. That's 0.24 milligrams per liter, or about 6.7 pounds in 24 hours. And look at the turbid bottle, 0.72, 142 pounds of phosphorus in one rain event. And so we have a pretty good handle on these external loads going into the lake, as well as with our in-lake sampling. All right, now, Tom, after I gave you such a hard time, oh, I got it. The other thing that I want to bring your attention to is development. And I don't know how much of this is an issue here, but in Indiana, at Lake Wawasee, you can see this area. We took this picture with our drone. Come on. right here, 5 acres, right next to the lake, nuked. Literally, the developer went in, cleared every piece of vegetation off of that 5 acres and started building houses. And guess what? It was legal. There are no ordinance in place in the county. The state had no jurisdiction, well, they had jurisdiction, but the rules were so spineless, I'll call it, spineless as a jellyfish, that they couldn't do anything to stop it. Unfortunately, this picture doesn't show up well. This is after about a 10-minute intense rain. I don't remember the date. And you can see this sediment plume coming out into the lake. It's unspeakably sad that even development is not held to be a little more accountable for the nutrients and sediment that run into that lake. So I don't know what you have here around Torch Lake in terms of kind of accounting for that. And maybe it's not an issue, but if it's even a possibility, I strongly encourage you to put it on your radar because it can be very problematic.
Especially Central Lake, where they have no zoning rules. See, part of our situation, Gary, is there's 7 townships.
Yep.
3 counties.
Yep.
That the lake touches.
Yep.
Okay?
Yep.
And even though Antrim County is the dominant county, it really goes down to the individual townships.
Yep.
And we have far extremes, like you're in Torch Lake Township, and Torch Lake and Milton are probably about the most responsible in addressing some of the issues.
Mhm.
But then across the lake, Central Lake, they have no zoning rules whatsoever. And it's unfortunate that they can overwhelmingly influence the quality of the lake because of their lack of ordinances. And it's a very, very tough argument trying to get them to accept some responsibility for the overall lake law. But we're working.
And unfortunately, oh, go ahead.
Fred, where did you say South? There's a lot of places that every time we get an inch of rain, there's noticeable plumes. Clam Lake, one in particular, of all the roadside ditches that, they drain. And it's not as simple as ordinances because in one case, one of the worst ones out there is due to just the natural topography. The runoff is cutting through the land. And it should be clear water coming down. It shouldn't be.
Right.
Son.
I don't have much further. I just want this talk because I keep speaking as if we may not have these problems here. Some of these pictures, that picture you showed of the lake, we had that when we had the washout for the culvert. That Torch Lake was as brown as that, from the middle to the east, all the way down the hall. So we do get that.
Yeah, we do see that.
I have to be honest, this is the first time I've ever seen Torch Lake. And we walked, I will tell you this too, I can tell you this little side story, is okay. And we decided we'll walk out to the public boat ramp not far from here. And I was excited to see the lake. Man, I was running to get out on there because I wanted to take a picture of that clear water. And I heard Melinda go like that. I thought, oh my gosh, what'd she do? She found a mushroom by a tree. She was so excited. I didn't care about mushrooms. They gave me a stomachache. So that's my first experience at Torch Lake. But these are things though, and I'm going to say this with all sensitivity, the phosphorus in sediment doesn't care where it's coming from. The lake doesn't care where it's coming from. And it will have a response at some point. You guys are fortunate. You have a huge buffering capacity here that the lakes that I see don't have. But we clearly understand now, what is this tipping point? When does this lake reach the tipping point of moving from this, I'll use mesotrophic to eutrophic conditions? We kind of understand that. And then I always say, nature will tell you when you get it right. So this is my second example. This is a small prototype lake for us. In Indiana, we have a program in the DNR called Lake and River Enhancement. Great program. I love it because they will cost share with lake associations 80% of the cost of doing a diagnostic study. But in their proposals, they only require 2 water samples. And then they use those two water samples, a high flow and a low flow. And then they say, well, then we can determine what the loads are going into the lake. I said, no, that's not correct. And they're great people. I work with them, and I'm not putting them down in any way. And so this is a pilot study that we used, and they were fortunate. They were good enough to come along with us. And they said, all right, we'll fund your approach using gauge stations, and let us see a report, and let's see how much we might be missing. So this, by the way, these are some of the most southern glacial lakes anywhere in the United States. And we know we're on the edge. And you talked about, we've talked about lakes going through successional change, and ours certainly are doing that. So this is just a 245-acre lake, maximum depth 30 feet, but look at the agriculture, 86%. And so this shows the position of our gauge stations. Two main inlets here, and here we had gauges, and then our sample sites in the lake, and then at the lake outflow. On July 13th in 23, I went to the lake we were just there, and we saw this huge blue-green algae bloom. Now, I don't know how many of you have ever experienced something like this. This was the first time for me, and I'm not showing you this to scare you, but this bloom was so bad that we couldn't stay on the edge of the lake. Our noses were burning, our eyes were burning, and if you look at this house, you see that roofing material? There were people roofing that house, they had to get off. They couldn't stay on the roof. And what was most frightening was, if you look in this picture, there's two kids right here. They were on this pier and they were ready to get in the water to go swimming. And their parents were going to let them. They didn't realize what was going on. So we told them about it, and they were smart enough to keep those kids out of the water. So this lake's in real trouble. So Lake Tahoe and Torch Lake, you see, this should make you feel very, very good about your lake. And so we know now through our study, we know what the condition of that lake is. We know the external loads. We know the internal loading. We've done sediment samples looking at the legacy phosphorus in the sediment, and we understand how much legacy phosphorus is being stored in the lake and contributing to the internal loading. The next big step, though, is taking that data and making a change. That's the really hard part. The easy part of every one of our jobs in here is going out and boiling the world to numbers. That's the easy part. We can come up with all kinds of questions, and we can collect the data, but using it to make a change is the hard part. Indiana happens to be the southern extent of this fish. You guys recognize this? The Cisco, yep, right, you have them here. And we consider it a sentinel species. It is, in my opinion, the best indicator of water quality in our lakes in Indiana. And you can see that in 1955, in a paper by David Fry, he did a survey. There were 45 lakes with Cisco that were reproducing and having a happy life. And by 2017, we're down to 7, less than 7, and there's 2 on the brink. And Cisco are now listed as state threatened, and most likely will be considered state endangered in the coming years if we can't turn it. We are quite confident that we know that phosphorus is the culprit to the demise of Cisco. We could talk a long time about that, which I don't have time because I'm probably running over now. So Clear Lake happens to be, which is up right in the corner of northeast Indiana, right up by Michigan and Ohio, one of the deeper lakes in the state, about 100 feet deep in 3 spots. And it had Cisco in 2016. So this is one of the most recent lakes to lose that species of fish. And we're working there, and our goal is to return the water quality back to some condition to reintroduce Cisco. For us, that's kind of a holy grail of success, if we can show that kind of change. So here's Clear Lake, April 19th, 2024. They just spent a bunch of money building a fairly sizable retention basin in this watershed. And we looked at what they built and we said, well, that's nice, and it might slow the water down a little bit, but we didn't think it would really have much of an effect. And sure enough, the first big rain, you can see the size of that sediment plume coming in. And when you see sediment, you know phosphorus is not going to be far behind, and nitrogen as well. So here's 2 bottles, again from our sampler, 4 hours apart. And here you can see the numbers. Phosphorus, 0.09, and Clear Lake tends to have a little lower phosphorus levels than Bruce Lake. And but when you go to that turbid bottle, look at that, 0.6 milligrams per liter, 586 pounds. These are huge numbers. Same way with the sediment, 44 milligrams per liter, and then it jumped up to 586. This is the first step in trying to answer the questions of what is the biggest challenge ahead of the lake. So, as I mentioned to you, we've included sediment sampling to look at legacy phosphorus just in the last year in our projects. And so in Clear Lake, we try to stratify our sample, well, we do, based on water depth. And most of the, well, every sediment sample we've taken from our lakes, it sort of looks like black mayonnaise. I was on a call with the Watershed or the Everglades Foundation, and they were telling me during that Zoom meeting that Lake Okeechobee has 50,000 metric tons of phosphorus tied up in the sediment, if you can imagine. So that made me feel pretty good because we don't have near that much. So this is just a brief glimpse of some of that data and why I think it's important. The blue bar represents the total phosphorus. These are sites on the x-axis, and this is milligrams per kilogram dry weight of the sediment on the y-axis. And so the blue bar represents the total phosphorus, but the portion of this that we're interested in is this bioavailable phosphorus. And we had the lab do a fractionation of this sediment, so we understood in that bioavailable fraction, what is it, what forms is it in, so we have a pretty good idea. And now we know by site where the most of the phosphorus is located. And when you look at, here's the average by depth category. Just when you thought there wouldn't be any graphs, didn't you? So here's the average concentration, phosphorus, milligrams of phosphorus per kilogram of dry weight, depth interval, 0 to 35, 34.99. And then you can see that much of the phosphorus is in this mid-depth, and in the deepest part of the lake is where it's being trapped. And so this is phosphorus that's being resuspended during spring and fall overturn, and represents anywhere from 45 to 75% of the phosphorus load comes from the internal loading. Oops. So, Torch Lake. As I looked through the program and everything, I thought, good for you guys. And thanks for everybody that's come out to help collaborate on this project. What a wonderful, wonderful mission you have, and you're doing a great job. And Tom asked me to throw in a little something, about, hang on a minute, about precipitation chemistry. And my mind immediately went to Gene Likens. You probably have heard of Gene Likens, maybe some of you. Yes, maybe, no, a few of you. So it turns out Gene Likens described acid rain in North America. He started the longest research and still running research on precipitation chemistry in the country, started in 1963. And he says, and this is a quote out of a book that he wrote, that long-term research and monitoring must be driven by questions, same things we all wrestle with, and follow an adaptive monitoring approach in which development of conceptual models, questions, data collection and analysis, and data interpretation are linked in an iterative process. In other words, how long should you do Torch Lake? 3 years is a very short time. We started out at Lake Wallasif with a 3-year project. When they got to the end of the 3rd year, they said, we have so many more questions, they extended it out 2 more years. And so we went 5 years, we just finished our 5th year, and that's still not long enough, but well, you understand why it's important. And one of the things that Gene was able to do was to develop stable funding to keep a project going since 1963, you can imagine. And so this took place at the Hubbard Brook Experimental Forest in New Hampshire. If you ever get a chance to visit there, I strongly encourage you to go. He founded an institution called the Carey Institute of Ecosystem Studies. Great place to website, visit it, see the kind of research that's still going on there. And I will tell you that Gene Likens is an Indiana guy and went to college in Manchester, Little Manchester College in North Central Indiana, and changed the world really, because through his work, and this is in an article, and I brought along a copy of it, in Atmospheric Environment in 2021, and Dr. Likens is about 91 or 2. He just finished another textbook and still writing. He's an incredible guy. But look at this data, precipitation data. Down, down, down. Guess what that's from? It's from his research in precipitation chemistry that affected federal legislation and the Clean Air Act. And he got a result. This is the missing link, like whoever was pushing the rock up, I can't remember their name, up the mountain and back down again. He was able to get to this point where he really made a difference. And again, you can see the dry constituents here, everything down. How does it affect water chemistry in lakes? I don't think we know for sure, but it's certainly worth keeping our eye on the ball in terms of these other large-scale changes that are taking place. So I also thought when I was doing this, I thought about this Big Yellow Taxi by Joni Mitchell, and I think about this a lot. From time to time when we're working on a lake, you know, we just don't know till it's gone. And we set at a pivotal point as a generation to institute a legacy project, whether it's Torch Lake or trying to fix a mess of a lake in Indiana, whatever it is, you know, we need more people like ourselves to help raise awareness about how the world works. And so I love fishing. We support summer interns through our business in the summer, and we get a lot of undergraduate research. We also support a master's student from Central Michigan University. We try to help young people. On the business side, it's a terrible idea, but it's something we want to give back. So these are a couple of research technicians with their fish, and that's my fish. Anybody need a fireball?
I'll take a fireball.
Hey, you know they don't make these anymore?
No, I didn't know that.
They just quit making them.
Oh, he's a red number.
Need a fireball? That was a good throw. There you go.
Oh, wake you up.
So this is my one text thread that's actually business related. 54. My family and then the senior moms. Oh, I should have gotten this.
What? I can't hear you. You want a break? We have one more presentation, but you want to take a break? Okay, we'll take a break. Let's take a 10-minute break. We have one more presentation, then we're going to go to the interactive Q&A. We did not show the DNR presentation, but we can do it for those that want to see it. Okay? a chance to get his presentation in. I think we got just about everybody back in the room. I don't see anybody in the hallway. Mark Rowe comes to us. It was very, very special help when we realized that this mussel invasion happening at Torch Lake was becoming more and more of a factor. We looked very hard for an expert that could come and help give us some insight as to how to understand the impact of this invasion in our lake. And Mark was kind enough to accept the challenge of coming and giving us a presentation. This is his bio. He's got a very colorful career, and he's still a young man by my standards. All right. So we're excited to have him here today and want to welcome and thank him. You can start your presentation. I'll get on the computer in just a second.
Well, I appreciate the opportunity to talk with you all today. I enjoyed Jerry's presentation. It was very entertaining. I don't know if I can live up to the standard, but hopefully you can all stay awake for one more. So I could give a couple disclaimers to start out with. One is that everything I know about Torch Lake I learned today, and it's been very enlightening. I appreciate it. It's always fun to learn about different lakes. The other disclaimer is that I'm a modeler, so I work with the data and crunch the numbers. We do have other people in our lab who, like our benthic ecologist, Ashley Elgin, who leads some of the mussel survey efforts and experiments with mussels and so forth. So she'd be a good one to hear from as well one of these times. But so yeah, I pulled together this presentation based on previously published information, some of which I contributed to, some of which is from others, but just kind of a roundup of information on impacts of Dreissena mussels on invaded lakes, and not specifically related to Torch Lake, but hopefully it could provide some food for thought.
I don't think that's going to work. I'll do it here.
Okay, go ahead.
What's happening? It worked yesterday. Here we go. First one.
Put this on the blue survey.
It's not PowerPoint.
Well, anyway, it was meant to be a PowerPoint presentation.
It did work yesterday.
Yeah.
Sorry?
Yeah, it is meant to be a PowerPoint presentation, but yeah, it looks like it's on a browser. Was the file downloaded? Yeah, that's in Google Slides. Okay. Hopefully it'll work.
There we go. Sorry.
Okay.
I had it set up yesterday, but it wasn't recorded.
Okay, no problem. So yeah, here's the mug shot again of the usual suspects that you saw before. And they're kind of cute as individuals, but you can go to the next slide. When they're coating the entire bottom of a lake, like in this picture from Lake Michigan, then they can have some impacts. And this one you can see these mussels, they call the deep water morph of the quagga mussels. Is this a pointer? Okay, yeah. So you can see they have the long siphons extended here for their filter feeding. And they've kind of adapted to do that in this deep water condition, because when they're in a continuous bed like this, they deplete the particles from the layer over the bottom. So they have to like extend up to get into the fresh particles above the mussel bed. Go ahead for the next slide. So this is the Ponar dredge that's used to generate a lot of the monitoring data for the mussel surveys, like the survey that was done on Torch Lake recently. So our lab does some of this monitoring in southern Lake Michigan, and then also participates with multiple agencies in the Cooperative Science and Monitoring Initiative funded funded by EPA that goes through and does a full lake survey in each of the 5 lakes on a 5-year cycle. Go ahead. So this is looking at this paper was looking at the kind of long-term course of invasion in invaded lakes. And so this is kind of showing over decades, several decades after invasion, in a shallow lake like Western Lake Erie, quagga mussels and zebra mussels can coexist. Whereas in deeper lakes, what happens is zebra mussels may get established first because they can kind of spread and get established more quickly. But then over a few decades of invasion, the quagga mussels can outcompete the zebra mussels in deeper lakes. So when we're looking at impacts on deep lakes, we're mostly talking about quagga mussels. And
So
then,
I have a question. Is Torch Lake considered in this vernacular a deep lake?
yeah, I would consider it a deep lake because it's deep enough to stratify during the summer. So a lot of the mussels are going to be in the hypolimnion, cut off by the thermocline from the surface layer. So like Western Lake Erie, it's not deep enough to form a thermocline during the summer. And in shallower areas like that, mortality rates are a lot higher. So it's kind of like resetting the invasion from time to time. So this one's supposed to be a video. I don't know if that's going to play, but yeah, well, I mean, it's kind of a cool video from Sasha Karatayev and others have explored using these benthic sleds with video GoPro cameras on them to show the mussel distributions as a kind of complement to the traditional PONAR surveys to be able to cover a lot more territory. But yeah, it was set to play automatically. It may be the software that's showing it.
Yeah,
It's
I
a
think-
PowerPoint.
I didn't know there was a video when I tried to play it yesterday. I should have called Joe, sorry.
Yeah, okay. No problem. Yeah, so anyway, that was a sandy substrate in like less than 30-meter area in Lake Michigan where the mussels get periodically disrupted by wave action, so they aren't able to form continuous beds. So this would be a shallow area with a hard substrate where the mussels can attach to the rocks. And then, since the light reaches the bottom in this area, they can also support dense beds of benthic algae. Go ahead. So this is another video, but you can kind of see that in this intermediate depth region, 30 to 100 meters, the mussels can form kind of a continuous bed. So in deep lakes, this is kind of the depth range where they would form the greatest densities. And these depths range in the Great Lakes would be shifted to a little bit shallower depth, probably in a lake like Torch Lake, because it's a little bit more sheltered, probably has a little bit shallower thermocline and less maximum wave action than the Great Lakes would.
Are those dead or alive?
Those are alive. Next slide. And so then this would be from like 100-meter depth range in Lake Michigan. So here you've got like individuals or a couple of mussels widely spaced apart because down here there's limited food supply, and so it can't support such dense assemblages.
Are they affected by the loss of sunlight at that depth?
I mean, I don't think the sunlight directs
I mean,
them.
as far
Yeah,
as
the sunlight is
Something
affecting
for them to feed on.
their food supply. That's right, because the phytoplankton are growing in the sunlit layer on the surface, and then once it's stratified, the ones down here are kind of cut off from that during the summer stratified season. Yeah, go ahead. So then, this is what it looks like when we look at the lake-wide survey data. So in this, the little symbols are showing, the stations of the survey. Obviously, the PONAR survey. And so then we applied a geostatistical Kriging type model to try to interpolate and estimate what the lake-wide biomass distribution would look like. And then because the surveys were conducted every 5 years, it captured the course of the invasion of Lake Michigan. So in 94, 95, there was, a few zebra mussels around. And then the quagga mussels started coming in the north around 2000. And by 2005, they had become established in, dense beds in the mid-depth region all around the lake. And then even more dense in 2010 And in 2010, it looks pretty similar to, or 2015 looks pretty similar to 2010, except just a little bit more in the deepest areas. So yeah, we're like, yeah, about 10 years was long enough to kind of fully invade the lake.
So do you think Torch Lake today is sort of like where they were in 2000?
Well, I don't know. I mean, I just had briefly looked at the results of that survey, but it seemed like they were pretty well established.
Because it's scary to think of what could happen between 2000 and 2010 there, what we have to look forward to in 10 years.
Well, I don't know where you are on the trajectory here as far as, yeah. But yeah, over 10 years is long enough.
Mark, that last data point is 14 years old. Is there contemporary data point?
Yeah, I mean, we've got a map like this for 2015 and it looks similar to 2010, you know, slight changes.
So it's like it's leveled out.
Yeah, I think for the most part. I mean, there are still changes. There can be changes due to like predation, you know, round gobies becoming established, and then demographic effects. There can be kind of boom bust cycles and things like that. What's that?
The whole lake isn't solid yellow now.
No, I mean, I don't think it's going to be uniform all over the lake because of the different depth zones. Go ahead. So yeah, the mussels are filter feeders on phytoplankton. This is Hank Vanderplug, my former supervisor, getting ready to take the video. There's some mussels in there. The video that'll show on the next slide, although it probably won't play. But yeah, so he was measuring clearance rates of quagga mussels and also selective feeding. And so these are the kind of data that we need to put into models to be able to model their impacts on lakes. This is showing the volume of water they can clear per milligram mussel biomass per hour, and showing the temperature dependence. You know, they feed more actively at warmer temperatures, but they're still active at low temperatures, and they don't need as much food at colder temperatures. And then it also depends on the quality of the food as far as how vigorously they feed. So
Mark,
for
if we
the-
want to model that in Torch, do you think that those numbers with the same graphs would apply? Since they're the same species, or do you think is that very specific?
I would guess so, yeah. Yeah, I mean, here he was feeding them in the lab off of, you know, some fresh phytoplankton. Go ahead for the next.
You think that we eventually could get to that point?
Well, you heard that.
We just use that directly?
Yeah, that's what I just.
Yeah, go for the next slide.
Well, but what does high quality food mean? I mean, is that basically the phytoplankton?
What was the clearance rate there?
See, there's
The milligrams is a measure of
The muscle biomass,
muscle density?
or the muscle biomass,
How did you
milligrams.
establish that? Was that from video and then lab work? Or how do you?
It's done in the lab. It's done in the lab. He'd put them in either a beaker or a 5-gallon bucket, put a certain number of mussels in there, measure the phytoplankton before and after, and then harvest the mussels, measure the dry weight biomass.
For a lake, an actual lake, how do you sample it to get an idea how many milligrams of mussels you have?
The Ponar dredge.
Okay. That's
Yeah.
brutal.
So yeah, this is meant to be a video too, but it's showing the fluffy stuff here are Microcystis colonies. So those are colonial cyanobacteria, like the kind that cause the Lake Erie harmful algal bloom. And so then there's a zebra mussel here with the siphons showing, and it's kind of sucking in phytoplankton. And then the cool part, you can watch this one on YouTube if you want to, but so that it actually spits out the cyanobacterial colonies. So yeah, they do feed selectively. So this selective feeding on like avoiding the colonial cyanobacteria can actually promote harmful algal blooms by consuming the competing phytoplankton. But they can also sort out microscopic plankton on their gills and then reject the ones they don't want to eat into the pseudofeces. So yeah, our lab's done a lot of experiments on selective feeding. So that was one of Trish's questions, like could they change the phytoplankton community composition? And yeah, they can. Next one.
I'm gonna have to try to understand that.
I thought because they killed algae that they would create. Okay. So go ahead. Yeah, so this is a paper by Ashley Elgin, I mentioned from our lab. Has done experiments where she puts caged mussels in different depth ranges in lakes and measures their growth. So this is kind of explaining why we see, different densities of mussels in different depth ranges. So this is from Lake Ontario. So like in the 15-meter depth range, they grew a lot. At 45 meters, they grew intermediate amount. And at 90 meters, they grew very little. And then these data came from the moorings where she had the caged mussels. So the shallow ones, they experience warmer temperatures and higher food abundance. And then as you go deeper, temperatures are colder, there's less food, so they grow more slowly. And then the other part of this is that factors other than growth are controlling abundance in the shallow zones. So in the lake, we see kind of maximum densities in this intermediate zone. So even though growth rates are higher in the shallower area, the mortality rates are higher too. So the kind of steady state population tends to be greatest in these kind of intermediate depth range.
We're in trouble. What contributes to mortality in shallower?
Physical disturbances like wave action, possibly predation by round gobies, in some areas like Western Lake Erie, potentially episodic hypoxia.
Does UV inhibition affect it at all?
I'm not sure about that. I guess another thing would be ice in shallow areas could disturb them. So this is a paper where we kind of reviewed modeling needs for this type of interaction here, where we got mussels in shallow areas where the light reaches the bottom, and then they can support growth of attached benthic algae because the mussels are feeding on ceston or phytoplankton, and then they're excreting dissolved phosphorus right into the benthic algae bed. And then the other thing is that they're increasing the light penetration as they remove particles from the water. So then that increases the area of the bottom that can support benthic algae. And then when they're feeding on the edge of a deep lake, so they're like consuming the particulate matter here, and then by turbulent dispersion, the particulate matter from offshore moves in and then gets diverted to the bottom. So then when they're on the edge of a deep lake, they can kind of be like sucking in material from offshore. Go ahead.
Okay.
So this one was interesting. So we were able to actually show that spatial patterns of chlorophyll concentration detected by satellite imagery in Lake Michigan could be explained by the mussel abundances. So this would be satellite imagery showing surface chlorophyll concentration in April. So April is the traditional time of the spring phytoplankton bloom in Lake Michigan. At that time, the lake's isothermal well mixed from top to bottom. And so the filter feeders on the bottom can have access to phytoplankton throughout the water column and impact the surface concentrations of chlorophyll. And so then you can see like before the invasion, you get this kind of donut shaped spring phytoplankton bloom in the southern basin that's based on the bathymetry there. And then in 2005, when they're kind of halfway established, the chlorophyll concentrations are greatly reduced and you start to see kind of this band of low chlorophyll there. And then in 2010, when they're even more established, then you can see these areas where the chlorophyll is totally depleted. You can actually see from satellite imagery. So that's kind of cool. And that was another question that Trish asked, like, could the mussels be responsible for, depleting the phytoplankton concentrations at certain times? And well, they can, and you'd be able to do a calculation like this, fraction of the water column cleared per day with the data you have from the benthic survey. So this is calculated using the bathymetry, the biomass of the mussels in different depth zones, and the filtration rate data that we showed in the previous slide. So yeah, you could do this. And then like, yep.
So, because that was going to be. Thank you. This is almost like the slide I want to ask this question. You know, so without doing full-blown modeling, which may take us, you know, another year and a half to get all the data for, let alone develop the model and fine-tune and calibrate it, you know, with somebody of your experience and having spent a full day on Torch, couldn't you, and I think you're saying this, just back of the envelope, you know, couple scenarios of quagga mussel density and aerial extent, say whether or not they're likely to have an effect when you couple that with just the phosphorus balance and water balance. It's like first order perturbation theory in some kind of mathematical model, you know?
Right,
Like,
yeah, you can do this calculation right here because you've got your mussel survey data. You've got the bathymetry of your lake.
Right.
And we've got the clearance rates from the previous slide. So you can calculate this fraction of the water column cleared per day. Now this would be kind of in a spring isothermal well mixed time
Right.
of year.
but again, it'd be like,
then-
I don't want to oversimplify it, but it'd be some hand calculations versus at best, maybe a little spreadsheet, but it wouldn't have to be a full-blown model for you to say, yep, this is important or this is not, right?
Right, yeah, you can do this one kind
Right.
of back of the envelope. And then like the doubling time growth rate during the spring bloom for the phytoplanktons like about 10 days. So then when this is greater than about 0.1, then, you know, they're essentially clearing out the water column faster than the phytoplankton can grow. So then that's like an indication that they could have a substantial impact on the phytoplankton abundance. Get after. What do you mean by get after this? Yeah, I haven't done much with that, but there is people doing research on that. There's a group called Invasive Mussel Collaborative that kind of does control type research. And Harvey Bootsma over at EW Milwaukee has worked on that some as well. So there's information out there on, you know, different strategies people have tried.
Okay, ready?
Yeah, so to dig deeper, we applied this Lake Michigan biophysical model. So the R Lab applies numerical ocean models to the Great Lakes. So we had this model that can predict currents and vertical mixing that had a lot of spatial detail. Like the model grid was about 0.5 kilometer resolution along the shorelines and 2 kilometer in the mid-lake. And then we linked that to this representation of a phosphorus limited lower food web with phytoplankton, zooplankton, detritus, and racinated mussels feeding on the phytoplankton, recycling nutrients, and so forth. Go ahead for the next slide. In this one, you can click it one more time. This one's going to have stuff popping up.
Okay.
Yeah, so these two maps are showing two different versions of satellite remote sensing chlorophyll in April of 2010. And then go for the next click. And then these three are model simulations of that same time, April 2010. So this one has the quagga mussels in the model and phosphorus loading coming in through the tributaries. And so, yeah, you can see these chlorophyll depleted areas and kind of the same places you see in the satellite imagery. So that's the model reproduced that phenomenon. So kind of indicating that the mechanisms represented in the model were, you know, what was responsible for that. And then if you click on the next one, so this model scenario, we just turned off the mussels in the model, and then the spring phytoplankton bloom returned. And then one more click. And so then this one, we turned off the tributary phosphorus loading. This is just a 1-year simulation. But so that showed that, you know, the inputs from the rivers can maintain some productivity in the nearshore areas, even in the presence of the mussels. Go ahead. And this is from the same paper, same model simulations. This is showing components of the lake-wide phosphorus inventory expressed as the equivalent of concentration as phosphorus. So anyway, so the total here was around 5 micrograms per liter average phosphorus, total phosphorus in the water column prior to the mussel invasion, and then progressively went down to like 4.5, and then a little over 4. And then this black dashed line, that's the amount of phosphorus that's in the living mussel tissue lake-wide. So then, you know, that increases with the invasion. And then here in 2010, the phosphorus in the mussel tissue was enough to account for about 1 microgram per liter of phosphorus lake-wide. And it could kind of almost account for what was lost from the water column.
Is the phosphorus in the mussel tissue leveling off, or is it that the number of mussels are changing so you can't? I mean,
Yeah.
because obviously they keep reproducing, right?
Right, but it kind of builds up to sort of a steady state population at some point.
If I were to try to take those 3 graphs and parallel them to Torch Lake, that would tell me that in our future, as the quagga mussels continue to grow, it's going to have a similar effect where the available phosphorus is going to go down.
Right. Yeah, yeah. Try the next slide and we'll show the same point again. So this is a different paper that used a little bit different type of model that was less spatially resolved, so they were able to run it for a longer time period, but similar concept showing phosphorus in the water column in Lake Michigan declining over the years due to declining loading. But then, you know, in their model, so without mussels, you know, the phosphorus in the water column was around 4, and then with mussels, it was like a little over maybe 3 or something. So showing that decline in phosphorus in the water column, shift of phosphorus to the mussels and the benthos, you know, associated with the mussel invasion. And this one is looking at the phosphorus fluxes. So in the lake before invasion, there's like, you know, gradual settling of phosphorus, phytoplankton from the water column, some recycling at the bottom, you know, kind of low rates. But then as soon as the mussels come in, they're really dominating the cycling of phosphorus in the lake to where the flux of mussel feeding and excretion is, you know, much greater than the rate of phosphorus cycling was before the invasion. So
That's
try the next one. Okay, so this one is the same model I talked about earlier on the, not the last one, but the previous model. So this one we looked at how lake morphometry determines the mussel invasion. So this one we just took an idealized circular lake and assigned different bathymetry. So this is kind of shallow lake bathymetry, like Western Lake Erie. This is a deeper lake that has like smaller hypolimnion. So that's kind of like eastern basin of Lake Erie. And then this shape of lake, maybe more like Lake Michigan, where it has a large volume in the hypolimnion. And so then this figure is showing the total Dreissena biomass in different depth zones and lake-wide, and then the chlorophyll concentration, or it's the reduction in chlorophyll concentration. Okay, so in the shallow lake, like Western Lake Erie, you know, you don't really get a huge mussel biomass because they quickly deplete all their food supply because they have access to the total water column all the time, so they just clear it out. And then in a deep lake, then you can get, you know, high mussel biomass in these intermediate depth zones because they don't have access to the total water column all the time because it's stratified for much of the summer. And then, you know, they're kind of on the edge and the phytoplankton can grow in the middle. So then in a large lake, you know, you tend to get these high biomass in the intermediate depth zones and then low in the deep zones where there's not much food. But the overall lake-wide, you can support much bigger biomass than you could in the shallow lake. It's because they're cut off from depleting the entire food supply. Go ahead. Yeah, so what are the implications for the upper trophic levels and fish? So this paper here by Chuck Medengian and others, this was based on a review of observational data, so this was not a model, but looking at what happened to Lake Michigan after the invasion at different levels of the food web. So yeah, they noted 35% decline in offshore primary production. There was a decline in prey fish abundance, which was already well on its way before the invasion, but they figured the invasion of mussels didn't really help with that. But a surprising outcome, I guess, was that the salmon, trout, lake whitefish abundance remained relatively stable. So I guess everything's not necessarily doom and gloom, but they thought that was a surprising outcome. But I guess the food web can be resilient in terms of coming up with different pathways and unanticipated outcomes in complex food webs. Not to say that there aren't impacts, because there are certainly winners and losers before and after invasion, but you know, it's not necessarily a complete disaster for a lake. You talking about the mussels?
Yeah.
Right, yeah, I think they probably have, and Lake Michigan reached close to a steady state population. Well, that's possible. You know, there can be, like I was saying, kind of demographic effects of boom and bust, like if they are established so densely that young ones can't settle anymore, and then the old ones eventually get old and die. Or, you know, new predators can come in, like round gobies getting established or something like that, or a disease, or who knows, you know, what can happen. That's about it. So yeah, that's just a summary here. So impacts on invaded lakes. So increased water clarity, that can be keep an eye on in Torch Lake, because, you know, there's room for it to become more clear, and that would increase the bottom area that could grow benthic algae. Reduced water column productivity, increased benthic algae, potential promotion of cyanobacteria, transfer of total phosphorus to mussel biomass and sediment and the benthos, and then dense mussel populations in the depth range around large lakes, and potential unanticipated outcomes for fish and complex food webs. So
Next one, or
that's all I have. That's it for
Okay,
me.
can we ask a question?
Yeah.
All right.
So
If I wanted to take away from this discussion relative to everything you heard today and what we've been doing for the last 3 years, one of our objectives, and you heard from Dale and you heard from Jan, we've tried to quantify and qualify our data for the trend line of phosphorus available. And we look at this data, we question this data, we take more data. But if we're assuming a steady state condition affecting the available phosphorus and try to conclude a trend line, it's not valid, because what this tells us is that the introduction and growth of the mussels in the lake are affecting the available phosphorus. So our presumption that a development of a trend line is not valid, right? I mean, what do you mean? No, it tells you right there. It tells you transfer of total phosphorus to mussel biomass and sediment. So as the mussel population grows up, what you're measuring in the water in phosphorus is going to look like it's less. It's just in a different place.
It is less where we're measuring it. But that's what Jan's saying too. Everybody's is just trying to explain it. All we're saying is that the data isn't good enough to tell us if this is happening. And if it was good enough to do it, we would see a decrease. If this is what's happening, we would see a decrease in the lake.
Okay.
We just don't have the data to support it.
But fortunately, we're taking data now, and we're still at the early end of the quagga mussels.
Well,
So
I don't know. I mean, it'd be interesting to repeat the mussel survey, and, you know.
well, that's the
5
next
years or
talk, is
whatever.
what our plans are for this year.
Right.
And it's a different approach than what the report is that what Three Lakes did, but we are trying to get some kind of handle on it. I just got to go talk to Jeff and get a couple 100,000 from him to finish the work.
Two things. One, if you were to see photographs of the mussel beds, like you had in the videos that we couldn't run, but you saw them, do you have a qualitative feel on what kind of density you're looking at if you looked at a quality photograph? Or does it require a protocol with the with the PONAR to develop some kind of a representative density for the lake? How would you go about establishing that? If we wanted to get a density number for Torch Lake, how would we go about that?
Well, I mean, the PONAR methods are pretty well established. The video survey methods that Sasha Karatayev and others developed, they did do some quantitative analysis to try to, get quantitative values from those types of video surveys. So they did have some methods to do that.
Okay. Also, we took the time, we have all our mussels, all 1,500. That's a small sample, but we had 1,500 mussels. Some of those were zebra, but it was a small amount of it. They were all measured, and we just, for expediency, put them in bins. But in talking with Harvey Bootsma, if we had actually measured or we could go back and do it, their actual length, their size, that we could find out from that what stage of the infestation we're in. Have you done anything like that? The size and then determining where you are in the infestation stage?
Yeah, my colleague Ashley Elgin at our lab, she's done a lot of that in terms of establishing length weight regressions. And it does vary, somewhat depending on the condition of the mussels. If they're fat and happy, they're going to be heavier for a certain length. And if they're starved, they're going to be kind of skinny.
So it would be a little bit influenced by the lake because
Yeah.
the food source might be different a little bit
But-
from one lake to the other.
But yeah, if you measured the lengths, you could use some of the published length weight regressions to get an estimate of the biomass. And of course you could make your own if you scrape out the tissue and dry it and weigh it.
But we'd need the weight as well?
If you want to get the biomass, which is a better indicator
Okay.
of the total amount.
We're just contemplating whether we want to go through our jars and do any more than we've already done.
Would the weight still be valid? Just like
Well, they were put in preservative, so
Yeah, maybe you can talk to my colleague Ashley Elgin. She'd probably be happy to talk to you about it.
okay, thanks.
Mark, we've been talking about trying to do something like this in Torch Lake, the modeling you're doing. Given how narrow the lake is, do you think you could use a 1D model to drive it? Or do you still need the 3D to get it to onshore, offshore effects?
I mean, you could certainly give it a try with a 1D model, for starters.
Okay. Because it's just mostly clearance rate, and then instead of having bins, you just have layers. So that,
Yeah.
yeah. It's sort of like what Dan was saying was sort of, well, you could try it before you get into something too complicated.
You could also look at that Lee et al. Model that was published. That was more of a box type model that could maybe be applied without too much difficulty.
Okay. Any more questions? Yep. Okay. You ready?
Okay. Save the best for last.
Yeah, I've read that that gobies, the invasive goby feed on the quaggas, but I've also read that perch are feeding on them. Can you comment on that? Is that true?
I don't know about perch. I mean, I definitely heard about gobies eating mussels.
Yeah, I've only heard that gobies did it. Okay. Any more? Oh, more questions?
Mark, everything we looked at in terms of onshore, offshore were very close. Would that say that either it's a 1D system or I'm just wondering if because of its width and everything else that they're having the full effect already? That's, sort of how long they've been around and what they're doing. We don't see everything we've looked at is pretty uniform across. So
well,
I'm just wondering if that says it's 1D just because it already, I'm just wondering if we have to simulate nearshore and offshore differently just because everything we're measuring is roughly the same for chlorophyll.
I mean, from what I read of the mussel survey, it seemed like that there were different. It seemed like there were more mussels in kind of the intermediate depth region. But Oh, go ahead.
So not a modeling question, and I think I know the answer, but I got to ask. So Jeff said Tahoe has had boat washes in for, I don't know, 100 years or something like that. Torch Lake, Elk Lake, I don't think there's a boat wash on the whole chain of lakes in, at our place. So if we've got quaggas already, it's not even worth bothering putting in boat washes because we're screwed already, right?
Well, I mean, I guess they're already in there, but you could maybe prevent other lakes from being invaded.
It's too late. Start with something.
Just commenting on Dan's question, are you presuming that quaggas are the last invasive species? I mean, Tahoe just got New Zealand mud snails. If maybe next time I can bring some.
Mark, I have maybe a kindergarten level question. I'm thinking about a mussel 2 inches big, clearing a water column 100 feet deep. How is that accomplished?
Well, they're closer to 1 inch, but there's a lot of them. Yep, just lots of them. Give another one.
Mark, you mentioned Harvey's work. Was part of that developing a chemical to kill them? Are they working on something?
There's companies that have developed, I don't know if it's exactly a chemical, I think it's a bacteria spore or something, is one thing. I know Harvey's done some work with like putting a tarp down to kill them and see if they come back. And in some cases, I guess they haven't recolonized areas like that have been cleared. So I don't know. I mean, there's a lot of research on it that I'm not that familiar with, but there is research to draw on control attempts.
No, okay.
I didn't hear the last question, but I did hear the answer to it. We don't have quaggas, we have Asian clams, and we did a lot of work looking at putting impervious barriers on them, and it worked really well. It's like 98% effectiveness, but at the end of the day, nobody could afford to put them over a large enough area. So.
Dan, I really thought you were going to ask this question. Okay, now that you saw that the mussels are out here. All the talks up before didn't worry about mussels really. They're really worried about golden brown algae. So the real question is do you think that the mussels out here led to the golden brown algae, or did they reduce the phosphorus concentrations like Jan's theory to leave something else drive the change? So do you think that the mussels were ultimately a possible real big cause of what they're seeing out here with golden brown algae?
Well, of course, I don't know. I mean, so I'll just lead with that. But I mean, we did see that, you know, you can expect reduced phosphorus concentrations in the water column for invaded lakes. So there's possibly some support for that theory. You know, originally I was thinking about increased light penetration, but it looks like that golden brown algae is in extremely shallow areas. So I don't know if that would be, yeah. But I mean, it could be something to keep an eye on, the light penetration in the lake, because you might expect that to change and there could be some impacts.
I think we've seen that already. If I only threw up that one plot and you saw it get a little bit deeper and it sort of leveled off. So it's definitely, you know, one of the things I was saying, we sort of had this argument about whether total phosphorus has dropped. And all I've said up to now is that there's about 5 different reasons we could think of, like increased calcium carbonate, bringing the phosphorus down would be one reason. Mussels would be another reason. So there's a lot of real reasons why the phosphorus could have dropped. All I've said up till now is that the data don't support anything just because it's so noisy. We didn't have a good lab 15, 20 years ago. If we'd have that, I think we would have seen that the Secchi depth increased. I think we really would have seen the phosphorus drop. Jan argues that we already have seen it. Maybe if you believe the numbers, it has dropped. It's just the question is, do you believe them? So a lot of this stuff comes together with that, and it's just whether, I'm not sure we can find a way to test Jan's theory more than what he's doing already. We'll have to see what that is, that the phosphorus is causing like a species change that's leading to, more of the benthic algae. Because it's obviously, what would have done it would be a shift in species from offshore kinds of things to the benthic. And so ultimately what you're saying with phosphorus, overall mass balance, yeah, it's there, it's just where it is. But if we're only measuring offshore, it'll drop. If we somehow try to do a mass of that and the sediment, oops, he's gone, and the sediment and everything else, but that's tough because that's been accumulating over hundreds and thousands of years. So it's not a simple answer to any of these, and it's probably a combination of all of them to, what triggered it. Could it have been the mussels triggered it? Could it have been acid rain reduction triggering it? It's probably a combination of all of these things, which makes life really difficult.
Yeah, it's
More of a
easy
comment.
to want to blame everything on the quagga mussels, but it's good to step back and think about the other things that are changing, like winter conditions and loss of ice cover is a change.
No longer growing season. There's a lot of things there that.
And then if these whiting events are important, the mussels clearing out the phytoplankton could have some effect on that. So the calcite precipitation events, is that your typical whiting event?
But what did you call it?
Whiting
Mark?
event?
Whiting?
The,
Okay, yeah, I'm with you. Got it.
Precipitation. Any more questions? You got one, Randy?
How quickly are these proliferating in mass groups? How long does that take and how do they reproduce?
yeah, I mean, one of the papers I showed looked at the timeline of invasion across multiple lakes, and 10 years is enough for them to get pretty well established.
I think we're in the beginning of it. Can they land on sand and multiply there, or rocks, or both?
Right, yeah, they can. The quagga mussels can, lay on a soft bottom and become established. They can also attach to rocks. Of course, in shallow areas where there's a lot of wave action, they'll be disrupted periodically. But yeah, when they're kind of below the depth where the wave action is going to affect them, then they can kind of just lay on the bottom.
What have they done to the zebra mussels?
What did they do to them? Well, again, I can't say specifically for Torch Lake, but that is the typical trajectory in a deep lake, is that the quagga mussels would displace the zebra mussels over time.
Okay. You all set?
I think so.
Okay. Mark, thank
Thanks,
you very
everyone.
much. All right, we've got one last presentation. Wayne Lancaster got his arm twisted like Trish's, and he volunteered to try to give us a very brief update on our plans for our mussel survey this year.
Well, this is right up my area of expertise. I'm a tumor virologist, so this should work out well. So I got introduced to this Torch Lake Protection Alliance and stuff that's going on here last summer. And I've got a grandnephew, Josh Vey, who works for a company that does underwater surveying. And I just kind of asked him, I said, geez, we should survey maybe Torch Lake for quagga mussels. And he said, yeah, that sounds like a good idea. And he's trying to finish his bachelor's degree at Northwestern Michigan College with a senior project. So if I could have that next slide. We know that the mussels are in the lake. There's been some videos showing that. And we need to identify just how bad it is. And Josh has proposed to, as a senior project, to do a little bit of a survey using the facilities of Northwestern Michigan College. And John Lichko is going to help him apparently. And they've got an ROV that can do depths of 300 feet. And it plans to use that device for doing video documentation. And then he wants to use a multi-beam sonar and also to determine temperature and salinity measurements. And he's got some other stuff that that they use in these surveys that he does that can do all kinds of interesting things and generate data. And he's planning on doing this sometime in mid-June. So I think maybe the next slide here would. So he's in South Africa right now, apparently surveying something underwater. And when he comes back in June, he's going to get the boat from Northwestern Michigan College. It has this ROV on it. And I'd like to go along with him to see how this all works out. But I think it's really imperative that we know what the hell's going on down the bottom of this lake. And it also is going to be, I think, fairly critical to determine where he's going to scan. It's a big lake. You can't do the whole lake, obviously. So the area that he's going to use all this instrumentation to give us some idea about these mussels, I think has to be really carefully selected. And it would be interesting also to take the data that he can generate and try to link it up with any of the data that's being generated by Dale. So that's kind of like where it is. I don't know much more about it. I mean, we can talk about human papillomavirus. I can do that all day.
One of the things that I think we really have to do before he starts, just 1 minute, is before he starts the survey is, I don't want to get like, Fred was saying, well, we want to measure another thing. We really should make sure that maybe he talks to Mark to try to figure out what can he actually, given his equipment, what kind of measurements would he need? And so you don't want to have it all done and then say, oh, shoot, we forgot to get their width, something like that. And so it'd be really good to try to get him to talk to somebody like Mark and say, these are the kind of things that ultimately we would need from the
Sure.
survey.
After hearing the presentation, I think it's pretty imperative that's how it should work out. Yeah.
Any more questions? Come on, you got to give Wayne a little bit of work here. He raised his hand first.
This isn't so much a question as just a follow-on comment. We did some work at Tahoe with, after Asian clams were discovered, the idea of trying to get a survey of where are they. They only really exist in shallow water. And there we used an autonomous underwater vehicle, basically a submarine that could be programmed to stay 1 meter or any depth off the bottom and just cruise and use both sonar and imagery to quantify it. So that, I think Josh's work is great with an ROV. It's just time intensive. So, but it may be a great first step to see what's there. And
Yeah,
maybe-
if they go over if it's possible in subsequent years to go over exactly the same spot, just
Yeah.
to see what the trend is.
Yeah. But here it's essentially programmed and it will go, I mean, it can do the same spot and it can run continuously for 8 hours taking images. So it's just a further technology trying to establish the same thing.
Yeah, as this project comes together, I only chose to publish one photo in our report, which was when we started, we attached a GoPro to the Ponar dredge. But when we got our video back, we didn't even know if we'd be able to see anything at 75 feet. The images were so clear and nice. We ended up doing several transects with the GoPro where we had no Ponar. We had a weight ball dragging on the bottom. The Ponar was above it and pointed ahead of the plume from the weight ball dragging on the bottom. And we did a number of transects from 100 feet up to 40 feet. Those files are huge. I can't send them to you, but I could make them available to Josh if he's interested, just to give him an idea. They're amazing videos. This was done throughout June and July. I don't know if we actually got out in early August or not, but mostly June and July. So not the very beginning of June. These are high school students that we were working with. So I think our first day on the water was probably the second week of June. And we went out every Thursday. I think 7 trips they took.
This is where the data starts to mix together. And there's quite a change in water clarity out here. We're going from 18 meters down to 4. And that means the amount of light down deep is going to be changing dramatically. And so sometimes if you're going to do something you're doing earlier in the year or later in the year, would probably be better. Sure.
Okay, and that's going to be driven by the availability of the equipment. And that's where, fortunately, Josh did get a semi-commitment from the university for June, okay? So that works out. I think that what we want to do, and you mentioned it, and it's correct, we want to talk to Mark. I think that Trish's information on the villagers, where the concentration was, is an input. I think that the Three Lakes Association went down to what, 175 was the deepest you went? So I think what we want.
But, you know, these Ponars, trip them and get it correctly tripped and take a sample. When the line isn't vertical, it's tough. And we were subject to the days that we went out.
Yeah.
So ideally, we, you know, if we didn't have interns involved, we'd have been out there early in the morning. But we did have some issues at the deeper depths. So, but most of the bars were 75.
Yeah. So I think the other thing we want to do, I think we want to overlap, but then cover the deeper areas that you did not, so that we get the most value out of this study to, again, support the other work that's been done and give us the greatest amount of information of the overall lake.
And that's where the ROV would be most beneficial in those deeper zones where the Ponar drop becomes really labor intensive.
Yeah, yeah. And I think it's going to be the same ROV that they use at Elk Lake. I think it's going to be, but I haven't been able to confirm that yet. We're going to ask Josh to confirm that for us. Oh yeah, I got a couple of them here, but we're going to lock the door and not let anybody leave until they got the surveys turned in. But one other thing is, what we did not do, we kind of mixed it in. We were going to try to have more of an interactive section at the end, and Dale reminded me that, because is Leslie Meyer still here? No, she's not. Oh, there she is. Did you want to give a little bit of an update on some of the things you're doing? Well, I think it's worth it for everyone to hear, because again, this is part of our collaboration effort, is to make sure that we know what each others are doing and how it interacts with the others. How late is it? Oh, we're fine. The hors d'oeuvres don't set up till 5 o'clock, right?
I can talk fast. Anybody that knows me know I can talk fast. My name is Leslie Myers. For those of you that don't know me, I am known as the Dam Lady. So I'm here to give you a dam job update. So I wanted you guys to know, every one of the scientists, etc., that we do have the HEC RAS and the HEC HMS at the county that was just completed. We have a total of 2 people fully trained to use that software and 2 people that are half trained. So if there's somebody that would like to use that data, it is available. That data was also used to update all of the flood maps in the county, and that's going to be coming forth in the next 6 to 8 months. So those of you who haven't looked at those maps, that's all going to be available quite shortly online for you guys to be able to take a look at. I'm going to be putting together a press release for the floods issue so that you guys can share it with your membership, and it'll be shared with the general public. The county had 4 townships and 1 village that were in the floodplain. But come 2025, every township and every village in the county will be in the flood map at this point.
They'll be considered in the map, but not necessarily.
They might not be in it, but they will then hopefully have the ability to buy flood insurance. I'm now working with talking to all of the townships, because one of the hardest things that's going to happen here is that half the townships don't have zoning, and they're not going to want to adopt a rule that they have no one that can enforce. So we're looking into that.
Years ago, what happened along Lake Michigan. Okay. So several years ago, about 6 years ago, the high water mark was questioned, and a study came out, and they basically changed what the definition of the flood zone meant along the Lake Michigan shoreline. And so suddenly people got letters in the mail, you're eligible for flood insurance. That wasn't the problem. The problem was it went to the bank, and the bank in Elk Rapids, which is now closed, sent letters to all the homeowners saying your mortgage will no longer be valid after this year unless you purchase flood insurance. There were people that literally could not afford to stay in their home because of the cost of flood insurance. So I think that there's a lot of unintended consequences if we end up putting people in a situation where suddenly, and maybe not correctly, think that they're in a flood zone. So there's a lot of history right in that office over there of a lot of angry people.
Got it. And I'm doing my very best to let the municipalities know the pros and cons of doing what the next steps are. However, we knew that those floodplain maps were coming. They started the project right before COVID. It got sidelined, and now those maps are ready to be done. So if we do nothing, mortgage companies might choose not to give mortgages anyway to begin with. So there's a lot of things that could happen. But that's coming up, and that information will go out to the lake associations next week. And then also, because of the HEC-RAS and the HEC-HMS model, we did some additional modeling on both of the dams. We found out that the Bel Air Dam had some issues, and that in the event of a 100-year storm above the dam, we would overtop the banks. So we wrote a dam grant through the Dam Risk Reduction Program. And it was announced yesterday that we received a $500,000 grant to do the engineering for the rehabilitation of the Bel Air Dam. And then we will then apply for some funding for next year as well to help us then do the construction. But we're going to determine what it takes. So we're working on it. I also met yesterday with the engineer over in Elk Rapids to talk about the Kids Pond spillway. And we're looking at it all. It's front and center. And the good news is that the state of Michigan's very interested in making sure that those dams that are around town are going to be viable, because nobody wants another Midland. So that's all I have. Thank you.
Question for you. We now have a couple gauges on the system right here. Are those going to be something that would be?
I have them on my phone.
Okay, that's what I mean. Are those things that will be useful to?
Oh, very much, very
okay.
much. And I've been using them. The neat thing is okay, the USGS looks really good, and takes a lot of time to get through there. But I found this really great app that's for kayakers. And when I need the quick abbreviated, I can look at any 3 gauges just right here by pushing a button. So thank you. Yes, sir.
In many parts of the country, what was the historical 100-year storm is now 10 years, 20 years. So which are you using are they using the historical, or is it a new climate change?
I'm going to say it's the historical. I have no reason to believe that it's anything other than what I've been working on for the last 20 years. I cannot address that. That's the Village of Bel Air. However, I will let you know that that's my backyard, so I care. So, and my good buddy Fred right next to you probably knows more about it than anybody else in this room that I know. But I cannot answer what their plans are. I work for the county.
Because it's come up a couple of times in our project team, we all talk about it, but nobody knows what to do about it. What can we do to get, to drive action?
Come to the meetings where you can speed up it. Well, no one's discussing this. It's not in the paper. Permit is up for renewal in October. My suspicion is that Eagle will increase the amount of phosphorus that's permitted. It's right now 120 pounds over a 12-month rolling period. They were at 200 in 2023. When you try to point back at past data, they say it's unreliable. There are so many layers to this I couldn't tell you right now.
Well, we're going to try and resist that permit approval along with.
Well, the first thing we got to do is call for a public hearing. We have that opportunity. The second thing is
George told me he would help support us.
and then we need to get the information out. There's a lot of levels to this. It was all started due to management issues. Those are behind us. Because right now the state of Michigan is helping us manage this wastewater treatment plant. But all the work of bringing a 1980s level facility up to current standards and handling the growing capacity demands, that's all still ahead of us.
It's a tough one. Jim?
Are you using the intermediate gauge, or are you happy
Yes.
with it? Okay.
Okay.
You're happy with it?
The intermediate gauge is what I have to use because the court order is based
Yes.
on the intermediate
Okay.
gauge. So that's the most important one that I look at.
Okay.
But then you got to remember, here I'm dealing with a court order to maintain a level at a certain space from a gauge that's 8.5 miles away from where I have a gate. So quite honestly, after all of the non-precipitation that we had last winter, everything was dry. This rain has been a blessing, and I'm letting everything soak in, and we're a little high right now. So if anybody's a little concerned, I will be changing that shortly, but I want to recharge the back areas because it's been so dry for so long.
Okay, well, let us know if you have any issues.
Yeah, thank you. It's really nice to have the other gauges. Thank God they're all in the same datum.
You got another question?
Because we have 3 datums here in this county.
Don't leave.
Thank you.
I have one question. What's happening with Rug Pond?
Rug Pond over in Kalkaska County?
Is that?
No, it's not me, but I did hear that a plan was finally written and adopted by Kalkaska. And I don't know if they're still looking for funding. Maybe Becky. Did she go and hide?
I think she left. She's probably over there having a drink already, where the rest of us should go.
Yeah, except for she doesn't drink.
No, no, but she's going to join us over there. Okay.
But Becky might know a lot more about that, and we used to talk about it at the Urkel Whippet meetings a lot, and that has changed a little bit of what they talk about over at the Urkel Whippets. So last I heard, there was a plan written, and maybe a good call into the guy that runs the conservation district, Mark Randolph, could tell us. But last I had heard, they did have a plan.
Okay, you have an announcement to make?
Okay, before
Thank
you
so much.
depart, we need you to, would appreciate you filling out your blue survey sheets. And we have leftover food, so we hope you will take sandwiches and cookies and vegetables, etc., because they won't keep. We'd like to share.
We might need some help from some people with the chairs and stuff too.
And after you get your food stash secured in your car, please help put tables away. Thanks.
Steve, I need your help with the tables. Okay?
I don't know what Tom wants. Ted, where do you want the survey?
Steve will help us. Well, I'll tell you. Well, take enough notes?